Welcome. Can you see and hear me, Santiago? Good. So I'm going to send a message, and this is also a response to the message, the question that Gergo asked. Is this going to be streamed live on YouTube? Yes, it is. And actually, I'm going to send that link to Haskell Cafe. For anybody who's not registered, they can still follow the talks. Did I copy it right? Yeah. So anybody who wants to and has the link can now watch our presentations online. Welcome, everybody. Let's see how we are for people. 17 in the session. I've already seen the first two speakers. That's Toby Bailey and Rudy Matila. Finn, are you around already? Don't see you yet. We still have a few more minutes, so we started a bit early so that we can communicate the link at YouTube to everybody. I hope a few more people will drop in, of course. Let's see, let's go. If things don't go so smoothly as at first, blame it on my inexperience here. We did do a practice session yesterday, but it's quite different from how it works at ICFP. So I'm going to pull the first speaker to the stage. This is Toby Bailey. So we can start up with things. There's Toby.
Hello.
I can hear you.
Oh, brilliant.
I can see you.
Yeah, that's good. I can hear and see you as well. So.
All right. So I think you can start sharing your screen if you want to set things up.
Okay, I will do.
And then I'll introduce you.
Okay. Okay.
So for our the people in the audience, if you go to conversations, there's typically conversations and people's in session. So with people in session, you know who's there. With conversations, there's particularly chats and Q&A. In the chats, I think you can put remarks, but if there's a question you'd like to see answered at the end of the talk, then it's better to type that into the Q&A, and then I can pull that to the stage, and then later on, and then you can ask your questions and we can mark them as answered. And you can also try to raise your hand if there's really something that needs to be in terms of interruptions. Of course, if the speaker wants, they can also react to questions in the Q&A if they can see them. But I think if there's something really that you would like to have immediate reaction to for some reason, then you use the raised hands facility. And we're trying to keep an eye on everything at the same time and hope that the internet stays afloat. So still a minute to go, but we are not in a, I think, in a very big rush. Give people the time to. We're now a healthy 33 people with Yu Kong entering. Welcome everybody. And the structure is relatively simple. We have 3 presentations first, and then we have a break, and then we have the keynote, the first keynote. Then there's a break again. Although it says the keynote is 90 minutes, don't worry, it's only 60 minutes, but this is the way that the system works. The last 30 minutes of the keynote are actually break time. So you don't have to worry about that. And after that, we start with the final, the 2 papers of today, and then I give a short chair report, and that's the end of today. And then tomorrow we have basically the same setup with, again, 5 presentations and a keynote. The idea is that Toby will talk for about 25 minutes, and then there's 5 minutes time for questions as usual. But like I said, if you have questions along the way, you can put them in the Q&A. You can put remarks in the chat. And I see Richard coming in. So before we start, I prefer to see if I can make Richard co-host. Because that means that if something goes terribly wrong on my side with my machine, then he can take over. Right, so you're now co-host, Richard. All right, the link is at Haskell Cafe. Let me check if the mail has arrived there. Yes, it has. Good. So maybe we'll draw a few more people in. So I want to start the symposium. So welcome everybody for making it to the Haskell Symposium. This is a 2-day symposium. Both days are not very long, which to some extent is also quite nice because it means that I could put all the presentations in an area where most people around the world can actually make it without any losing too much sleep. The first presenter today is Toby Bailey, and he will be talking about Haskell, how to model a 2-player game at the type level. Go ahead, Toby.
Thank you very much, and welcome everyone. Hello. Yeah, as mentioned, I'm Toby Bailey, and I'm going to be presenting Haskell. So let's get started. So the way that Haskell was born was, if you play chess terribly, like me, you're always being corrected by your opponent. But what if instead of that, you were corrected by a computer program? But what if instead of that, you were corrected slowly by a compiler? And so Haskell was born. So here we can see a valid move by a white pawn in the game of chess. You don't need to know chess for this talk, by the way. I'll explain any relevant rules as and when they become relevant. So yeah, here's a valid move by a white pawn from square e2 to square e4. And we express that in Haskell as follows. And if you compile this game with GHC, it successfully compiles with no problems. But here's an invalid move. They're moving to square e5 that they're not allowed to move to. And we express that in the same way. The pawn's moving, we specify the origin square and the destination square. But this time, this particular game won't compile with a type error, saying that there's no valid move and pointing you instead to where the pawn could move. So Haskell started off as my 3rd-year dissertation project. It contains a full type-level model of all International Chess Federation 2018 laws of chess, the ones that concern the game, that is. And it comes with a Haskell EDSL to interact with that model. And, of course, Haskell's type features made this a really smooth process, right? Well, no, it did not. There were a few hurdles, and this talk is going to take you through some of the interesting hurdles and some of the interesting problems we faced. So first of all, let's do a little comparison. This is beloved open world game, The Witcher 3, at the highest graphical settings. And here is a 10-move Haskell game. So the memory usage of The Witcher 3, it's about 3.5 gigabytes on average. That's pretty good. It's got an open world, lots of dynamic actors. And here it is next to the memory usage of Haskell. So as you can see, Haskell's memory usage was a bit of an issue during development. At the core of Chescal, I'm just going to give you a quick overview of how Chescal works. At the core of Chescal is a central type family move that basically takes in the board state, it spits out a board state in which the move has been made, and you pipe these together ad infinitum. So a value level equivalent could very well have this type signature. You take in the origin square, the destination square, the current state of the board, and it tells you the new state of the board where the move has been made. So to have the code be as idiomatic and reusable and clean as possible, we looked for a solution to partial application at the type level. And unsaturated type families are really exciting, but unfortunately, they're not available yet. And so in the meantime, we chose a different solution, first-class families devised by Li Yaoxi. And I'm just going to briefly introduce that and give an overview. So as we all know, you can't partially apply type families, but you can partially apply type constructors. So let's say that you want to be able to partially apply an addition function at the type level. So you make a data type to hold the arguments, but you need something of kind star. So you define a new type x from a to star, which allows you to basically hold all of the arguments for this function, but you still need a way to evaluate those arguments. And that's where an open type family called eval comes in. And you define an eval instance for those arguments, and then you're able to partially apply them. And of course, if you want to evaluate it, you just call eval on the argument list, which is wrapped up in your custom type. So with the following definition of map and a definition of our own version of type level plus, we can now map over lists at the type level, like so. So in Chescal, each turn of movement is expressed as a first-class family. So here's that move function that we were talking about earlier. It's a first-class family here, origin position, destination position, current state of the board, and it returns the new state of the board. And thanks to the use of first-class families, we can extend this with rule checking rather naturally using a type level version of function composition. So from right to left, you have the pre-move checks, the move itself, and then the post-move checks. And as for the Chescal EDSL itself, we define it using continuation parsing style. So we basically define type spec, which can simplify the type signatures a little bit. And this is the start continuation. It passes in a proxy type start deck of kind board decorator into the continuation, where start deck describes the initial board state. And we use more continuations to move pieces around the board. Here's one for pawns, just so that you can see. And here's the last continuation that ends the continuation stream, and also the Chescal game. So now that you have an overview of how Chescal works, let's talk about a few of the hurdles. So one of the most common actions in a chess simulation, it occurs at the end of each move, is determining whether one of the kings is in check. And a king's in check when they can be attacked by a piece of the opposite team. So the old approach for checking whether the king was in check relied on move lists. So here you can see a white bishop at square c5, and I've highlighted all the positions that they can move to. A move list for this bishop would just be a type level list of all of these highlighted positions. And the old approach for checking for check would be to get every move list for every piece on the opposing team to the king, use a first-class family version of concat to append them all together, and then check if the king position was in that list. And as you can imagine, this old approach was incredibly slow. So to verify how slow it is, here is the definition of the first-class family move. And here you can see the check for if the king is in check, check, no check. And here's the pre-move checks and here's the post-move checks. So an 8-move Chescal game using this old approach would compile in 1 minute and 37 seconds using 23 gigabytes of memory. But if we comment out the check for whether the king's in check, then that same game would compile in 24 seconds and only using 8 gigabytes of memory. So we know for certain that checking if the king's in check is definitely the slowest part of the move. It adds an additional minute to compilation time. So when compilation times grew and we were experiencing some out-of-memory errors with GHC, we started looking at where we could make some optimizations, bring down memory usage and compile time. And we were trying to think of how we could optimize the check code. And of course, as one of the first things that we're taught, one of the first things that all computer scientists are taught in their undergraduate degrees, you should turn to algorithmic improvements. You know, we're taught about big O notation and how you should bring it down. So we started looking into some improvements. So the new approach is essentially to, from the king's position, simulate other pieces' movement rules. So here you can see the king at c5 simulating bishop movement, and because it can reach a bishop of the opposite type, that king is in check. So instead of appending together a bunch of different move lists, we would instead compute essentially one extended move list. So this, with the old approach, a 10-move chessable game at the time would cause GHC to crash and run out of memory. But with the new approach, a 10-move chessable game would cause GHC to crash and run out of memory. So while attempting to diagnose why this was happening, why the algorithmic improvements weren't really changing very much, we moved out pre and post move checks into two separate definitions. So here's another definition of move. As you can see, we've moved out a lot of the checks into its own first class family called move with pre-checks. And just splitting out the definitions like this caused that 10-move chessable game to compile in 1 minute and 30 seconds and using only 25 gigabytes of memory. So, you know, the lesson to be learned here is that sometimes algorithmic improvements can be less effective than fiddling with the type checker, at least in this case. On to another attempt optimization, finger trees. Haskell move lists are, you know, Haskell singly linked type level lists, so appends are ON, and these move lists are combined dozens of times each move. So we tried to look for an appropriate data structure with improved append time. So we turn to 2-3 finger trees. Here's a part of the definition for finger trees at the type level, which we implemented to try and alleviate some of these issues. And we implemented custom first-class family equivalents of append, folder, fmap, just so that it could be a drop-in replacement for those first-class family equivalents that we defined for the normal Haskell type level lists. So after we'd put in the branch with a finger trees, we found that compile time did in fact decrease by a tiny fraction. It decreased by about 5 seconds. So once again, algorithmic complexity wasn't responsible for the unpredictable compiler performance, but if anyone needs some type level 2-3 finger trees, feel free to ask. So let's talk a little bit about type applications and type signatures. So let's say that you have a declaration, something of type proxy int, and you need a way to assign it an expression of type proxy int. One way of doing that would be, you could use a type application, or you could also use a type signature. And in this case, you'd expect the two of them to behave incredibly similarly. Basically, functionally, you'd expect them to do the same thing, right? Well, as we explained earlier, the game begins from some initial board state. So the type start deck of kind board decorator. And the first version of start deck was constructed in code basically through a bunch of type family applications that were rather expensive, lots of setting the pieces through code rather than writing out the definition. So here is the type, okay, my bad, let me restart. So here is the definition of chess, the first continuation in a Haskell game, and it's using a type application. And this definition, when you compile just this definition on its own, only uses 46 megabytes of memory and compiles in close to 1/4 of a second. But if you instead use this definition of chess with a type signature, you'd expect them to behave rather similarly. But actually, here you can see the memory usage compared between the type signature and the type application version. But the type application version is, in fact, on the graph. It's dwarfed by it. The type signature version uses almost 26 gigabytes of memory. And it took so long to compile and was starving so many of the other resources that it wouldn't compile. It was sent sig kill by the OS after 3 minutes and 10 seconds. So because this behavior is unexpected, we filed a GHC bug report. And in the meantime, we wrote out start deck's definition in full in the Haskell source file. And you can use either definition with no problems. Now let's talk about some descriptive error messages. So originally, the error messages in Haskell were intended to include the exact move that violated a rule of chess. So for the incorrect game that you saw earlier that fails to compile, we were hoping that the error message would be more along the lines of explaining the error, but also pointing you towards the exact move that has caused the problem. And we can achieve this by including the move number and the type that represents the game board, the board decorator. So as you can see, the board decorator, it contains the board, but it also contains some useful information, such as the currently moving team, the position of the kings, and here you can see the move number. So we include it in the board decorator. We implement custom type errors in Haskell like so. So using first-class families again, we essentially just define a first-class family wrapper for type error. And we can easily modify this definition to include the specific move that results in the error. So at this time, you don't just pass in the error message, you also pass in the board decorator. And so you return the type error and also some extra information at the end, just saying the exact move that caused the error. So here's that same game again. And here it is without the additional move. And without the move number, not without the additional move, without including the move number in the type error. Without the move number, it compiles in 19 seconds and uses 4.5 gigabytes of memory. But when we add the move number to the type error, suddenly it takes almost 2 minutes to compile and uses 26 gigabytes of memory. But strangely enough, taking other information from the board decorator, like the king positions, and putting it into the errors doesn't cause similar spikes. The behavior was unpredictable and we couldn't figure out why. So we turned to our most creative solution yet, and I'm particularly proud of this one. We cut the feature. Haskell error messages do not contain the exact move that resulted in the type error. And finally, let's talk a little bit about Haskell shorthand. So here's a comparison between Haskell syntax and algebraic notation, which is one of the standard ways of describing chess games. And as you can see, the Haskell syntax, it's noticeably longer and more verbose. And so we were thinking of creating an optional shorthand syntax that people could use if they'd rather express it in something a lot closer to algebraic notation. So essentially this 5-move game would become this in the shorthand. It's a lot shorter, it's a lot closer to algebraic notation. As you can see, you're not specifying the origin square anymore, just the destination square. And you leave it up to Haskell to calculate the origin square based on the piece that's moving and the destination square itself. And we thought, it'll only be a little bit slower. It's only a little bit of extra work, right? So here is a 10-move Haskell game. And as you can see, it's using the longer syntax. And this takes 3 minutes and 25 seconds to compile. But now with the shorthand syntax, it's the same game, but now we're not specifying the origin square. This takes 1 minute and 20 seconds to compile. It's under half the compile time, and we see similar reductions in memory usage just through this the implementation of this shorthand. And we were thinking, this could be because there are fewer continuations, but no, unfortunately, we're still not entirely sure for the exact cause of the improvement, because here's the shorthand when compared in terms of memory usage against other non-CPS versions of the code that rely on function composition and function application, respectively. And more than 2 moves, the games that we tested were only 2 moves, because if we express games that were longer than 2 moves, then GHC would crash when using either of the non-CPS variants. So ultimately, without intimate knowledge of the compiler, without working on GHC, performance is wildly unpredictable and it's hard to reason about. And it's quite telling that the most dramatic performance improvement in Haskell was completely unintentional. And so some tools for measuring type level performance or a clearer model of how your code gets executed when you write type level code would be incredibly helpful for those who are writing code at the type level in Haskell. And additionally, one of the reviewers of the paper suggested avoiding the move list approach. So instead of searching through move lists for each move, we take into account the fact that behavior at the type level is strict and those lists aren't going to be lazily evaluated. And so we generalized the array-based approach for check to be used for all move calculations in Haskell. So here is a bishop at a7. And previously, if you wanted to know if a king at c5 was in check, you would get all of the bishop's positions, you'd get the move list, and you would check, is the king's position in that list? So yes, it is. And instead of that, we use raise. So to know if a bishop can move to c5 at all, and not just for check, we shoot out a ray from c5, mimicking bishop movement, just like we did earlier for the check code. So you send out the rays in each direction, one by one. And so to know if a bishop can, in fact, move to c5, in this case, we only shoot out one ray. So we don't have to consider the rest of the positions. And it's a net reduction in the amount of work that you're doing. And the results from using rays, the performance increase is noticeable, especially for pieces that have really expensive move list calculation, like queens, who have to basically do all the move list calculation that bishops have to do, and all the move list calculation that rooks have to do. And some games that previously were failing to compile because they would run out of memory now, in fact, do so. So here's a 10-move game. And the move list approach uses 30.4 gigabytes and compiles in 110 seconds. But the ray-based approach slashes memory usage in half and takes a fifth of the time to compile. But unfortunately, the increases and improvements aren't completely straightforward. So here's a different 10-move game. And the move list approach used about almost 18 gigabytes and compiled in 26 seconds. But the ray-based approach actually saw an increase in memory usage, even though there is a slight reduction in compile time. Overall, across the benchmark suite of the Chescal games tested, performance did improve with, however, a few games were displaying increased memory usage and or compile time. The lesson here is that Haskell idioms, such as searching through a list for something, don't always translate to the type level, and you should take the strict performance into account. But even when you do, performance can still be very unpredictable. One of the big things in GHC9 is talking about compiler performance improvements. But sadly, we haven't been able to test Chescal and GHC9 to see if any of these improvements bring down memory usage or compile times because of some of the changes to the type checker. Simplified subsumption does not play well with some of our continuation passing style code, and we're not in a situation where we can easily eat or expand some of the types that we're using. But if anyone has some tips for getting this kind of code working with GHC9, please let us know. There is, of course, room to expand Chescal further. We could implement a session-typed version of it to see how that affects memory usage and compile time, and use it in combination with the existing Chescal type-level chess model. And we could also, to try and bring down memory usage, investigate a type-level bit vector implementation using NATs and pattern matching. So currently, currently the chessboard is basically a vector of vectors, and so that could bring with it some substantial memory usage. And so using just NATs has the potential to bring down memory usage, but of course it would make the code a lot more obtuse and harder to reason about. So in conclusion, we have presented Chescal, a full type-level model of chess, which enforces all of the rules in the International Chess Federation laws of chess, bundled with an EDSL for describing chess games and for creating custom chessboards, which uses this type-level model for all of its rule checking, and some interesting findings on compile time and memory usage, which hopefully will be of use to the implementers and maintainers of GHC. Thank you very much. And yeah, thank you for listening. And now we're open for questions.
Yes. So I'll do the applause. Everybody can use the pictures. So there's a few questions lined up on the Q&A. So I'm going to pull these to the stage, starting with Rudy Matilla. So this is the question that Rudy poses. Maybe you can answer that question if you can.
Yeah, of course. Should I read it out first?
Well, I think everybody can read it. So,
okay.
But it's your preference.
So we ended up testing it at different stages in development. It would be tested on different devices. The one that we tested it on for most of the benchmarking towards the end has 32 gigabytes of RAM. It's a Windows 10 machine. And as for some of our tests ending up using swap space, some of them did. On some tests on the Mac operating system, it would go beyond the actual RAM limit of the device and would be extensively using swap space.
Okay, so I think this is an answered question now. And the next one I'd like to pull to the show on the stage is by Jeremy Gibbons, but it's actually in two parts. So maybe I'll just invite Jeremy to the stage so he can ask his question live.
Mm-hmm.
Hi, Jeremy, go ahead.
Nice talk, thank you. So part one is on the screen. These outrageous compile times, they don't smell to me like they're something to do with the wrong implementation of lists or the wrong implementation of sets or the wrong implementation of intersection or anything like that. There's something much more fundamentally taking exponential time when you'd hope it would take quadratic time. And so part two says that's something I can't tell whether that's because you've accidentally written a quadratic time algorithm in your types, or because there's a bug in GHC and something there is sorry, you've accidentally written an exponential time thing, or whether there's a bug in GHC. Did you investigate that? I mean, it seems to me like quadratic improvements are just moving the deck chairs around, and your Titanic's going to sink anyway at the moment.
Yeah, I completely understand what you mean. So we did do some investigating over the course of, so basically several months were spent trying to optimize and bring down compile time and memory usage. And so, of course, we did some investigating. Of course, there's always the chance that I've missed something. But in any of the cases where I spotted some of the more egregious examples of implementing things in quadratic or exponential time, as you've said, we did address those.
Okay, thank you.
Okay. I'll kindly remove you from the stage again, Jeremy.
All right.
Mark has answered. So I think the next one I'd like to pull to the stage, a question that I want to get to the stage, is by Dominic Orchard. So he says, does en passant ruin everything?
It certainly came close a few times. So en passant, I'm afraid I'm still not sure how to pronounce it. I'll say en passant. So en passant capture was one of the last rules that we implemented. And it was what led to the use of the board decorator type rather than just the vector of vectors being passed around between the continuations, because we needed information on the last move made and the pieces and how long the game had been going on and that kind of thing. So fortunately, en passant capture is part of Haskell. It's in there. You can compile games with it, and it will fail to compile if you try en passant and you mess it up somehow. So no, fortunately, it doesn't ruin everything, but it was definitely one of the pain points during development.
Thanks. So another one that got a vote here is the following question by Noon van der Silk. Do you think GoCal would be easier for GHC to compile?
That's a brilliant nickname for it, and maybe PhD project right there. I personally haven't tried, so I don't want to. Having seen some of the unpredictable behavior and compilation times, I can't say for certain. But I believe that Go moves are time agnostic, so you don't need nearly as much information about the previous board state as you would with chess. So my gut reaction would be that it would probably be a bit easier because you might be able to cut down on the amount of information that you're storing. But I wouldn't be entirely sure without trying it.
All right, thank you. So there's still quite a few questions lined up. I'm not sure because all the other ones are not yet voted on. So I'm not sure which one to pull to the stage as being most interesting at this point. I think it's good that if you later on that you go through all the questions and answer them to the people who posed it. But of course, we have a time limitation here. So maybe we should actually stop at this point so that the next speaker can set up. And I hope you can answer these other questions either through chat or directly to the people involved. So thank you all for your questions, and thank you, speaker, for answering them and giving your talk. I'm going to kindly remove you from the stage. And I'm going to look for the next person to invite. That's Rudy. If I can find Rudy among all these people. Yes, there's Rudy. Rudy,
hi everyone.
How are you doing? I can hear you. I can see you. Maybe you should.
Can you hear me?
Sharing. Yes, I can.
And is the audio good? Audio good?
No, it's good. Yes.
Okay, cool.
Just share your screen.
Yeah, let me share screen.
Yeah, I can see your slides.
Cool.
All right. So Rudy Matila will now give his presentation on express applications of dynamically typed Haskell expressions. Go ahead, Rudy.
Okay, thanks for the introduction, Julian. So hi everyone, my name is Rudy. I'm going to present my paper at the Haskell Symposium 2021 titled Express Applications of Dynamically Typed Haskell Expressions. And I'm not currently affiliated to any company or university, and this work was developed indefinitely. So this work is about a Haskell library called Express, which allows us to manipulate applications of dynamically typed Haskell expressions. This library is available in Hackage and can be installed as usual with command install and imported with import data express. But what is it about? Well, the Express library can be compared with the data.dynamic library. Data.dynamic encodes dynamically typed values, and data.express encodes dynamically typed expressions. And Express is itself implemented as a wrapper around data.dynamic that extends it with several features, such as pretty-printing, delayed evaluation of applications, support for variables, and expression matching. And we'll see that these extensions allow Express to be applied in a few surprising applications, such as conjecturing specifications, property testing, and program synthesis. Now let's take a look at, before we look at the example applications, let's take a look at the library itself, at Express. And let's start with the representation of expressions. So at the core of the library, we have the expert type, which represents a dynamically typed Haskell expression. And each expert is either a terminal value or an application between experts. And terminal values are encoded both as a string representation for pretty-printing and pattern matching, and as a dynamic value, which can be pulled back into a regular Haskell value. To construct terminal values, we can use the value smart constructor. And the value smart constructor takes a string, string representation, an actual Haskell value, and returns an expert. And we can also construct terminal values with the vol smart constructor, which is for show instances, which simply takes a Haskell value and returns an expert. Let's see them working on GHCI to maybe clarify how they work. Here's a definition of a value 1, which is an encoding of the value 1 of type int as an expert. If I check the type of 1 in GHCI, it will say expert because it is of the expert type. However, if I evaluate 1 on GHCI, I'll see 1 of type int. And that is due to the show instance of experts, which pretty-prints them as the string encoding of the value paired with the type of the value. Here, I'm encoding a function as an expert, as a terminal expert. Here's the plus function, and I encode it as value string plus, and then plus bound to the int argument type. If I check the type of plus, again, it's an expert. But if I evaluate it on GHCI, I get a pretty-printed version of it, which is again due to the show instance of experts. And I can take our previously defined values plus and 1 and apply them to each other. So apply plus to 1, and I get the 1 plus section of type int to int. And I can further apply to another 1 to get the value 1 plus 1 of type int, to get the expression 1 plus 1 of type int. And Express also provides a function called evaluate, which is able to pull back an actual Haskell value from the expression. And here I'm evaluating plus apply to 1 at the type int. And I get the 2 value because 1 plus 1 is 2. And it's a maybe here because it returns nothing when the type doesn't match and returns just a value when the types do match. Let's take a look at another simple example, heterogeneous lists. So we can declare a heterogeneous list of values using Express by doing like so, x's of type list of expert, and then we declare each value in the list like before. So for example, here I'm encoding the value true, the Boolean value true as an expert, and here I don't need to bind the type of true because it's already monomorphic. And here I am encoding the values 1 and 2 of type int, then the function end, then the function adds. And I can write map evaluate on x's of type list of maybe int. And I get nothing, just 1, just 2, nothing, nothing. So that means I'm trying to select the values that are of the int type, and I get nothing for the values that are not of the int type, and I get just the actual int value for values that are of the int type. And Express provides also this other operator here, which is I call it $$ or $$. And it applies two expressions and always returns a type correct expression or nothing when the types do not match, do not fit together. So here's an example. I'm taking f values from x's, the x's from the previous slide, and x values from x's, and running f $x and concatenating the values that are just values. And I get and apply to true, abs apply to 1, and abs apply to 2. Before we look at the example applications, let's take a look at another feature of Express, which is encoding variables. We can create a variable represented as an expression in Express using this var smart constructor. It takes a string, which is the name of the variable, and a type representative, a, and returns an expert. This is just a proxy value, although I didn't use a proxy tag, but. So here's how we can declare an expert representing a variable x of type int. I just do var string x and then pass the representative undefined of type int. Here's the same thing for booleans. So here's a variable p of type boolean represented as an expert, and I declare it as var string p and then an undefined of type representative. And of course, we can use these variables inside expressions like plus apply to x apply to 1, x plus 1 of type int. Okay, now let's move on to our first example application, which is conjecturing equations based on the results of testing. Our goal is to have a function speculate about of type list of expert to list of expert that, given a collection of Haskell symbols encoded as experts, a collection of Haskell functions encoded as experts, such as nil, cons, and append, it prints a bunch of equations about them based on the results of testing. Never mind those equations now. I'll explain, we'll parse them later on. But let's try to implement this using the Express library. We start with a function called candidate express from, which will take of type list of expert to list of expert. And we can use it like so. Candidate express from applied to a variable of type x of type int, the value 0, 1, and 1 of type int, and the functions plus and times bound to the int argument type. And what this function will do is it will enumerate those terminal values, x, 0, 1, plus, and times. Then it will use the $$ function to build values of size 2, x plus, 0 plus, 1 plus, x times, 1 times, 0 times, etc. And then it will use again the $$ operator to combine values from the previous sizes to make values of size 3, and so on and so forth, up to expressions, up to an arbitrary limit of size 5 symbols, 5 definitions. We take those values that it generates, and we take the cross product of them using this small function here. Never mind the code, but this is just taking a cross product between those values using an equation encoded as an expert. And the result, the important thing is the result, which is this. These are candidate equations. These are our candidate equations in our application. There are equations here that are, of course, are not true. We return false, but we'll filter them out later. Let's put those equations aside for a moment. And let's take a look at this function grounds here, which takes an expression containing variables and returns a list of ground expressions, which are the expression whose where variables have been replaced by ground values, by actual values. Let's see an example to make it clear. So here I have the expression not p of type bool, where p is a variable. And if I apply grounds to not p, I get not false or not true, which p can be assigned to false and to true. Those are the two possible values of Boolean. Here's another example. Grounds apply to plus, apply to x, apply to y. And we get 0 plus 0, 0 plus 1, 1 plus 0, 0 plus minus 1. We get the possible variations. And we can generate those values using a property-based testing library, such as QuickCheck or LinkCheck or Feat or any other that you want to use. I'm using LinkCheck here, but we could have used another. But the point is that using grounds, we can implement a function called isTrue, which takes a Boolean expression encoded as an expert and returns a Boolean whether this expression, telling whether this expression is true for an arbitrary number of tests. And here I'm using 60, but we could have used another value. So if I say is true plus apply to x, apply to y is equal to plus apply to y, apply to x, and that is true. Like if we run tests, there's no way to falsify that. However, if I run is true that plus apply to x, apply to y is the same as plus apply to x, apply to x, and that is not true, that is falsifiable, and it can find it using tests, and it will return false. Well, what can we do with what can we do with that? We can now get back to our goal, the speculate about function, and we can just put the pieces together. We start with the candidate equations from our basic symbols. Then we filter those that are true using our function is true that we just defined. Then we discard later equations that are instances of earlier equations using this function is instance of, which I won't have time to describe here, but is part of the express library. It does matching between expressions. And of course, we could refine this function further with a few more lines, but I won't have time to explain those. And then we can write speculate about, and then pass the symbols encoded as expert. Here's nil, cons, and append. And we get these equations in a list. And x appended to nil is equal to x's. And then a couple of interesting ones are the two later ones here. This is the recursive case in the definition of append. And this is the associativity of append. And it does that in less than 1 second. It's pretty quick to report those equations. And of course, those are conjectures. I mean, these are true, but there could be cases where they are not, because this is based on the results of testing. So you should analyze those and see which are true and which are not manually. Here's another example, equations about 0 plus an abs. And it prints a bunch of equations, such that abs is idempotent, that plus is commutative, and plus is associative. And here's the entire code. This is the full code of the application that does this. And I know the font is small, and the point is not for you to read this, but the point is that using Express, we can build an equational generator in 66 lines. There are, of course, several details and limitations that I omitted here, but those are discussed in the paper. Okay, now let's take a look at another feature of Express, which is support for deeply encoding values as applications of constructors. So the Express library has this Express type class, which has this function here. The important part here is the expert function, which takes a Haskell value A and returns an expert, which encodes this value, deeply encodes these values as applications of constructors. Let's see with examples how that works. So for atomic types, like Booleans, expert is just equal to vol, the vol we defined earlier in the presentation. Same thing for ints, which are also atomic. You can break them down, so expert is equal to vol. However, for types which have constructors, such as pairs, here's the instance for pairs AB, and we can read this as the deep encoding of the pair XY is the pair constructor applied to the deep encoding of X, applied to the deep encoding of Y. And this funky operator here is just a type binding, just to select the pair constructor at the correct type. Here is another example, the instance for lists. So the deep encoding of a list access is just the actual list if it's nil. If it's the empty list, you just encode the new constructor. However, if the list has a head y and a tail y's, the deep encoding is the list constructor applied to the deep encoding of the head of the list applied to the deep encoding of the tail of the list. But what can we do? What can we do with this? And we can do the second example application, which is generalizing counterexamples of property-based testing. Let me do a quick review of property-based testing. So property-based testing is a method of testing that instead of testing a specific input and output cases, you delegate the generation of tests to a library or tool. And here I'm writing that for any access you give me, applying sort of access is the same as sort of access. And for a correct implementation of sort, usually the tools will report test fast because you can falsify it if it's correct and the implementation is correct. However, here's an example where the property is wrong. So for any access, the length of nub of access is the same as length of access. And that is obviously false because nub discards repeated elements. So and usually property-based testing tools report a counterexample such as this. The list 0, 0. This falsifies this property. However, what if we could extend this information that property-based testing tools give and also report a generalization of the counterexample we got? So instead of saying that the property fails just for the list 0, 0, we say that it not only fails for list 0, 0, but also for any list of the form x cons axis, which is any list where the two starting elements are the same. We can do that using Express. We take our counterexample 0, 0 here. We make a deep encoding of it, which will return this funky expert representation here. But never mind that. That just means 0 cons nil encoded as an expert. And we pass that to a candidate generalizations function, which will provide us with candidate generalizations by replacing parts of this with variables. Like so, it will basically list the values in this lattice from most general to least general. And these are made by replacing values with variables in the middle of the expression. The function that does this is short, but there will be no time to detail it in this talk. But the point is that it's quite short and does produce those values here. And with that function, we can write this function counterexample in generalizations that tests the property regularly with a property-based testing tool, then generalizes the counterexample using this pattern here. So it takes all the candidate generalizations and select those that always falsify the property for an arbitrary number of test values, a configured maximum number of test values. And this function, with this part here, will be able to produce this output with x cons axis. Here, the generalization of this property here, so that any counterexample of this form will falsify the property. Of course, that's a conjecture. It may not be true in all cases, but in this case, it is. Here's another example. Applying check to the pair x and y, the properties that says that for any pair x and y, x is different to y, we get the result that 0, 0 is a counterexample, and also that the property fails for any pair of the form x, x, where the value is repeated. Hope that's clear. Here's the entire code of the application that generalizes counterexamples. And the point is that using Express, we can build a counterexample generalizer in just 51 lines. There are, of course, several details and several limitations that I don't have time to mention here, but those are discussed in the paper. Now, let's take a look at our last example application, which is synthesizing functions that match a set of argument result pairs. Here's a partial definition of a square function in Haskell. Square of 1 is 1, square of 2 is 4, square of 3 is 9, square of 4 is 16. And this only works for those 4 argument values. And let's say I collect a bunch of primitives that I think could be useful in an implementation of a fully defined square function. And the values that I choose were 0, 1, plus, and times. And if I write synthesize square with the primitives, this function prints square of x is equal to x times x. Here's another example. Here's a factorial only defined for 4 values, 1, 2, 3, and 4, which are 1, 2, 6, and 24. I use the same primitives as before, but I also add full-dar and num from 2. And I write synthesize factorial with those primitives. And then the tool prints factorial of x is equal to the product of the values 1 through x. Unfortunately, I won't have time to detail this application, but its code is very short. Here's it in its entirety. So using Express, we can build a function synthesizer in 66 lines. This function synthesizer is very limited. There are several limitations, and there are several details I've omitted, and those are discussed in the paper. And hopefully now the title of the talk is clear now. It's clear now what I mean by applications of dynamically typed Haskell expressions, because it's sort of a library that has this bunch of features, but they are useful in different applications, and it's sort of hard to describe without showing the actual examples. This is the best I could come up with applications of dynamically typed Haskell expressions. But now you may ask me, those applications were just a toy and example, short examples. But you may ask me, is Express useful in the implementation of real full-featured libraries? And there's this, yes, I think so. And to prove that, let me tell you a story. Back in 2017, I worked in the creation of 2 libraries with my co-author at the time, my supervisor at the time, Colin Rensman, which were Speculate and Extrapolate. And Speculate is a tool that generates equations based on the results of testing, just like our first example application. And Extrapolate is a tool that generalizes counterexamples, just like our second example application. And back then, Express didn't exist. I hadn't implemented it yet. And since then, I refactored both Speculate and Extrapolate to use Express instead as the engine to manipulate expressions. And the result was that I was able to reduce the number of lines of code by 25% in those 2 tools. So objectively, those real full-featured libraries have less lines of code. And as a more subjective measure, this is more subjective, the code is now more elegant, organized, and easier to maintain. And there was no negative performance impact, and I have benchmarks to prove that, but those are detailed in the paper. And there's more on paper, comparison with other expression encodings, comparison with data dynamic, comparison with template Haskell and why Express is not as similar as it seems, table compare features, etc. And as future work, I'm currently working on improving the synthesizing functional examples and turning it into a full-featured library. That's one of my goals currently. And I think that this maybe could be applied to mutation testing or comparison testing, and maybe something else that I haven't thought of, because I think this is pretty generic, it can be applied to other stuff. Thank you for taking the time to watching my talk, and I'll be happy to answer any questions you may have.
So I'll take the speaker. There are a few questions lined up, and I'm going to take the first question asker to the stage. I'm going to take the question to the stage, and I think I'll invite Armando to ask his own question, which has the additional advantage that people on YouTube also know what is being asked and what is being answered. So Armando, can you ask your question to the speaker?
Yeah, thank you. Really cool talk. So my question, and I guess you maybe approach this in the paper, but what I want to ask is, are you familiar with QuickSpec? It's a tool that also tries to generate equational laws for free. You give it a bunch of functions, and it just tries to generate equational laws and that you can use in property-based testing. And I asked you if you have used this to generate or find equational laws for free in testing, but I guess you did, just said that in your presentation. But do you compare your approach with QuickSpecs? Could you talk about that?
So let me try to summarize that. Getting some audio feedback. Yes, I am aware of QuickSpec. and I have used it before in the past. And actually, QuickSpec was one of the tools that inspired me to create Speculate, which is the other tool I mentioned. And I have there is a paper about Speculate, which is this other tool I made, which does compare its results with QuickSpec. What are the performance results between them? But this actual the simple example application, the 50 lines one that I showed you in the talk, I haven't done any deep performance comparison with QuickSpec because it will obviously lose. It's like just a small. It's just like a case study, a proof of concept to show that Express can be used to write shortly and work as an engine to manipulate expressions. I hope that answers this question.
Yeah, definitely. Thank you, Rudy, once again. And thank you, Julian, for welcoming me on stage.
Okay, I'll kindly remove you from the stage. And Mark, your question is answered. So there's another question by Yuji Yamamoto. I'm first going to show on stage, and then I'm going to invite Yui. Can you ask a question, please?
Okay. Why does the var function receive and define it as a type proxy instead of a proxy or using type applications?
The answer is pretty short. It's just because of backwards compatibility. So it's more backwards compatible to just use the undefined value because proxy was defined at a given JC version. I wanted to support earlier versions, but we could have used the proxy there. There's no reason why a proxy couldn't have been used.
Okay, thank you.
You're welcome. Yeah, thanks for your question.
Thank you. Can I kindly remove Yuji from the stage, and Marcus has answered. Are there any other questions at this time? See in the chat if there's anything. I don't see anything there. So if you have any questions, you can still pose them. So no one has a question. I'm going to show it on stage and invite him to the stage to pose his question. So don't go ahead.
Hello, thanks for the amazing talk. Just curious, the synthesis part works by enumerating all the options, or does something else?
It's this simple version I presented in the talk. It works just by enumerating. It's brute force enumeration, and it has no pruning at all, and it doesn't scale well. Like if you give it 4 or 6 symbols, 8 symbols, it can generate small functions. But if you give it 12 or 20 symbols, it will blow up and not produce an output. It will be killed by the OOM killer or even take too long to run. So it's just brute force enumeration, and that's it. But I'm working currently on another tool that tries to prune and does something more fancy. But this one in the talk is just brute force enumeration.
Thank you.
Thanks for the question.
Okay, and kindly remove Silk known from the stage, and Marcus' question is answered. So I think we can thank you again for answering the questions and giving your presentation.
Thanks.
And then I'll uninvite you from the stage kindly to invite the next speaker for today. So the next speaker for today is Finn Teagan. Finn, welcome.
Hello.
I can hear you, I can see you, so you
Perfect.
can share your screen.
It's in progress. So can you see my screen?
Yes, I can see your slides.
Perfect. Okay. Should I start?
So the next I'll introduce you. So the next presentation is by Finn Teagan, whose work is on Haskell inverted, automatic function inversion in Haskell, co-authored with Kai Oliver Prott and Niels Bokenberg. go ahead, Finn.
Yeah, thank you. Welcome to our talk about Haskell inverted. I am Finn, like introduced, and I'm happy to present the work done by me and my colleagues who are also here today. And as you can see, some advertising, there's an artifact available, which I'm going to refer in just a moment. So there is something to try out if you want to. So what is this talk about? Let us start by decomposing the subtitle, Automatic Function Inversion in Haskell. Well, let's start with function inversion. What is function inversion about? Let's say we have a function f that yields the output y for some input x. Then the inverse should yield set x for y as an input. And it's somewhat informal, but inverses in general have many applications. Some of them I list here. For example, parser printer can be seen as inverses. There has been work done before, compressor decompressor as well, and serializer deserializers also. In general, any form of encoder and decoder can be seen as a pair of function and inverse function, or vice versa. But there are also other applications. For example, there is work about the synthesis of parallel divide and conquer algorithms. If you have a language which has inverses available, you can indeed synthesize algorithms that can be computed in parallel. And one of our contributions is the implementation of so-called functional patterns, which will I come to in a moment. So what about the part in Haskell? Some of you may notice that the informal introduction to function inversion has a little flaw. It's only applicable for injective functions. But if we consider a language like Haskell, and we do not want to restrict ourselves to injective functions, well, we have to face the fact in Haskell that many functions are not injective. And one example, our favorite function here is the append function, which takes two lists and yields the concatenated list. And yeah, if we evaluate the expression empty list appended to the singleton list with 1, we get the list with 1, and we can swap the arguments and get the same result. So in conclusion, there is no unique inverse because there are, like here, two different values that lead to the same result, and that means that the inverse is not unique, and an inverse function in the mathematical sense does not exist. However, we can work around this problem by allowing multiple results for the inverse function, and that leads to the kind of inverse functions we are going to look at. And this is something like this, where we take the result type of a function as the input type for the inverse function and yield a list in this case, so multiple values of the arguments as a tuple, in this case a pair. That's the kind of inverse function we take a look at here, and that is the kind of inverse function we want to synthesize in the end. So last part in the subtitle was automatic function inversion in Haskell. That's quickly explained. That's the artifact I mentioned before. There's a Glasgow Haskell, so GHC plugin available as an artifact, and also at GitHub that does all the things that I will try to describe here in the talk, and that are also explained in the paper, of course, in more detail. All the things there explained will be done automatically by the plugin. So if you want to use inverses in Haskell, you do not have to do much. Just load the plugin and add a pragma at the beginning of your module, and you're ready to go. Okay, so what are the contributions of our work? Basically, we designed a framework for function inversion that enables the inverse computation of Haskell functions in Haskell itself. Support includes inverses and also partial inverses, which I won't cover in this talk. But you can basically imagine that you fix some of the arguments of the function to instead of returning all function arguments of the original function as the result of an inverse function. Most notably, our function inversion framework supports or limitedly supports higher order functions and also primitive types. And in conclusion, we really support the full Haskell 2010 standard. So everything you can imagine to write in Haskell can actually be inverted with our plugin. So it's not just restricted to some sort of model language or some subset of Haskell. You can invert any function you can write in standard Haskell. Moreover, other contributions are the implementation of functional patterns. That's a pattern matching extension that is known from functional logic programming, for example, in the language Curry. Basically, you can think of it as the extension of pattern matching by allowing function symbols in patterns and therefore allowing arbitrarily deep pattern matching in data structures. If there's time, I can show an example later on. But we have found a way to implement said functional patterns using inverse functions and also make this pattern matching extension available in Haskell for the first time. And like I said before, there is a GHC plugin to do all the stuff automatically. So how is inverse computation achieved in our framework? The basic idea comes from logic programming. If you consider Prolog, for example, where we also have an append predicate available, we can call the append predicate with 3 variables as an argument, and the third argument of the predicate here is the result of the function. And if we call the predicate this way, we get the bindings for the 3 variable arguments, and in this case, the list of 1 can be obtained in 2 ways, like seen before, and Prolog does all the computation for us. And also inspired, we of course do not the same as Prolog, but we want to do something similar. So we want to extend Haskell in a way to enable logic computations. So we result in a functional logic extension of Haskell, and we require 3 variables and non-determinism. So that's the overall idea. How do we achieve the functional logic extension of Haskell? Basically, it all starts with a monadic lifting. And let us consider the following minimal example program where we have defined the list data type and the append function. And the first step in our monadic lifting is to do a pattern match compilation. It's well known, at least I hope. And all that we do here is to make the pattern matching, which we have here in the pattern positions of the function, explicit by moving it to the right side of the function and expresses as case expressions. And this is some kind of preliminary step for the actual monadic transformation that then takes place, which transforms the data type by adding a monadic type parameter to every component of a data type, and especially the pattern matching, which we have made explicit in this version, becomes a call to the bind operation of the monad we use for the lifting, which is M in this case. The rest remains mostly unchanged. This is some way simplified, because in the real monadic lifting we use for our inversion framework, we also have to lift the function arrow, which makes the code much more complex and less good looking. So I omitted it in this version here, but the idea remains the same. So pattern matching of the original function results in bind operations in the monadically lifted function. Keep that in mind. If we have a monadic lifting, question is what monad to use for the monadic lifting, and this is sorry, I forgot to mention that of course in the final program we achieve after this transformation, we keep both the original definition and the lifted definition, because of course the user wants to keep a way to use the original definitions in his program, so we don't want to strip it of the original function he intended to program. What's the actual monad we use for the lifting? It's quite complex, so I won't show the whole monad here, but I will try to give an idea. Like I said before, we need support for non-determinism and free variables, and we further need support for both the implicit instantiation of free variables during the execution of the bind operation. We will see in a moment why. And at the same time, we require the ability to be able to do pattern matching on free variables, because we want to efficiently compute bindings for those free variables. And the solution we came up with is the use of two monads, which are nested or built on top of each other. And the first and inner monad is a simple non-determinism monad, which has the support for an explicit representation of free variables, and support for Haskell's call by need evaluation by representing the state of the computation in a heap. So the heap contains the binding of the free variables. And on top of that, we build the function logic monad, which is the one we actually use for the lifting, which adds the support for the implicit instantiation of free variables. How is inverse computation now finally achieved? It's quite, the idea is quite simple. The first part is that we compute the lifted function with free variable as arguments, and in the process, the pattern matching of the original function will result in the instantiation of the free variables we provided as arguments to the lifted function. And on the outside, we match the result of the lifted function, which we called with the free variables, with the input of the inverse function. So you can say that the matching process here in the second step drives forward the inverse computation and also maintains the laziness of the original Haskell function, in the sense that only the parts that are demanded are actually being evaluated by our inverse computation. So that is different from the naive approach, where you generate all possible input values and test if the result value matches with the input of the inverse function. So we try to be as efficient as possible with this approach. And in the end, the bindings of the free variables on the heap represent the result of the inverse function. Of course, that's only the overall picture. There is a detailed explanation in the paper. But to give you an idea how this works, let us take a look at an example. If we consider the initial example where we want to compute the inverse of append with a singleton list containing the 1, which would be this expression, we can now translate it into something like this, where we have some kind of match function. And well, this argument to the inverse function gets translated in the lifted representation. There's the boilerplate code that does all this stuff that I show here. And of course, the plugin does all the generation of the boilerplate code for you. So again, no work for the user of inverse function here. So the argument of the inverse function gets translated into the lifted representation and passed to the match function as an argument. And like said before, the lifted function of the one we want to invert is called with free variables as arguments. For the purpose of this presentation, free variables are represented as these small boxes. In reality, of course, they have a representation in the function logic monad, but since I haven't shown any definitions of the function logic monad, I figured that it would be easier to just use these small boxes. So what does happen now? The evaluation of match triggers the evaluation of this monadic function call in the second position here. And if we remember that the append function does pattern matching on the first argument, and this first argument is a free variable, and we also recall that pattern matching in the original function leads to the instantiation of free variables, we can conclude that this free variable titled A gets instantiated to the empty list and also non-deterministically to a non-empty list, which again has free variables as arguments. So we instantiate it lazily. And some of you may recognize this is very, very similar to the process of narrowing from logic or function logic programming. And indeed, it is some form of narrowing. So let us follow the first computation branch here. If we instantiate the first parameter with the empty list, the result of the append call is just the second argument of the append call. So this reduces to a match call with the same list and the result of this function call if we instantiate A with the empty list. So after one computation step, we have to match the same list with the free variable B, and the matching is done very simply here. We can just enter the binding for the variable B and enter it on the heap. And afterwards, the matching was successful. So we now have one solution for our inverse computation. We remember that the inverse computation's result is represented by the bindings of the free variables on the heap, and A is bound to the empty list. Of course, we have to convert it back to the Haskell representation instead of our lifted representation. Also something that the plugin does for you. And B is bound to the singleton list. So we have the one solution where the first list is the empty one and the second the non-empty one. So let us follow the second computation branch here. Here, the result of the append function in the second case is the non-empty list, which has C as a first element and the append call with D and B as the tail. And we still want to match the initial list with this expression. And now the match call triggers the evaluation. First, we can actually match something here. We can match the 1 with the C, because the 1 is the first element here. So we can enter C maps to 1 in the heap, and then can reduce the matching to the call that we have to match the empty rest list of this singleton list with the rest list of this second argument here, which is D appended to B. And yeah, now that's nearly the same as the first call we had here. Again, the first argument is free variable, so we can non-deterministically instantiate it with the empty list and the non-empty list. In case of the empty list, we can return B as a result, which has to be matched with the empty list, and that results in the matching where we can bind the variable B to the empty list and have a successful solution here, successful computation branch. And again, the solution is represented by the bindings on the heap. A is bound to C const D, and C is 1, D is the empty list. So this is the expected second solution, where the first argument is the singleton list and the second argument is the empty list. And For the third computation branch here, we get this match call where we can quickly see that we have a mismatch because we want to match the empty list with a non-empty list. So this computation branch fails, and we have our two solutions in the end. That's basically the idea of our function inversion. Although presented quite simply, it requires, like I said, a lot of boilerplate code, which is automatically generated by our plugin. So what do we find in the paper? Of course, there's the function inversion framework explained in detail, the design of our monad, the type classes and type families involved in our framework are explained and defined there, and also some design choices discussed. There are extensions to the framework to cover higher order functions and primitive types. The latter are efficiently implemented using constraint solving. So we use an external solver to efficiently generate constraints and solve them during the computation with free variables if primitive types are involved. We provide an implementation of functional patterns, which also enable nonlinear pattern matching in an elegant way in Haskell. And last but not least, we also discuss partial inverses, which usually are used to make non-injective functions injective, but in our setting have some nice use cases where there are also non-injective partial inverses, which can be very useful in practice. So have a look in our paper. And of course, we also discover some related work, as always. So we compare ourselves to other approaches. For example, there are not many approaches that cover higher order functions or primitive types at all. Yeah, that would be all from my side. Thank you for your attention, and I'm happy to answer any questions you have.
Okay, thank you. There's a question by Jeremy, so I'm going to show it on the stage and invite Jeremy to the stage to pose his own question.
Hello.
Hi.
Hello. This was fun. But so my question is not really about your main point. So if I put the function inversion aside, you have this monad FL, which, if I understand right, gives you logic variables as in addition to the non-determinism that we sometimes simple-mindedly think of the essence of doing logic programming in Haskell. And I wonder how useful that FL monad is for doing the other fancy logic programming stuff.
Right now, it's solely used for the function inversion purpose, but you could easily define your own DSL using that monad to support logic programming in Haskell. And although not tested, I am pretty confident that the Queen's program should be implemented or can be implemented using the FL monad.
So, of course, the Queen's program can be implemented without the FL monad. All you need is lists.
Yeah, that's true, but efficiently implemented.
Right. So Fruro's program is, he says, an order of magnitude faster than the one from O'Keefe's prologue book, because it uses logic variables to do comparison tests. I think that's the essence of what's going on.
Yeah, I will give it a try. I can come back to you, but
yeah.
It should work.
Yeah. Okay. Well, I look for, I mean, if you don't, I will. So I'm quite interested in this. So great. Thank you.
Welcome.
All right. I'm kindly removing you from the stage, Jeremy. Marcus has answered, and there's a new question by Rudy Matilla. I'm going to show on stage, and I'm going to invite him over.
Hi. Hi, how are you doing? Yeah, so this is more of a comment than a question, and just something to bring up discussion, because I mean it's a plugin for GHC, which kind of limits how easy you could use it, because I mean, you have to build GHC with a plugin and a specific version. But I was wondering if you could do this using template Haskell. Say, for example, write the function inside a th quote, then apply a similar technique to produce both the original quoted code and an inverted version, like normal and invert, and then you pass the quote and you get both versions. And of course, use the technique that you described. Have that crossed your mind? Have you thought about that?
It actually did. And it would work in some sense, but there are some limitations to the template Haskell implementation. For example, you can't add exports, as far as I know. You can't add exports to your module. So if you generate an inverse function and you have an export list, it's actually not available in any other module than a module you use template Haskell in. So the decision to use a plugin was mostly because of practical reasons, and indeed we use some template Haskell within the plugin to exactly what you said.
Cool. Thanks for the answer.
Okay. I'm kindly removing you again from the stage. And mark this as answered. So there's a new question by Jean-Philippe that I'm going to show on the stage. So questions are coming in quickly now. I'm going to invite Jean-Philippe.
Hello.
Yes, we can hear you.
Yeah, so there was another implementation, perhaps following up on Jeremy's remark, already 2001 of logic variables, and I checked in the paper quickly, and it seems you say it's too strict. Can you elaborate why?
Well, basically, we want to reuse the laziness of the function we want to invert, and this requires the deep embedding in the data components. And as far as I'm aware of, this is not the case with the approach you mentioned. So we want to support non-strict non-determinism and non-strict logical variables in the components of data types, and that's not the case with that approach as far as I remember it now.
Okay.
All right. Does that satisfy you, Jean-Philippe?
Well, I think it's not saying anything more than in the paper, but what I imagine is that when you evaluate, if you use, I think this 2001 approach is based on a state monad, and that could mean that it becomes too strict. But I think you also have a state monad in the background, don't you?
We use state and a state transformer in the background. That's right. But I will gladly come back to you. But in the short version, I would imagine that the embedding, as they use the library to embed Prolog in Haskell, and they also match the semantics of Prolog as far as I know. And Prolog is definitely more strict than the inverse computation we want to have. It's like comparing Prolog to Curry, if you know it, which is a lazy functional logic language. And although not covered by the append example, because that's basically like an SLD tree, what I showed you, but there are cases where the demand-driven approach of our inversion is definitely more efficient than the generate approach that Prolog does. And that's the same reason why the embedding of Prolog of the work you mentioned is too strict for our purposes, because it builds the Prolog semantics or imitates the Prolog semantics.
Okay, thank you.
Okay. Then I'll remove you from the stage and mark your question as answered. So there's another question, this time from Gergo Erdi. I'm going to show it on stage and then read it out because he doesn't have a mic. So he says, is the transformation done on the service language or on core?
It's not on core. It's done in this some kind of on the surface language. So we do a Haskell transformation, but we check that the core code is correct afterwards to ensure that our transformation is right. But the transformation is done on a surface language level.
Okay, thanks. I'm gonna mark that as answered, and then there's I think a final question for this session by Katsutaka, who I'm going to invite to the stage.
Okay, so
Katsutaka.
what? Hi.
Hello.
So can you hear me? Okay, why do you use the FM monad instead of using Fisher and others monad for writing non-deterministic computation in Haskell? So I think that it is quite powerful to emulate many computation carry, in my understanding.
Yeah, the main difference is that the library by Fisher and L does not have an explicit representation of free variables, which is crucial for the matching algorithm we use. However, we thought of combining both approaches because the library by Fisher et al. Incorporates true call by need, so it incorporates true sharing, and indeed we already started on working combining both approaches, and the main reason we haven't done this in the first place is because it complicates much of the code. So it requires, for example, use of more language extensions. The boilerplate code gets even more complex, but in theory and also in practice, as far as we know for now, because it's already working, we could do so to gain an even more elaborate combination of the monad defined by Fisher and the one we use. But we require the explicit representation of free variables, which is not present in the approach by Fisher et al.
So I think in the Fisher's library we can emulate the free logic variable by using the non-deterministic generation and the sharing operator in the library. So
semantically, that's equivalent. That's right. But the problem with that is that you have to run the generator in order to match afterwards. And if you have an explicit representation of free variables, you can actually insert the binding on the heap, which is far more efficient than generating all possible constructors and then fail for every one except for one.
Thank you.
Okay. Thank you. I'll kindly remove you from the stage, Katsutaka, and mark your question as answered. So yeah, this brings us to the end of the first session. Thank you again, Finn.
Thank you
for giving the presentation and answering our questions. It is now a break time until 3 o'clock. So I'll be pressing the take a break. It seems that everybody will be kicked out of the session then, but at 3 o'clock or slightly before 3 o'clock, we will resume with the invited talk by Mathieu Buspluk from Tweak about linear Haskell and its practical applications. See you then.
Hey, Urian, I can't hear you.
Hello.
Hi, Richard. I can hear Richard, but I can't hear Urian.
Yeah, neither can I. Even though Urian, you're not muted, but we're not hearing you. So it's something further. It's closer to your mouth than air meat.
You're still on.
We can't see you, Mathieu. I don't know if that's intentional.
Oh, there we go.
There we go. That's better. Yeah. No, we still can't hear you, Urian. Nothing. But Matthew, you may want to move your mic up or down. We're getting a bunch of air sounds.
Air sounds?
Breathing.
This is better?
Yeah. Yeah, that made a big difference, actually.
Okay.
Yeah.
Still good. Still good sound quality.
Yeah. We can hear your voice just fine.
Okay. I'm not in my usual location today. I'm in Cyprus, and so I hope the quality of the internet connection is good enough for the video and the sound.
Yes. It definitely appears so from here. I think, just so we know, I think we're actually in front of everyone. I think 33 people are watching us now. Okay. Yes. But we still can't hear you, Yurian. Maybe restart Chrome? I don't know. Nope. Well, in one more minute, I will sort of kick off the session formally in the absence of Yurian's microphone. Okay, I think we're going to get going. We can try to debug this more later, but this is why we have backup hosts. So hi everyone. Welcome to the keynote session of Haskell Symposium today. It is a great delight to introduce Mathieu Bospflug. I hope I pronounced that correctly. Maybe.
Pretty much close enough.
Okay, close enough.
Bospflug.
And who is the CEO of Tweag, where, declaration of conflict of interest, where I also work. But he's here today to talk about functional programming and linear types and sort of Tweag's journey through these different ideas. So thanks very much, Mathieu, for coming to Haskell Symposium, and take it away.
Well, thank you very much. It's a pleasure to be here. And well, let's see if this works. So when I was first taught Haskell, that was 15 years ago. I was told that the int-integer distinction was a mistake, that this was a design flaw in Haskell 98, that there should be only one integer type. And it should be the ideal integer type, matching the intuition that a mathematician might have of what the set of all integers should be. And this is a fine view of functional programming. The way I see it, it's about abstracting away the inessential details that are mere artifacts of present-day computing devices. You could say it's about escaping the Turing carpet and reasoning in a world of infinites. And it's pretty convenient. Infinite integers, infinite memory, fast enough CPUs, predictable performance of integer arithmetic doesn't matter too much, and so on and so forth. So This talk, though, is about how I became much more interested in another view, the notion that functional programming is a darn good way to program actual computers by being very explicit and intentional to the compiler about what we want as the programmer. One important distinction between the world of ideal integers and the real world is that the real world is finite. Running a computation requires resources like memory, like file descriptors, like sockets, like database handles, like security tokens, like money. And the finiteness of these resources means that we need some level of control on how we use them. It means that it can be a good idea to ask the programmer to be much more precise about their intentions. If they know they are working with small integers, they can tell the compiler that they know. If they're allocating lots of small chunks of memory, they can tell the compiler exactly what should be freed when to avoid running out of memory. If they're implementing complex protocols, they want to tell the compiler that their code is intended to have good resource hygiene, and therefore that the compiler should yell very loudly when they're modeling, for example, pizza delivery as pizza duplication. So to borrow from Baudelaire, who's a French poet from the 19th century, there are abstractions or ideals, and in present, but programming also means getting down and dirty with the machine. So there's a component of spleen, as he called it. And I'm interested in the type of programming where you really do want to be explicit about all kinds of computer-specific details. I'm interested in the gritty details of CPUs, network cards, and memory to make the most of them. I guess you could say I'm interested in the spleen of reality, and the reality where everything is finite and integers come in different sizes. I think functional programming is a great way to talk about reality, actually, about the spleen of it even. And at the same time, I'm also interested in the type of programming where we can build new abstractions that are not leaky abstractions. For example, when I'm implementing a pizza delivery protocol that I mentioned earlier, pizzas are resources. There's a finite number of them. And when one person has one, then the other person doesn't. Duplicating pizzas doesn't make any sense. So if I'm implementing a pizza delivery protocol, then it would be really great if I could model pizzas in my code in such a way that they cannot be duplicated. So I'm interested in getting closer to the ideal of a pizza in my code, or rather to build abstractions that that model relevant aspects of this ideal depending on my problem domain. And so over the past 5 years, there's a number of people that worked on a project to bring linear types specifically to Haskell to address these things. And so I worked with a number of colleagues at Twig and with academics like Jean-Philippe Bernardi, who's going to talk about linear types as well tomorrow. And as I said, to work on both aspects to enable a more explicit style of programming in Haskell that's more aware of the underlying machine and operating system, i.e. the spleen of programming, and to enable programming to more accurately or more completely model certain ideals, like the idea of a pizza or the idea of a file alongside the idea of an integer. The way we did this is that we went about retrofitting linear types to Haskell, and that posed a number of challenges in of itself. And I'm not going to get really into that in this talk. You know, I'm kind of the token industrialist here, and so I'll talk about the motivations from the perspective of the industrial use cases that we had for all this. So here's a picture I lifted from a presentation made by Dick Seitz, who's an engineer at Google in 2015. And so each rectangular box here represents a rack, each containing about 60 servers. It represents what, at the time, happened it's representing what happens whenever a user makes a single search query. And the query is received by one server, and that begets requests to a number of other servers. And those requests are in green, and those in turn lead to other queries, which are in blue. And in fact, Dick Seitz in his presentation says there was even a third generation of requests, but if you represented all of them on this graph as well, then it would be nearly impossible to make out any single arc. At the lowest level, the requests take a few milliseconds to yield a response, which in turn make their way back up the request graph. And the total wall clock time spent for a search query, start to finish, is about 200 milliseconds. So the overall time budget is very low. And in fact, this time budget is low for a reason. Faster search directly translates into users making search queries more frequently, and therefore into more ads being served, and therefore more revenue for Google. The effective latency on user traffic is very well studied and is directly relevant to a lot of web services. You know, this is not just about search engines. So 15 years ago, Amazon found that for every extra 100 milliseconds of latency experienced by users, they lose just over 1% of revenue. And at around the same time, Google said in a presentation, I think it was the same year, 2006 or so, that if they add 500 milliseconds, they lose 20% of their users. And then more recently, in 2017, just to cite another study, a little bit more recent, Akamai says that for every 100 millisecond delay in website load time, for an e-commerce website, the conversion rates typically drop by 7%. So for a lot of people in the industry, lower latencies means more dollars. And that's a very important constraint when designing systems. It's a constraint that means you can't just keep average latencies low, but indeed the latencies of all requests, or at least say 99% of them or 99.9% of them, have to be pretty low. Because in order to achieve these very low latencies for all users, as we saw earlier, for a single query, you're typically going to have a bunch of sub-requests that are going to be sent to a number of systems and a number of machines. And so it's really important that what's going on under the hood, the request for these requests has a consistent latency. Here's another graph of the same search query that we saw earlier. And it's a timeline showing a request coming in, which in turn gives rise to 93 parallel requests. And two of these 93 requests are taking a particularly long time. And that penalizes the performance of the system as a whole, because we can't construct a response to the initial request until we have all responses for all the 93 requests. And it doesn't matter that most requests are pretty fast. If some are unpredictably slow for reasons, then that translates into slower service to the user and a degraded experience. So the problem here is that time is a resource, and we are not controlling our use of that resource very well, or we need to control it to avoid too much variance in the latencies, to avoid the long tail of latencies. Here's a graph of server response times over time, unrelated to the search query graph that I just showed. But the graph shows the response times for a number of API endpoints. And the responses are a bit all over the show, but what is particularly odd is the latency spikes in update credentials. I can't tell you the cause for these spikes, nor does it matter. It could be anything at all, like data compaction, like leaking file handles, and running out of memory, and forcing a computer restart, or quite simply a garbage collector making a sweep. And that's the point. Any of these possible causes are cases where we are not controlling very carefully when some resource reclamation occurs. And instead of managing resources carefully on the fly, we are knowingly or unknowingly letting resources letting resource management debt accrue over time, and then some automated process pays off that debt for us, and sometimes it can do it at the most awkward times. Okay, so how do we get a handle on this? The first problem that we have is that we want to avoid holding system resources like file handles, like sockets, database handles, etc., for longer than necessary. Even if we do release some or all of these resources back to the operating system eventually, releasing them too late runs the risk of having us blocked or killed by the operating system before because we exceeded some quota. For example, on Linux these days, the default is that processes are allowed to open 1,024 file descriptors at most, and that includes sockets. So the second problem we have is that memory management can be expensive. It takes time. It takes time to find a location in memory, to allocate objects, and it takes time to automatically find what objects can be freed, the way garbage collectors do. And again, we don't care about the amortized cost of garbage collection over the entire runtime of the application. That might be as low as 5–10% overhead if you can find the right GC parameters. The problem is that GC sweeps are not always instantaneous, and when they're not, you'll see spikes in latency. And latency spikes in one place can severely degrade the performance of the system overall. So let's focus on the first problem, and then we'll talk a little bit about how that what the picture looks like in the for the second problem. A lot of what we do is implement network services interacting either with other services or with a user's browser. And these are long-running processes. So it's important to ensure that they don't leak memory and that they don't leak anything that was allocated to them by the operating system, like file handles to read or write data, like sockets to create connections, and connections to send messages to other services. And so actually we want two things. We want any resource claimed from the operating system must be released back to the operating system in a timely manner. And any resource released back to the operating system should never be used again. A common problem is that we get a hold of a new connection, and so let's say every time a client connects to a service, and we expect that to happen thousands or millions of times without the service crashing. But if we forget to close the connection, then we're leaking the underlying file descriptor provided by the operating system. And the operating system will only give us so many file descriptors. We said that typically they'll only give us 1,024 at a time, according to the default parameters on Linux. And so we better use file descriptors parsimoniously, because otherwise the operating system might think we're misbehaving and just refuse to give us more file descriptors. So here's a screenshot of a patch that was done a few years ago on a system that's called Ganeti, and it's a virtual machine cluster management tool that was originally developed by Google. And it consists of a number of services, including a configuration service that clients connect to. And here's a bug fix. This is the client. This is a bug fix to the client code, and that was mentioned in the release notes. They were opening a socket to send UDP messages somewhere, and they were never closing the socket. So anytime they queried a new server, a new connection would be created and never closed. So the fix was to surround the network interaction code by a so-called bracket. Brackets are a common pattern in Haskell. The bracket function ensures that initialization and cleanup of a resource happens before and after executing the provided action, no matter what. And even if the thread is interrupted by a synchronous or asynchronous exception, and yet, clearly there was no static check forcing us to use the bracket here, and indeed, the original code didn't use it. In fact, this bug that's being fixed by the patch that you see here survived 2 years before being fixed. So arguably, this is an API design issue. And one way to avoid bugs like these is to bake in the bracket pattern into the API. So to say what I just said slightly differently, what we could do is to make any function that allocates a socket into a function that also frees the socket. And so to the left here, you have the original socket API. So you have the socket function to create a socket action to create a socket. You have send to. Of course, you can also receive data from a socket, but we'll ignore that for the purposes of this conversation. And then, crucially, sockets are system resources that need to be disposed of at some point. And so you have a close action. And so what we can do is introduce with socket. And the idea is that with socket kind of replaces both the socket function at the top on the left and the close function. And you give it an address to bind, and then you give it a function that says, you're given a socket, here's what we're going to do with that socket. And then once that function is done running, then with socket will just close the socket. And so with that, there's no way that you're going to forget to close the socket the way we saw was the case for 2 years in this system that was in production called Ganeti. And so if the problem here is that you might have to open a number of sockets, and that might mean, so if you're acquiring a number of resources, you're going to need to nest these calls to with socket, and that might make your code pretty unwieldy. So what you can do instead is to introduce a socket monad and make it such that the socket creation function can only be called when in the monad, and when the monad is run, then all sockets that are created get destroyed in one go. In fact, this is exactly what the popular resource T monad transformer is about. The resource T monad transformer can also be nested to create an arbitrary number of scopes. And if you want some resources to be, released sooner.
Excuse me, Mathieu. Sorry to interrupt. I think there's a slight presentation problem where the bottom.
There you go. Okay. Well, the crucial function was run resource T right at the bottom, and that was being obscured. Sorry about that. Much clearer now? You don't see the controls anymore? Okay.
All good. Thank you.
Excellent. All right. So the resource T mono transformer can also be nested to create arbitrary number spokes, so this is this is a fine solution. It's what people do at this point. But note that this is not a complete solution to the problem. Not only do we want all sockets that get created to eventually be destroyed and be destroyed exactly once, but we also want to make sure that sockets do not get used after they get destroyed. And so, for example, we may want to make sure that we are not calling send-to on a socket that has already been closed, because if we do that, that will raise an exception. And if this exception isn't handled properly, then the whole program crashes. So in other words, the bracket pattern or the resource T monads are only a partial solution to the resource safety. They provide a guarantee that resources like sockets will eventually be destroyed, but not that they won't be used after being destroyed, or indeed destroyed multiple times. So this is an example of code using resource T. I wrote the function socket so that once I get to the end of the scope introduced by the run resource T function, the socket will be closed. But there's nothing stopping me from writing send-to right after that block of code. This still type checks, even though the socket has been closed at this point. The resource has been destroyed. So how do we achieve full resource safety in Haskell? The key trick that we'll see in a moment is to track in the type system how many times a variable is used in any given lexical scope. And the way to do that is with the new linear types extension that my colleagues at Twig developed over a period of 4 years now, and that shipped as part of GHC 9.0 earlier this year. So here's the current API for sockets. And the first change that I'm going to make is treat sockets as stateful objects and actions on sockets as things that can take a socket in one state and return a new socket in a new state. So here, send-to now returns a socket where it used to return nothing. And if you, And so now the problem with this change is that there's nothing stopping us from reusing old sockets. So the idea of this API is that when you're performing multiple send-tos one after the other, I write code like this. But there's nothing preventing me from writing this instead, where instead of properly threading the different socket variables, where first use S0, then S1, then S2, and each variable gets used exactly once. Here I end up using S0 twice. So the second change that I'm going to make is to annotate some arrows, specially, to indicate that the actions are linear in some of their arguments. And I then need annotations to do the opposite. And in the case of implementing receive, but we're not going to look at that right now. But the crucial thing that we need right now is that we need the API to enforce that we're using the socket variables in a do block exactly once each of them. So this is still not enough because we designed the linear types language extension such that when in the legacy IO monad, linearity annotations can be pretty much ignored. And so we introduced a new monad that we defined in a package on a package called linear base, and in it you'll find a new monad called Rio. And we made it so that, so for the purposes of this talk, you can think of Rio as just the IO monad, but a resource-aware IO monad where the linearity annotations crucially do matter. And so with these three changes in place, I now have an API that enforces resource safety. There's no way for me to forget to close a socket after I opened it, because in the context of the real monad, if an action returns to me a socket and I don't use it exactly once, then that's a type error. So here, S2 is never used, and that's a type error. There's no way for me to reuse a socket by mistake, because doing so would mean using a variable twice, hence not exactly once, and that would be a type error. And likewise, there's no way for me to use a socket after it's closed, because again, this means using a socket twice, which would be an error, since the types are telling me that specifically in the context of the Rio monad and other linear contexts, all sockets must be used exactly once. And even better, I'm not forced into a nested discipline of resource management. This API does not force me to clean up sockets in any specific order. I can open a socket, then another, and close the first one before the second, or the second before the first. It doesn't matter, so long as they all do get closed eventually. And in our experience, this kind of freedom is I mean, it's not actually all that crucial for network code, but it's very important when the resources we're handling are not sockets, but objects in a secondary foreign heap. So let's talk about that next. But before we do, I want you to keep in mind the words of John Hughes in his seminal Why Functional Programming Matters paper, which is now 30 years old. John Hughes extols the virtues of modularity. He says, when writing a modular program to solve a problem, one first divides the problem into subproblems, then solves the subproblems, and finally combines the solution. The ways in which one can divide up the original problem depend directly on the ways in which one can glue solutions together. And then he says that this is the key to functional programming's power. It allows improved modularization. It is also the goal for which functional programming programmers must strive: smaller and simpler and more general modules. So we'll come back to that in just a moment. All right, so the other use case that I want to talk about is high performance language interop, because this is where you're going to see that nesting, using, for example, the with socket pattern can really be a cost when I'm dealing with other types of resources than just sockets. So something my colleagues at Twig and I have been focusing on since the very early days is high performance language interop. And we did this because we believe that re-implementing the entire world in Haskell could be a fun hobby, but it's a futile endeavor. We're not particularly interested in making our solutions all Haskell, all the way down. And in fact, for all our love of Haskell, we love other languages too. And we're not afraid to reach for Python libraries for numerical analysis, R libraries, or for R libraries for statistics and visualization, or even to reuse some of the many high-quality distributed computing frameworks from the JVM. And so I think that increasingly will be no such thing as big code bases in a single programming language, and increasingly we're going to want to reach out to existing high-quality components in other languages. And in fact, everyone has been doing this for at least 20 years. And what with Haskell 98 supporting, specifying an FFI, and I mean, in practice, the amount of C code leveraged by production Haskell code today is rather large. I mean, typically we're using OpenSSL, we're using zlib libraries to talk to databases like PostgreSQL and more. So in 2015, we released a thing called Haskell R, which allows us to interact with the R interpreter. In 2016, we did the same thing for interacting with the JVM, and a lot of other people have been implementing similar bridges to Rust, to .NET, and a lot more. And the problem with doing all this is that a lot of these languages are garbage collected languages. And that's a pretty dangerous state of affairs, because you then end up with having two heaps. And so in the case of Java, garbage collection is done by the JVMs, GC. And then Haskell itself is a garbage collected language, of course. And so normally the JVM's garbage collector is the only garbage collector in the entire process and has a global view of the heap. But now we have two heaps, and so neither the JVM garbage collector nor the Haskell garbage collector have a global view of the heap. And this is pretty dangerous because we can't let either garbage collector cut the grass under the feet of the other. Take, for example, this simple scenario. We have an object in Haskell pointing to another in Haskell in the Haskell heap, as well as an object in the Java heap, two objects in the Java heap. And the JVM garbage collector could believe that, for example, one of these objects is no longer reachable, in which case it gets deallocated, and then we're left with a dangling reference to uninitialized memory on the Haskell side. And so if we dereference that, we could end up with a segmentation fault. So we really need to essentially register any pointers that we have in the Haskell heap pointing into the Java heap. And so basically what we need to do is that we need to add those pointers as extra roots for the Java garbage collector. Okay, so the JVM's foreign function interface is called the Java native the JNI. And as it turns out, the JNI does have facilities for adding these GC roots. And we basically have facilities for adding two types of references. One is global references and the other is local references. And the global references are really slow and the local references are much faster. And so you really want to be using the local references pretty much all of the time. So let's say that I write Haskell code that allocates a new Java array. And so J here is the type of references to Java things. And here I have a reference to an array of Booleans. That's what the type is saying here in purple. And so at some point, I'll need to tell the JVM that I'm discarding that reference that I'm calling X's because it's a garbage collector root. And so if I don't do that, then the memory of the array will never be reclaimed. In other words, we're facing a situation similar to the early one. A third party, in this case the JVM, and in the previous case it was the operating system, handed us a resource, and we need to manage the lifetime of that resource somehow. So one way to do this is to add a finalizer to the reference instead of having to say, for example, delete local ref manually. Delete local ref is the thing that removes the GC root. But then we have no guarantee of when that's actually going to happen. And worse, we actually have to use, we can't really use local references for this because the finalizer could be run in any thread. It might not be the same thread as the thread in which we created the reference. And so, yeah, we need to use global references, and global references are a lot slower. And the JVM really encourages you to use these local references instead. So the one solution here is do the same thing as we did with sockets, right? We could be tempted to reach out for the same tricks as before. We could use the with pattern to never create a reference without also deleting it eventually. But now I want to show you a more complex example. So now I have a stream, which is at each step, it's calling the next method of the Java iterator and getting a local reference to some object in return. That's the point at which the resource is acquired. And then I have an action that processes that object somehow. And that action must delete the original reference, otherwise we'd have a memory leak. And moreover, if the processing function deletes the original reference, then we are discarding references on the fly as we are mapping over the stream, rather than accumulating references that at best we'd be deleting in one fell swoop later. But now the place at which I'm creating the reference is separate from the place at which I'm deleting the reference. And I can't make them be at the same place without getting rid of the stream abstraction. to illustrate what's going on, let's unpack the streaming abstraction and partially evaluate this code. Let's assume that the original array is just an array of 2 elements, and so morally what's going on is that we're calling the next method of the Java iterator twice. Then we're passing the resulting object to some action, and then after that we're printing the result. So the resource is being acquired in next, and then it must be discarded by some action, because otherwise there's a leak. And so let's zoom in even more closely into some of the code here. If this was Rust code, the next method would be moving ownership. If this was Rust code, the next method would be moving ownership of the reference out into the context, and then ownership would move into some action. And if some action doesn't return the reference, then by the Rust semantics, the reference would be automatically and forcibly destroyed because it is not moved anywhere. So there's no room for error. But Haskell is not Rust, and so we have to do something else. And applying applying the with resource pattern, the only thing we can do here is use the with combinator. The reference is acquired with next, used in some action, and then deleted with the with Java combinator. And so, in short, instead of using bind, which is the standard glue to compose actions, we have to use some other bespoke glue here. And in so doing, we're losing all the abstraction that was built using bind. So set in the framework of John Hughes, next and some action are not independent modules. Implementation details of both leak out into the context and forces us to use a special kind of glue. So rather than bind, which is standard 1, we're effectively using with Java object in its place. Whereas with linear types, we can model something similar to the move semantics of Rust and ultimately avoid the implementation details leaking out. With linear types, we can combine actions using monadic bind, like we do everything everywhere else. It doesn't depend on it's not because of some implementation detail of what's to the right of the bind and what's to the left of the bind that all of a sudden we have to say, ooh, well, these 2 things that I'm trying to compose don't compose with bind. They can only be safely composed with this other combinator called with Java object. So we're using this other combinator just because of implementation details of these 2 components. So coming back to our 2 problems, it sounds like with linear types, we now have a solution to our first problem, namely avoiding resource leaks without running the risk of seg faults. And a pretty general solution at that. And it's one that scales up to handling resources in a way that doesn't force us to give up existing abstractions. And so the second problem is really the other side of the same coin. So let's talk about that for a little bit. Memory is a resource like any other. And so traditionally, we've had languages split into 2 camps, the GC and the GC languages and the system languages. With and the problem is that the languages with that are garbage collected might be pretty slow, and so we might get latency spikes like we saw earlier. So take this, for instance, a post published by Pusher in 2016. They're implementing a service in Haskell, and they have a service that conceptually is an in-memory message bus. And new messages get pushed on one end, and old messages get popped out at the other. And if we look at the thread scope graph here, the pink lines show when a message comes in and into the system. So basically, whenever there's pink, there's productive work being done. but you see that there's not pink everywhere. And where there isn't pink, it's because there's a garbage collector doing stuff. That's the orange that you see over there. And so that means that the 99th percentile latency for this service is pretty poor, of the order of several hundred milliseconds or more. And so that's potentially money lost for someone, as we mentioned earlier. And these latency spikes are caused by the garbage collector. But crucially, they're long spikes because there's a lot of objects that are long-lived in memory. It's not because we're allocating a lot per se. It's just that the working set is very large every time we do a major garbage collection sweep. And so that takes time. And so one idea here is to basically split the heaps into two heaps and to have one long-lived heap in which one heap that's specifically for the data that is long-lived. And so in this case, it's the messages that we're keeping for a very long time in the message bus. And then everything else that are, basically scratch allocations, objects for allocations that happen during serialization and deserialization of the messages, for example. That can all go into this miscellaneous heap, which is managed by the GC, whereas the message heap is uses explicit allocation and deallocation. And so we might be because the allocation deallocation is explicit, we want to use linear types here to make that safe. So in many ways, adding linear types to Haskell has been an exercise in stealing some of the DNA of Rust and sticking it into Haskell. And so Rust has stellar facilities for handling system resources and fine-grained control of memory. And now Haskell has something like it too, but one question they might have been wondering about for a while now is why Haskell? Why do all of this in a functional language? The linear types work started in 2016 when Tweak started an engagement building software that where the latencies really matter a lot, like in the search engine use case, because we were building software for so-called exascale supercomputers, and that's to say computers with 1,000 petaflop compute power, or 1 exaflop, and 1 exabyte of storage capacity. And a lot of the tasks that are running on these computers are bulk synchronous tasks. They need to run. You need to run each step in exactly the same amount of time before they synchronize across all tasks. And so, why did we insist on building software for the high-performance computing industry in Haskell when we could have used C or C++? Well, it's precisely because us dirty and unwashed industrialists found John Hughes' argument convincing. The argument that taming software complexity has a lot to do with being able to compose building blocks using basic glue. Yes, we do want a programming language that lets us represent system resources using non-leaky abstractions, but we also want that programming language to let us assemble building blocks through simple functions, simple functions, and simple function composition, or monad bind. And to mention Rust again, in Rust today, concepts like functors and monads are pretty awkward to define and use. And in Rust, everything is a resource in that everything has a lifetime, and I have to reason about those lifetimes in my code. They appear in the types, and I have to think about them anytime I call a function or even define a variable, because I often have the choice of allocating on the heap or allocating on the stack, and these are all kinds of questions that I don't really need to ask in Haskell unless I specifically opt into all of that. So we thought that it was important because, in my experience in software and building software, you want to be able to iterate fast, and to iterate fast, it's iterating fast that gives you the ability to explore quickly a design space and backtrack often. And you need to be able to write code that you can refactor very quickly. so we turn to Haskell for all the usual reasons. Easy to refactor, and then of course when the code, we use Haskell to build prototypes. When the code grew and became less of a proof of concept, we were glad resources were modeled accurately because with no hidden gotchas, because then we could push that into production and things just work. And so it was very nice to be able to have fine-grained control over performance characteristics of a program when needed. Of course, at the time, linear types didn't actually exist, so we had to pretend that they existed. But now that they've shipped in GHC. And everything I just said counts double when you're writing correctness critical code, which is the other reason to use Haskell. So like in finance and biotech, or when writing embedded devices or embedded software for autonomous cars or autonomous planes. So to summarize, I believe that functional programming matters to us industry users. And in our work, we have to deal with the spleen of computers. And they're pretty messy and complicated. Linear types give us the means to model the essential aspects of the things we're dealing with. And to take the idea of a socket or the idea of a file and express the relevant aspects of those ideals in the abstractions we write as code. Functional programming with linear types, we can still have, with functional programming and with linear types, we can still have all those abstractions, like monads, like applicatives, and so on. And in reality, everything is a resource, of course, but we can selectively expose that reality while programming and hide that reality when it's not relevant. So I focused in this talk on the application of linear types to resources because that's perhaps the most salient angle from an industrial user's perspective. But linear types can bring a lot besides, like a pure interface immutable arrays, the SD-monad, quantum computing, all things that are going to be discussed, presented later in this conference. So leave it to Jean-Philippe tomorrow and some of the other speakers to talk about that. So yeah, thank you very much for listening, and I look forward to any questions if anyone have any. Jurgen, we still can't hear you.
I suppose if we can't hear Jurgen, I can chair the question period. So let's see. There is currently one question here in the queue. Oh, here comes more. But first, I'm going to call on Gergo. So I'll just read this one off. Why doesn't or can't RIO just replace IO? Why do we need a separate type?
In principle, it could, but if we did that, and in fact, so the system that was designed that was published in the linear types in the Pablo paper that presented linear types in 2018 includes multiplicity polymorphism, and it's designed in such a way that you could use Rio as just the IO monad, and everything would just work. The way the Rio monad is implemented today in linear base does incur probably a little bit of overhead, although we haven't really measured that, but it incurs, in principle, a little bit of overhead relative to just straight up IO. And the reason for that is if you want Rio to really be a correct abstraction for a resource-aware monad, then you need to be dealing with all of the vagaries of Haskell. And in particular, in Haskell, you have such a thing as asynchronous exceptions that could be sent to a thread, or synchronous exceptions. So when those exceptions happen, you want things to be deallocated. You want things to be deallocated even as you're unwinding the stack. And so we basically do some extra bookkeeping right now in the Rio monad in order to deallocate in all circumstances. But this is a minor implementation detail that might not matter to the community, and so indeed, maybe we can just redefine IO to be Rio.
Great, thanks. And that question was from Gergo Erdi. Mark that as answered. Okay. Next question I see here is from Dominic Orchard. Do you envision a route for these ideas to make it into other, quote, mainstream languages?
So I think that the ideas here are, I mean, they were developed in the context of one particular programming language and a functional one at that, Haskell. But I think it's at least applicable to most other functional programming languages. And but beyond that, we just haven't really thought about it very deeply when it comes to say more imperative languages. And I would say that, for example, the solution that Rust has is quite different from this one, but it works extremely well in the context of Rust. It works extremely well in the context of Rust because Rust is an imperative language, and the goal of Rust is just make the imperative style safe. Whereas Haskell is just, it's very different type of code. So I'm just not sure that we can say, hey, here's a new invention, let's use it like a hammer and go apply it everywhere. I think it's relevant for a number of other functional programming languages. I'm just not sure about the story in imperative languages.
Thanks. Let's see, we'll mark that answered. So this question is from Ryan Newton. Of the potential future work remaining in linear types, what do you think is most important? 1, linear constraints. 2, supporting linear let bindings. 3, something else.
So number 2 is something that's pretty important, but it's not too difficult. We're basically there as far as I understand. But linear constraints is the one thing that I'm particularly excited about, because if you look at the, for example, the socket code that I showed earlier, I said, hey, look at that. It's great. It's resource safe. There's no way that I can call send to after I closed. There's all kinds of bugs that just disappear. And as I was showing before that, these bugs do exist in practice, but now they've just become impossible. That's a great promise, but it comes at the cost of having to come up with all these fresh names all the time for any time I interact with my socket. And that's a real downside, very practical downside. And so it means that in practice, when I'm writing this network code, it's just going to be a lot more annoying to do it with the safe interface that I was proposing relative to the original interface with sockets. And so linear constraints is one possible solution to basically get away from that tedium. So I think that with the linear types that we have in GHT 9.0, we have the basics to allow you to write code that's resource safe, but we don't it doesn't mean that the user experience is going to be particularly great at this point. And then I think that linear constraints, is going to be what's going to be really key to getting the user experience to a much better place. And something else that I would add here is that Rust has been doing this for a while, and every iteration of the Rust compiler, every new release, have been a lot of improvements to the user experience there. And so I think you're going to see a similar thing happening with GHC, where with every new GHC release, we're going to make it, we're not just going to focus on, hey, let's enable people to, in theory, write resource-safe code. We're also going to make it easier for people to make it convenient for their users to write code that have linear types in their APIs.
Thanks. This one is from Eric Gorelick. As you say, most languages are cleanly divided between systems and GC'd, with not a lot in between that could be used for applications like soft real-time. Do you think linear types could make Haskell be the language of choice for such applications?
So I think, you could have designed. This is not inherent to linear types. You could have designed Rust in pretty much the same way that Rust is designed today. But for example, I don't think that it was necessary to give all these very strong guarantees in the semantics of Rust that make it so that the compiler is exposing to you whether it's going to allocate things on the stack or whether it's going to allocate things on the heap. You could imagine a kind of pared down Rust and maybe this might be the future for Rust, where you do have a garbage collector, and so then sometimes you use the garbage collector, sometimes you don't. The design that they would have there wouldn't really use the linear types as proposed here. But indeed, I think that for most applications, the future probably is a language where not everything is a resource, but some things are resources because you want them to be resources and you want to expose that reality. And then for the rest, you don't want to. I very much believe in that middle ground between, say, today's Haskell and today's Rust. I just want to point out, and linear types is one way to get to that middle ground. I just want to point out that there are other ways to get to that middle ground too.
Next question here is, I think it's a follow-up about the RIO versus IO. Or maybe not, maybe it's not a follow-up, but it's also from Gergo Erdi. How can you deallocate if close is now just a random but linearly typed function?
I'm not sure I understand what random means here.
So I'll invite Gergo to the stage. I know earlier he didn't have a mic, but maybe he does now.
Yeah. Can you guys hear me now?
Yeah, yes. I can hear you.
Yeah, so what I meant is that, when you were talking about RIO, you said that it has to be prepared to deallocate resources even in the face of exceptions. But the whole point of the socket API that you showed us was that there's no with pattern that would connect the close function to the creation of the socket. So it seems to me that we now have a random function that just happened to be called close, and it happens to close the socket, but it's not connected to the socket itself. So what does RIO do if there's some exception coming from somewhere? I'm just not seeing the connection here.
Yes. So you can imagine that the RIO is going to expose some primitives that are not otherwise available to the user of the socket API, but are available to the implementer of the socket API. And so then the implementer of the socket API is going to use these primitives to say, hey, this is close. And close is not just a random function like any other. It's a function that does something special to resources. And so, the answer then, I guess, is no, close is not a random function, but because it's implemented using a little bit of magic, but that magic is not part of the socket API, and so isn't a problem for the users. It doesn't break the guarantees for the users.
Does that answer your question, Gergo?
Well, it does, but I feel like I would need to know more details to form an informed opinion about it. So yeah, I'll take it as an answer. Sure, thanks.
Happy to discuss more in the lounge if you like.
Okay, let me remove Gergo from the stage. And then looks like this will be the last question from Adam Gundry. Another way to handle the long latencies caused by GC pauses is to use a low or no pause GC algorithm. For example, the non-moving GC in recent GHC versions. How would you say this compares to the linear types approach?
I would say all the more power to users. This is great. I think that there's no, let's take, for example, take the pusher use case. As I said, there's multiple ways to skin that particular cat. And so, one way is to use linear types, but there were other routes possible there. And for example, if the blog post, they wrote a blog post, and the blog post I was referring to dates back to 2016, which is before the new GC, incremental GC, made it into GHC. And it's possible that just by using this new GC, things would have been good enough for their particular use case. And it's possible that there was no particular need then to split things into two different heaps, with one heap that's managed manually and another one that's still managed by the garbage collector. Or maybe they want to push they want to get even more control over the latencies. They want the tail end of the latencies to be even tighter, in which case maybe they eventually do need to move to linear types. It depends on the use cases. It depends on your measurements. It's good to have multiple tools in your tool set to bring to bear when you have a performance problem.
Great, thank you. And we have one more question that has appeared. I do think this is going to have to be the last one to give everyone a break. But let's bring it up here. This is from Artem Penelitson. Judging by the experience in Interest 2, linearity can improve developers' experience and help to synthesize parts of code more effectively than in an unrestricted setting. Is Twig interested in working in that direction? For example, extending HLS to support linear types.
So this is absolutely one of the big promises of linear types. So now you mentioned Idris 2, and Idris 2 is a dependently typed language. And one thing I didn't mention, but is worth noting, is that the way we designed linear types was specifically, we specifically had in mind when we designed linear types the idea that it would have to be compatible with dependent types down the line, because we're hoping that Haskell will itself become a dependently typed language like Idris is. And something that I can say is that, going back to 2016, when we first started looking at linear types, we were actually wrangling. We were thinking about these pretty complicated protocols, and we weren't quite sure how to design these protocols and whether what we were trying to do actually made any sense at all. And so part of the reason why we started thinking linear types, and Jean-Philippe and Arnaud Spivak can we're closer to this at the time and can tell you what came first. What was it, the performance concerns, or if it was the aid in the design of the protocols and the design of the code that was more interesting to them. But this was definitely part of the story from day one for us. There were definitely both motivations. I focus more in this talk on one particular motivation, but both do exist. And I very much hope that we can get very nice integration the IDE experience for Haskell in the future, and with HLS specifically, because I think there's a great promise. And you might have seen some of the videos from Edwin Brady here that show the power of linear types, in particular with regard to code synthesis. And it would be absolutely fantastic to have the same in Haskell, and I see no reason why we would not have that in Haskell 2 down the line.
Great, thanks. Thank you so much for coming to Haskell Symposium. Let's all thank Mathieu again.
Thank you for having me.
We now have, I guess, 22 minutes until the next paper session of the day. So we'll see you back here then. Thanks all.
See y'all.
All right, I'll kindly uninvite Mathieu. We're still here. I'm going to bring the speakers in. Jamie, where are you?
Just so you know, your camera's off.
Yeah. Ah, Jamie's not here yet. Is Nicholas here? No. Okay. Let's hope they show up. That's weird. Jamie?
Hello.
Hi.
Hi.
And I was supposed to invite Nick too, right?
Yeah, Nick as well.
Yeah. Oh. And you can start sharing your screen if you want.
Yeah, let's go ahead and do that. Share screen, window, this one.
Yeah.
Good.
I can see Nick moving around. I can hear Nick. I can hear Jamie. Excellent. So we're good to go. My audio works again. Your audio works. I can see the slides, or at least, yeah, the slides essentially. And I'm going to give the floor to you, Jamie. Design patterns for parser combinators. And this is actually a functional Perl.
It is indeed. Right. Hi, Nick.
Oh, hi, Jamie.
I saw you having a bit of problems on the pull requests that you submitted yesterday. Do you want to take a look?
Yeah, I was trying to implement a parser combinator for the parser for the really cool calculator on your app, but something went wrong. So let's have a look at GitHub and see what's going on. I guess people can follow along if they go to the link, right?
Yeah, I posted it in the chat. We've got a few visitors to this code review. Let's check out the issue first to remind ourselves what we're actually meant to be doing. So I think your task was to write a parser, right, for this grammar here. It's got, the standard stuff: addition, subtraction, multiplication, unary negation, and various other goodies, right?
Right, exactly. And I was trying to parse this into a simple AST, which is basically a bunch of constructors of type expression, which sort of do the usual thing.
Right, yeah, I think this is the one you mean, right?
Exactly.
Yeah, lots of little constructors, one single AST. Okay, that all looks good. So should we take a look at the pull request then? And see
Right,
what's going on?
exactly. If you look at the pull request there, you'll see that the CI engine, the continuous integration, has failed, and there's something wrong in the test, and I can't quite work out what's happening.
Okay, let's take a look and see what actually went wrong. Okay, so it looks like it timed out, and on a very small example as well.
Yeah, exactly. I'm quite surprised.
Okay, let's have a look at your commit and see if we can figure out what's gone wrong. So why don't you talk me through what you've got here?
Well, okay, so I'm just using parser combinators in the very ordinary way. So you can see that I'm parsing alphas. That's going to say it's 1 of A to Z, lowercase or uppercase. Digits are 1 of 0 to 9. Something that's alpha num is either alpha or a digit. Never mind about numbers, but basically we're folding up a whole bunch of digits. An identifier is an alpha followed by many alphas. And I guess the interesting thing here is really the expressions. So an expression is just an add constructor followed by an expression that we parse, followed by parsing a character plus, and then going on with a terminal. Similarly with subtraction, it's going to be sub expression and then the minus symbol and then a term. Or it's just a term if we have no add or sub, and then term is going to be mul with exactly the same stuff. So quite a straightforward application of parser combinators. I can't see what's going wrong.
Yeah, so you've modeled this exactly like the grammar. They look very, very similar. That's kind of the problem you've got here. Actually, you're running into left recursion. If you see here, either of these cases are left recursive. Let me go to an example so I can show you a bit clearer what I mean by that.
So what you're telling me is left recursion is somehow a problem with parser combinators?
Yeah, for quite a lot of parser combinator libraries, it doesn't work out so well because they're implemented with recursive descent. So if you look at a parser like this, which is meant to represent this regex here, this is fine in a BNF sense. But if you think about how this gets evaluated, we try evaluating bad. And in order to do that, we evaluate bad immediately. And where do you go after that? Well, you evaluate bad again, and so on forever. It's never going to terminate.
Oh, don't tell Andras about this. I worked for him for years and I didn't realize this kind of thing. Well, maybe you can refactor this grammar by having char A, char B, and then adding bads on the end of it or something.
Yeah, so you can do some grammar refactoring techniques. I don't like those for parser combinators because it kind of exposes implementation details in the grammar itself. Actually, I was thinking about this recently, and most parser combinator libraries support these chain combinators. And they basically abstract this repeated application of a parser to an operator. Let me just push that into the library and I can show you what I mean. Okay, so let's go and have a look at them. It's a bit easier, isn't it? Okay, so here's what I've added. 2 combinators, chain L1 and chain R1. If you look at their types, they both take a parser that makes A's and one that makes operators of A to A to A. And it will pass P op, P op, P op, P, and then it will apply those operators, bracketing either to the left or to the right.
Ah, okay, so I see. So rather than just writing things out manually and then doing recursion, I can use these chain combinators. So let me hack up some code really quickly that will do the right thing. Right, I've pushed that up. If you should be able to find that in just a second.
Looks like
here it comes.
It's working its way through the pipe. There it is.
Okay.
Right. So tell me through what you've done here then.
Right, so I've removed the code on the left-hand side there, and I've replaced the recursive calls. So in the definition of expr, we don't need to make mention of expr itself anymore because that's dealt with the chain R combinator. And then I've said that the leafs are called terms, so that's going to be the first parameter to the chain R. And then what we're doing for the operations is either an add or a sub, and so we just parse a char plus or char minus as appropriate.
Great, yeah. And actually combining the operators in this way is slightly more efficient than the original representation you had, and it won't require any backtracking. Let's see if the issue is then fixed in the CI. Looks like it's still churning its way through.
I guess another 10 seconds to go or so.
Hopefully.
So the hope is that with parser combinators, we can basically replace common patterns with things that we see happening often, and that means we have less to think about, right?
Yeah, exactly. So the advantage of parser combinators is that they can be used to build parsers as building blocks, unlike something a bit more rigid like a parser generator. So we can build these combinators to manipulate things. Oh, it looks like actually the test did fail.
What?
Let's have a look. Okay, so we have a new example here, neg of num0, and it looks like the parser failed when it encountered a space. Have you actually handled spaces or lexing at all?
Spaces? What? Oh, okay, so this is classic. So spaces weren't part of the original grammar, so I didn't encode them in any way whatsoever. I just sort of followed it blindly. I guess we'd need to somehow have some spaces put in everywhere inside the grammar, right?
Yeah, actually, I've got an issue about this. So yeah, you could add in these white space combinators all around the parser to fix this. But actually, I think that's quite intrusive to the overall structure, and it's quite cluttered as well. We want to keep it looking like the BNF, which actually doesn't have these things in. Actually, I think the cleanest way to do this for you would be to split this into a lexer and a parser and expose, say, a token combinator and a fully combinator to sort of handle white space in a more controlled manner.
Ah, okay, I think I get the idea. So let me just patch that up as well. So we want some kind of combinators and we want to, there we go. All right, let's have a look at the code. I've just pushed.
Oh, wow, it's up there. Okay, so talk me through what you've done here then.
Okay, so this is essentially the same. And I think what's interesting is going to be the white space combinator below. And that basically says that white space is, if you satisfy that something is space, there's many of those. And we use that void combinator to make the types work. So the parser has type unit. And the real interesting part is that a lexeme is basically some parser P followed by white space. And what a token is we just try first and then we do a lexeme. And that the idea there is that you can roll back to the point before the token. So you parse the entire token or not at all. The last bit is fully. And the idea here is that we've got this lexeme combinator which gets rid of all trading white space, which means we just have to deal with the leading white space that might exist at the very beginning of the file just once. So we do that with this white space followed by P, followed by the end of file. And if you scroll down a bit.
Okay, so it's being used there.
Exactly, that's right, yeah. And for the expressions, I guess it's just an easy case of wrapping everything around with token because that's what that was designed for, right?
Okay, yeah, sure. Actually, I think you've done quite well here because you've established a consistency about white spaces, where white space is passed, and that can be quite important. So these all look great. I would think that the test's actually passed now. Actually, it looks like the 8 has still failed again.
What? More failure?
More failure. Okay, so, right, this is a classic problem. So we've got a variable here that was generated by QuickCheck. It's the variable negatex. So this is one variable on its own. And we expect negatex to come back, but it looks like the actual passed term was negate of x.
Wow, hang on, this is a bit confusing. So negatex isn't some random word you made up, is it?
It's been built into the actual unit tests here. It's QuickCheck can find this as a variable name, but it should be handled as a specific single token, and your parser has broken it into 2. In other words, you need to ensure that when you pass negate, you don't allow it to be a valid prefix of an actual identifier.
Huh. Oh, I see. So the problem is that negate is actually a keyword rather than a token or an odd. Right. Okay. And so somehow I need to deal with that.
Yes.
Okay. Well, let me see if I can hack something up for this as well.
Okay.
So good thing you're my PhD student because I don't think I'd be able to afford your services.
Yeah, I charge a lot by the hour. Okay, looks like that's gone through. I'm really liking your commit messages, by the way, very descriptive.
Yeah, I think they're just an important part of what we do.
Okay, so talk me through what you've got here.
Okay, so what we have here is I've added this keyword combinator. So a keyword K is basically that's string K not followed by anything alphanumeric because that's what determines the fact that it's a keyword. And then it's a simple case of replacing token with keyword in the actual grammar for the word negate. And hopefully that's going to be the last issue we need to deal with.
Great, yeah. And it looks like you've also made sure that you've atomized it after doing that check, which is quite important. So that's good. Let's check on the CI if it's still... Okay, it's still running. So actually, while we've been doing this, I've actually realized there's a bug in the pretty printer. So I'm just gonna push that through, and I can explain what's going on with that. Actually, it looks like our test did pass for that, which is good.
It did pass, good.
But there is this bug. So it turns out whoever implemented the pretty printer forgot to put brackets around this parentheses node, which obviously isn't the right behavior.
Don't quite understand. I'm seeing the word strong here. What's that?
Oh, right. Yeah, actually, there's two types of AST in this code base. As we saw earlier, you're working with the weak one. There's also this strong one here. The difference is that each of the grammar rules is actually represented as its own data type here. And what that means is that it's a bit stricter about what things can appear where. And actually, the explicit introduction of parentheses means that it's really easy to pretty print with minimal brackets.
Oh, I see. So this is basically following the BNF, but at the data type level much more closely. So it's a kind of much stricter version, a much stronger version of the data type.
Yeah.
Seems like that'd be quite useful for catching all sorts of errors that you might not think of.
Yeah, and at the moment, we're just converting between the two whenever we need to. I mean, I would hope that it doesn't affect the CI, but it looks like it actually has. So we've still got a problem with our parser then. It looks like this time the test case is an add with a subtract on the left, but actually the result that we've been given back has the addition on the right. Remember, so plus and subtract on the same level.
So the test case here is where the data that we're trying to test has left associative things, but the parser is parsing as right associative?
Exactly. But we fixed that earlier, right? Let's have a look at the commit that did that. It was this one, right?
Right, I fixed that already. See, even says so in the commit message, chain L.
Chain L, but it looks like you're using chain R in the actual code.
Oh, rookie error. So I should have used chain L instead, and that would have worked out just fine.
It would have done. Although, actually, I mean, you could just fix it like this, but it's not really going to help. Anyone could make that mistake again. I think, actually, it would be really good to use that strong AST that we were talking about. And the problem is that the chain combinators don't have the right type for it.
Right, so yeah, it was not good enough that I can just swap in chain L and chain R. If only we had some kind of stronger types, then we'd be able to fix this error. But then I can't use chain L and chain R because the types won't fit, right?
Exactly. But as it happens, I've actually been playing around with some new versions of the chains that actually will help here. I'll just push them up and then we can take a look at how they differ.
Okay.
Okay, so they should be coming through any minute. There they are. So the key difference here is that instead of having A to A to A, they have B to A to B and A to B to B. These look very familiar to classic fold R and fold L. And actually the B's represent the associativity. B's bind tighter to the left here for infix L and tighter to the right for infix R.
Ah, right. Clearly we need strongly typed PRs. Well, in any case, this looks just like a fold left or fold right pattern, right?
It is. And actually these wrapping functions that get added as the first argument help to convert a terminal P into, a K-like parameter for the fold.
Okay, so I think I know how I can patch this up. So let me have one last go at this. Okay, it's on its way. Hopefully.
Get through those pipes. There it is.
There we go.
Magic of the internet, right? Okay, so tell me what you've done here then.
Right, so I've replaced your weak AST with the strong AST, so that changes the data types a little bit. And the key point is that I'm using infix L rather than chain R. And obviously the R was the bug, now it's an L. But the infix is making it work out type-wise. So it goes from an expr, which is going to make a parser expr, to a term, which is a parser term. And going from an expr to term requires the of term constructor. And so that's what is being fed in as the first parameter. And then going from term to negate needs of negate. And then going from negate all the way back up requires a parser, a parens. Well, that's for the atom, actually. And hopefully that should fix all the issues we have, right?
Yeah, this should fix the issues. It looks like the CI is still running through. I guess while we're waiting for that, we can think about whether there's anything else we could improve about this here and now.
It is a little bit annoying, yeah.
But go on, go on.
Well, I think I'm a little bit annoyed by the fact that this looks quite close to the grammar, but there's a bit of clutter, right? There's this like token char and keyword negate and all this kind of stuff hanging around.
Yeah, absolutely. I mean, we could kind of unify the token char, or I guess token.string, with keywords, and actually check whether the argument provided is a keyword in order to sort of make things a bit more uniform. But you're right in that, you know, these keywords combinators still have to appear in the thing, and it makes it look less like the grammar. I don't have any solutions to that offhand. I don't know if you have any thoughts.
Actually, I do have an idea. We could probably use overloaded strings here, couldn't we?
Overloaded strings? I don't think I've heard of that.
Ah, all right. They're just a GHC extension that means that when you type in a string, what you get is basically any type that you want, so long as you have a way of converting from a string representation to that type. And so in this case, we can basically farm out the job of getting the right tokens or keywords just by doing some type inspection and letting classes do their work. So let me just do a patch view for that one.
Okay, and while you're doing that, let's I'll check on this CI. Looks like it's all passing again.
Good.
So we definitely have a working parser.
Now, hopefully, that patch has arrived.
It has. It has. So yeah, talk me through what you've got here.
Right. So now the keywords are all held inside this list of strings called keys, which holds in this case just a single keyword called negate. And the interesting part is the isString instance, which is what the overloaded strings use to create new strings, to create things from strings. And if you take a string and it's an element of that keys list, then it's a keyword, and that's what we do on the right. Otherwise, we say it's a token, and we just use the same combinators that we had earlier. And if you scroll down to the grammar, that just means that everything gets cleaned up and everything becomes much simpler and neater.
Oh, this is lovely, isn't it? So none of the garbage sat around. It's just string literals, which is basically what the BNF grammar looked like.
Exactly. Well, with so many lessons that we've learned, I just wish there was a place where I could go to read about these different things when working with parser combinators.
Actually, yeah. I mean, you've been pretty quick at coding this stuff up, but as we've been talking, I've been writing. And it turns out that I've already prepared a paper for us.
Oh, wonderful. And it's been accepted at the Haskell Symposium.
Nonetheless, yeah. Let's have a look.
Great.
So I've basically started with the same initial problem and parser that we had originally. And I've outlined, as I've gone, the different problems that we've encountered, as well as what the various solutions are in, you know, quite bold boxes. There's actually more than one pattern for some different solutions, so they've been added. And there's even some goodies that we haven't talked about today, but I guess those can wait for a future PR.
Oh man, I thought that parser combinators were useless, but turns out they're actually really good for parsing with. Thanks very much.
Yeah, absolutely.
Good. Well, I think that's all we have to talk about. So I guess I'll catch you later.
Yeah, great. Thanks for your time here, and we'll get this PR merged and ship our product.
Don't forget to unlock the repo.
Oh yeah, absolutely.
Thanks.
Thanks.
All right. Thank you very much for your interactive
no problem.
presentation.
Yeah, I'd just like to plug quickly that I do intend for this repo to now be a place of future collaboration and things. So people can feel free to visit the discussions and you know, share their own patterns, or you know, do a show and tell of whatever they want. So I intend for it to be a little hub for parser combinator pattern-y related things. Yeah, thanks a lot.
Great. So are there any questions? So I see a question by Tom Smeding. I'm going to show the question on stage and read it out. So this requires a list of keywords that must agree precisely with the list of keywords in the grammar and appears disconnected from locations in the grammar where the keywords appear. Could this perhaps be made more foolproof?
Right, so I think the last pattern that we showed off there actually helps address this in part, because you basically package all those keywords together, and the strings that you use inside the actual parser get checked. So you still have to list the keywords out from the original grammar, but you don't have to remember which parts of your parser need the keyword combinator versus the the token of string, which helps a little bit, I think.
Is this okay for you, Tom?
I saw a thumb.
Oh, wait a minute. I probably have to invite him to the stage, otherwise he can't react.
He says yes in the chat.
Oh, he says yes in the chat. Then I can remove him from the stage again. Okay. Are there any other questions? Oh, I already see a question by Artem. Do you ever consider performance impact of various patterns, like rejecting some patterns on the basis of poor performance?
Right. So I guess, yeah, the ideal pattern is not only good, but keeps its performance. Performance is a bit of a relative term. The ones that we've done so far, the chains, for instance, they will help performance. The lexing ones can help performance depending on how they're used. I think most of the patterns we've done don't impact performance too much, but actually it depends on the library. If you're using some libraries like my very own Parsley, a lot of any overhead that could be introduced has been eliminated at compile time anyway. So it kind of depends, but there will certainly be patterns that might sort of damage the performance, but not in an asymptotic way. So it probably won't make it way worse on larger inputs, but it might just increase the constant factor. You're always gaining something from it.
I think your question sort of reminds me, so you're talking about, would we reject some patterns? Something that we wanted to do in the paper as well was actually talk about anti-patterns, so things that you don't want to do. And so if you go and have a look there, then you'll see there are a few more things that we've said that, you shouldn't do this, you shouldn't do that, because they tend to be, they look like solutions to start with, but they turn out to be bad things to do.
Right.
Thanks. Any other questions? So then I have a question, maybe a final one. So I mean, there are quite a number of partial combinator libraries out there. I mean, and this is kind of focused on one particular implementation, but you also have monetic partial combinator and stuff like that. I mean, are you going to develop versions for these other partial combinator libraries as well, or does it make sense at all?
So the patterns that we've got in the paper so far are actually applicable to basically any library. Some aspects of them will not be required. So there are libraries without try, for instance. So you can sort of just ignore try when you see it in the paper, but they're sort of widely applicable to everything. So I guess there are patterns that are specific to some libraries that are going to be uncovered eventually. But yeah, they're sort of widely applicable. The interesting one is that the chains are something you don't see in Megaparsec, but they actually favor precedence combinators, which is something that the paper also describes. So, there's something for every library in there, I think.
All right, and then Noan has a question. He also needs some help, it seems.
I am always available, just at me.
For money, I assume, right?
Well, it depends on the project. I'm always willing to help open source, right?
All right, I'll mark this as answered then. So this is a meta question, I guess, by Andreas Klevinger. How often, if at all, did you practice this talk? He loved the delivery.
So I actually have a count of how many times we did it.
I think this is take 4, isn't it?
This is this is take 4, basically, of like the finalized thing. But we only started actually preparing together 2 days ago. So we had the idea in the back of our head for a while, and I sorted out all the repo and the various Git patches. Turns out archaic ways of transmitting Git commits by email actually useful for something in the modern day. And then we actually got together and decided on what we were roughly going to say within the last couple of days.
Every take is different.
Every take is unique in its own special way. And the CI gets delayed or fast in different ways for each talk. So how do you ever know what it's going to be like?
Okay, so and related to this, Jeremy asked, how much of it was live or canned video? Or
everything that you saw here today was 100% live.
And we were very pleased that GitHub didn't crash. And you know, I wish we were sponsored.
Yeah, I wish we could say that, you know, we asked GitHub to make sure that nothing went down, but we didn't. It could have all gone wrong. We did record yesterday's last take just in case, but turns out we did not need it.
Great. All right, I'll mark this as answered. And I don't see any more questions. So I want to thank the speakers again for their impressive performance and answering all our questions. I'll kindly remove both of you now to introduce the next speaker.
Bye, see ya.
See you. So let me look for that person. Click. Finbar Keating is invited to the stage.
Stage, I think. Let's turn on my camera. Yeah. Oh, that was such a good talk. I really enjoyed that.
Yeah, and now you're up next. You're up next.
Yeah, no pressure.
So
like,
no pressure.
I'm afraid I'm not going to write a paper during this talk or magically make a bunch of Git pull requests. That's so sad. But God, that was so good. Right. Tell me when I should go, I guess.
Yeah. So what you can do is, I mean, you can explain to us exactly what are graded monads and about type level programming for dependence analysis. Go ahead.
Yeah, I will. All right, I'll just get started then, shall I? Right.
You can.
Hello, I'm Finbar, and today I'm going to talk to you about this joint work with Michael Gale on graded monads and type-level programming for dependence analysis. There's quite a lot going on in this title, so let's start off with a motivating example. Oh, gotta click. Here's a robot I found earlier, and what we're going to do is take its sensors, like this distance sensor, and its actuators, like this motor, and represent them as mutable memory cells, like I/O refs. So on this robot here, we have a distance sensor, which you can read from to get the value that's currently being detected by the distance sensor. Same with this light sensor. We have a pair of motors where you can write to them to set the speed. And we have this robot screen, which we're going to use as both an input and an output. You can write to it to set the value on the screen, and you can read from it to get the value that's currently shown on the screen. With that in mind, what we could do is define our robot's functionality as a collection of computations that read and write from these memory cells. So here, for all of these computations are represented by these arrows, where they go from the cells they're reading from to the cells they're writing to. So we have this remove error computation, which reads from the distance sensor. Maybe it removes some error or whatever, and writes that result to the robot screen for debugging. Then we've got this write to motor that reads the result that's stored in the robot screen and writes it to a motor. And then we have this hit if dark, which separately reads a light sensor and then maybe turns on the motor when it's dark enough and it's detecting an object in front of it. And on the right, we have two possible implementations for this. There are lots of implementations, but here are two of them. The first one, we sequence them with remove error, then write to motor, then hit if dark. And then with robot prime, we swap the first two. Now, here's our problem, and the main thing we're going to focus on in this talk. If we run robot prime here violates a data dependency because it ends up using an old value from robot screen. So by running it first, we get the old value, and then we update the value of robot screen with remove error afterwards, which is a problem. Ideally, we would like these values to be propagated for the network properly. This might be fine if these computations are being run like once every 30 times a second or whatever. But if we have a sensor that only updates every few seconds, then you get a real problem because that motor will be the wrong speed for a few seconds and could cause the robot to crash or do something similarly bad. Furthermore, we'd ideally like to not worry about sequencing these things at all. An example here is hit if dark, which could be run anywhere within the order of computations. but we still have to sequence it because that's just how I/O computations work. You have to write the order and give that order. So ideally, we'd like to solve this. One thing I should also mention is the fact that our sequencing error that we talked about, this remove error write to motor issue, is mainly caused because the types aren't specific enough. If we consider both of these definitions are well typed, because neither of them talk about the reads and writes that they're exactly doing. They just go, oh, there are some reads and writes. Trust me, this is all going to be great. So ideally, we would like some better types to represent these computations with, and then have some way of avoiding the sequencing. And we're going to do this in 3 steps. First, we're going to make the computation types more specific, as I said. So instead of having these I/O units, we're going to make them reflect exactly what reads and writes they do. This is the graded monad part of the talk, spoilers. The next thing we're going to do is take a look at these types and prevent dependency violation at compile time by using type families to order them. Then finally, we're going to take this compile time result, this new type that we've got that correctly orders the computations, and apply this result at runtime, which requires a few extra steps that we're going to briefly talk about. So, first section, make computation types more specific. As I said, we're going to look at how these computations are currently typed, and then introduce more specific types that detail these reads and writes. So, here is an example implementation of write to motor, one of the computations from the robot example we just showed, where we're essentially going to get the value from the screen and then immediately write that value to the motor rather than doing anything with it. This is a very simple implementation, but you could imagine more complex ones being here that actually do something with the value. To do this, we're going to get the screen val by reading an IORef. For this talk, we're going to stick with IORefs. And we would really like it if this type reflected the fact that we read from the screen variable specifically. Similarly, for put motor, we're just going to write to an IORef, and we'd really like it if that type reflects the fact that we wrote to motor. And then finally, we would like the type of the composition to reflect both of these things, so that we both read from screen and we write to motor. Fortunately, we have a neat solution for this in the form of graded monads, introduced to Haskell specifically by Orchard and Petracek back in 2014. Here's the existing definition for monads in Haskell, and we have a bit of a problem. If we wanted our computations to say somewhere in their type, oh, I do this read, and oh, I do this write. So let's say we wanted this first computation to have an M which says I read from this variable, and this M to say, oh, I write to this variable. We can't, because these M's have to be the same. But fortunately for us, graded monads solve this problem by introducing a type parameter that the monad, or by parameterizing this monad over a monoid. This monoid has a unit type, which represents the parameter of doing nothing. So our return operation now has this M unit A type to say, we don't actually do anything here. We're just bringing it into the monadic context. And then we have plus, which takes 2 parameters and combines them. So what we can say now is if we have some MFA where maybe F is reading from a variable, and then we have this A to MGB where G is, oh, I'm going to write to this variable. We can now combine them with this plus operation to say, oh, we do both of these things. They've been used in a variety of different contexts in the literature, like dealing with concurrency, avoiding deadlocks in concurrency, and making better reader monads that allow you to see exactly what's being read in them. But this is a fairly new, this is a new application. This is the type that we use to encode our reads and writes, and therefore to encode the dependencies between computations. We add a parameter S, which represents the cells being read from and written to. So we represent these as a pair of type level sets. We're using a single parameter because that's what fits with graded monads in the literature. These are treated as type level lists of type of kind star, but morally we're going to be treating these as sets. And in the actual code provided in the paper and alongside the paper as an artifact, we use the type level sets library. This monad is accompanied with this run memory function that takes in the memory cells being used. So this is the value level representation of the cells in our sets. and gives us a computation out where we take in the things we're reading and writing, and then we read and write them. It's that easy. This is a graded monads. We provide the type family we provide unit and plus as follows, where unit is the pair of empty sets saying we don't read anything and we don't write anything, which makes sense. If we return, then we're not doing any memory, we're not actually accessing memory at all, so we have these two empty sets. And then we have plus, where we take the element-wise union of the two sets. So the combined computation does all of the reads of both computations, and the writes are the combination of the union of the two sets of writes. Final thing we need to do is we need something to put in that type level list. And what we do for that is we name memory locations rather than just using raw IO refs, which would have some problems because we want to look at we want to check uniqueness of types effectively. And if we say if we only use an IO ref, then you're only allowed one IO ref int, which is really bad. But we associate them with a symbol kind, which is a type level string that allows you to give our IO refs a name. So to give an example of that, we have input here, which is an IRF int, and then we turn it into a cell simply by associating it with a type level string. In this case, we've gone with input because that makes sense. You can do this either with an explicit type annotation or with a type application, which is lovely. And with that, we can now define our own read and write operations that do this properly and that successfully track our reads and writes. So we have read IO cell here, which takes in an IO cell with the name S and the type T and gives us a computation with that as its reads, no writes, and a thing of type T. And similarly for write IO cell, except we're storing it in the list of writes rather than the list of reads predictably. So with that, we can now rewrite our initial example. We have getScreenVal now successfully mentions the fact that it reads from screen, and we use read IO cell to confirm this. Put motor reflects that it writes to motor, and then we take the union together, and wow, that's exactly what we want. We now have computations that effectively represent the reads and writes that they do. So now we need to actually prevent this dependency violation, and this is where the type level programming comes into it. We're going to build a dependency graph and word this as a graph problem, but first of all, we need to do a few extra little steps to make sure that everything, well, to lead up to that point. So first thing we want to do is talk about what our goal is for the rest of this section, for the rest of this talk. So what we want is now we've got these better types, we can represent a group of computations as a H list, a heterogeneous list. The definition is given on the bottom of the slide, but the main things you need to know are that this colon plus colon operator is list cons, H-nil is the empty H list, and the resulting type corresponds to the types of its individual elements. So for example, remove error has the type disk to screen, hit if dark has the type light to golf, write to motor has the type screen to motor. Note that we're shortening the types here because otherwise the types are going to get very long, and that is an issue with using graded monads and using these kinds of type representations. We're combining these computations arbitrarily. We don't care about the order because the compiler is going to fix this for us. So as it says on the slide, we're going to use this type information to find a valid ordering for these that does not violate any of the dependencies. So step one, we need to determine the order of these computations more formally. So we need a type family that says this computation must run before this one. We use the notion of data dependencies from an old Bernstein paper. So for example here, write to legs has a dependency on remove error since remove error writes to screen and write to legs reads from screen. So we need write to legs to run after remove error. This can be implemented as a fairly simple type family where we're just pattern matching on each of the components and then getting the intersect of the intersect of the cells written by one computation and the cells read by the other computation, and checking whether it's non-empty. That is there a cell shared by the two that forces a dependency to exist? And you can see that in work here. So we have MIO applied to MIO disk screen, MIO screen motor. There is a dependency. So this type family correctly shows us that this dependency exists. So what we're going to do now is generalize this, or not generalize this, apply this to all of our computations pairwise to build a dependency graph where an edge on the dependency graph represents there being a dependency. So in this example, there is a dependency. Right to motor depends on remove error, but there are no other dependencies. So this is our resulting dependency graph. And with that, finding a valid ordering is simply just finding a topological sort of this graph, because that's what a topological sort does. So for the rest of this section, we need to talk about implementing these graphs and implementing topological sort. So we represent a type level graph as an adjacency list, taking this mapping type, which is from the type level sets package. And we're going to map nodes, which are types, to their in edges and out edges, which are lists of types. As a result, we also get some nice type families like get in edges and get out edges that get these in and out edges for us. This is really cool for reasons that will come up in a couple slides' time. Now we have to take a brief detour before we can talk through our implementations, because like in the Haskell paper, we use first-class type families by Chia. First-class families is a really cool trick for making type families partially applied, because regular type families are not allowed to be partially applied until unsaturated type families becomes more prevalent anyway. I'm very much looking forward to unsaturated type families. It's going to be great. These partially applied type families are simulated through data constructors, which can be partially applied. So for example, we have this non-empty intersect data constructor, which takes a list of kind k to a list of kind k to an x bool. We'll get to exp in just a second. And then to define how that family is executed, we define a type instance eval for this. So we're saying if we get a type non-empty intersects x is y, good news. This is how you implement. This is how you execute it and get a result out. So we should now talk about exp briefly. As was mentioned in the Haskell talk, exp is basically a trick to make sure that the type checker doesn't hate us. Data constructors can't have non-star kind as their return type, which is really irritating because there are lots of type families that we use which don't have kind star return types. So stuff like filter, for example, which would give us a list of kind k, we couldn't represent that as a data constructor. So exp is a neat trick that allows us to do that, even though, there's not an end to that sentence. Exp is a nice trick that allows us to do that. To avoid having to then keep unpacking and repacking this type, we fortunately get a type level monad with this reverse bind operator and pure specialized to exp. So to briefly go through this example, we've got not, null, filter, and flip, which are all defined by first class families and make this code significantly more readable. And because each one gives an exp k out, so for example, this filter, which checks each element of y's to see whether it's an element of, to see whether it's in x's, gives an exp k, and then we use this bind to unpack that and then apply it to null, same to apply it to not, and then eval the whole thing to get the result, which is a really lovely trick that's allowed for a lot of reusable code, and we'll hopefully show that properly in use in the next two examples. So now we can build our adjacency list and get one step closer to having this type level graph. I've grayed out most of the code because it's not super important, but the stuff that is important is colored and in bold and very, very clear, hopefully. So all we do is map this get adjacent function to each node, and this just makes a key value pair, one of those mappings from earlier, from that node to all the nodes that satisfy the comparator and all of the nodes that satisfy the reverse of the comparator. So that's getting you all of the out edges, those that satisfy the comparator, and all of the in edges, those that satisfy the reverse of the comparator. We then implement depth first search on this type level adjacency list. Again, I've grayed out some of the code because there's a lot of code on here. Key points to mention are, we're just going to go through this key subroutine. Unbool is essentially if, but in reverse. So it's the false case, the true case, and then the condition, which makes sense purely because the reverse bind means that all of our code basically reads in reverse, which is a bit weird. But that's just something you get in exchange for all of the benefits that first-class families give you. So if we've not encountered a node yet, we're going to apply a search strategy to get a list of nodes. This is where our get in edges and get out edges functions from earlier type families, from earlier apply. So instead of just having one DFS, we essentially have multiple DFSs based on how you explore the graph. So this could be getting all of the in edges or getting all the out edges or whatever, but we get them and then just apply DFS to each of those. And then because it's a post-order traversal, we're going to update the stack with the node that we were exploring in the first place, which is great. We now have this useful modular implementation. And we use this useful modular implementation to implement a bunch of cool graph algorithms that allow us to implement both what we wanted to, both the topological sort and a couple of other bits from the paper. So topological sort is just applications of DFS get out edges, your regular standard DFS. Connected component search, which we use in the paper to find groups of computations that can be run concurrently, is just applications of DFS get edges, which are the undirected edges. And then finally, DFS on the graph transpose, which we use for Kosaraju's strongly connected component search, again in the paper, is just DFS with the in edges. So you get all of these algorithms at the type level for significantly cheaper than you would if you wrote them with normal type families and didn't have any of the modularity that we got. So with this, we're now one step closer to having our goal. We've successfully, what we have here is the ordered type family, which just combines the adjacency list building and the topological sort from earlier. We apply it to our comparator is less than, and that means that if we get in this list of computations of type X's, like we did at the start of this section, we can apply this type family to get a sorted version of that at compile time called X's prime. The final challenge we now need to talk about is getting the result of this topological sort, so getting a value of type X's prime, or H-list X's prime, sorry, back down to the value level. And that's what we're going to do in this final section. So we're going to, well, let's just get straight into it. When we have the result of a type level algorithm, there tends to be two possible approaches when reifying. First of all, if a type has a single associated value, you can just use that value. So for example, the unit type, good news, it's unit. Similarly, those type level strings we encountered, while they're not types, you can get a single value out of them. However, we're not working with types like that. We're working with this MIO reads writes A, which is slightly more complicated. There are many possible implementations. You can have if you just have like something that reads from X and writes to Y, you could just have something that reads it and directly writes that value. You could add one to it. You could do lots of different things. So we're unable to do that. The alternative is that you can re-implement this type level algorithm at the value level, which is not ideal. It means we're taking all the hard work we've done and having to repeat it. If we then went, oh, I want to change this analysis slightly, then yeah, bad news, you're going to have to rewrite it again at the value level, which is a serious pain. So what we propose is a little technique called rearrangement, which uses the values we started with to inform what values we get in the output. So here's the idea. We want a generic way to permute an input into an output. This is exactly what a sort does, right? We have a collection of values, and then we've sorted them into some new ordered collection, but they contain the same values. As such, what we assume is that the values of elements in the output are the same as those in the input, but reordered. So if we see an element of type int in the input, and actually that's meant to be somewhere else in the output, it'll still be the same int. So therefore, to reify an element of our output list, we're going to look up the first unused value of its type in the input list. So to give a very small example of what that actually means, let's say I've got this amazing list of type int bool unit, and I do some type level algorithm that goes, actually, this should be of type bool unit int. Then it's just a game of looking things up. We look up the first bool that we find, it's true. We look up the first unit we find, and we look up the first int we find, and we successfully get a rearrangement that successfully, or we've now got a value of the correct type, and we've done that sort at the compile time. So it's just a case of quickly doing this lookup at runtime to get this sort to be completed. And we apply this exact same idea to the larger computations that we made. A very brief bit about implementation. I'm only going to show the class here and not the instances. The instances are available in the paper and they're fully explained, and that's much more useful than me talking you through lines of code right now, especially looking at the time. So we implement this as a class rearrange_del, which takes in some input list type, and it gives us both the target list, which is like the type that you wanted out of it, and whatever elements were unused, which allows it to be used not just for sorts, but also for filters and other similar cases where the elements in the input should be the same as the elements of the output, or at least a subset of them. Now we can see this in use. With this rearrangement, we can now just say, okay, so we had this x's, and we did some type level sort to find an x's prime. We know how to rearrange these. So if we are able to produce a rearrangement for x's to x's prime, leaving no elements left unused, so it's a full permutation as opposed to like taking some elements, then we can just use this rdel function we just defined. And with that, we've successfully taken a problem with some dependency. We've successfully taken our computations, which have these read and write types. We've looked at the type level how to solve this, and then we've brought that back to the run level, to runtime. So, in conclusions, we use a graded monad to make the types of our computations, so those I/O unit types that mutate state, more precise. So we now have these cool read and write types that effectively go, look, there we go, we can read and write now. We then use type level programming to look for dependencies between those computations, and we used we use a dependency graph at the type level to order them such that the programmer doesn't have to worry about it at all. And then finally, we used these rearrangements to take the results of this type level computation and bring it back to the value level for free. And with this, we can guarantee that our computations run in an order that satisfies those dependencies. And this is the cool new trick that we get. In the paper, there's some other fun stuff, like I mentioned earlier about running things concurrently. There's also some stuff about running partial updates, where if you know that a cell hasn't been updated, how many of your computations do you actually need to run? But for that, I recommend you check out the paper. So yeah, thank you very much.
All right, let's thank this. I will thank the speaker again. So we have 4 questions lined up. I'll take them to the stage one by one. Yeah, 4 questions.
Oh my goodness.
So the first question is by Chris Smith. I expected plus to subtract the first write set from the second read set, since there is no external data dependency when you read something you've just written. Would this be sound?
Supposed to subtract the first write set from the second read set. As in set subtraction.
Maybe I'll invite
if that's
him
okay
to the stage, and then he can clarify a bit.
Yes, please. That'd be fantastic. Hello. Sorry for the confusion.
Yeah, no problem. I was just wondering. I expected, like, if I say like write to the screen and then immediately read directly back from it, and then I combine those 2 operations with a bind, I feel like I get an operation which should not necessarily depend on previous writes to the screen.
Oh, yeah, that's a really good. Yeah, I think that would be sound. So that would be, to confirm, you have some operation which reads from this. If you bound together the 2 computations in the robot example, do you mean?
Right.
I'm just going to bring it up just for clarity. So if you were to bind remove error and write to motor together, you would have disk to motor rather than disk screen to screen motor.
Well, I think you'd still need screen as a written.
Oh, yes, sorry.
Yes. Right.
I think it would still be sound. I would have to check. So that would be not reading from screen because you write to it. Yeah, I think that would be sound. I'm not going to make any sweeping statements at the end of a talk, but I think you're correct. That's a really good point. Thank you.
Great. I'll remove the invitee from the stage, and Mark has answered.
Fantastic.
And now I'm going to show the next question. What happens if the graph is cyclical?
Okay. Well, fortunately, we have
screen or write motor.
Yeah. We don't get an infinite recursion or a loop because we actively check for this. So in the paper, rather than just using topological sort, we actually use strongly connected component search and then check if any of the components are greater than size 1. Because if you have a component greater than size 1, you have a cycle. And as you said, if we didn't check for that, we would probably get some kind of infinite loop in GHC, which isn't ideal. So we actively error. There's some really nice error messages that say, hey, these computations of these types are all in a cycle. You should probably fix that. But yes, we've fortunately thought of that. That is a really good question, nonetheless.
Great. I'll mark that as answered. And there are 3 more questions. So Gergo Erdi says, the Chesco talk showed quite a lot of performance problems. What's your experience with GHC's type-level computation performance for these graph traversal algorithms?
That's a really good question, particularly because one of the reviewers brought this up and I didn't get time to properly investigate it. But from anecdotal evidence, from just compiling on my laptop, which is a fairly new laptop, it's like 16 gig RAM, yeah, something like that. We didn't get any memory overloads. We didn't test any particularly big graphs. I think the largest graph in the paper is something like 8 nodes and a collection of computations between them. So admittedly, it hasn't been like seriously tested like Chescal was. But from my experience, it was taking maybe 30 seconds on some of the worst compiles. So it really wasn't super bad, but proper investigation needs to be done. As I say, that's very, very anecdotal as opposed to formally tested.
Thanks. I'll mark it as answered. And then Dominic Orchard asks whether you can make a pull request for the rearrangements to the type level set package.
Yeah, sure. That sounds really sensible. Yeah, I'll do that. I will screenshot that because otherwise I will forget. Lovely. That sounds like good fun. I'll do that.
Answer.
I really like that package, by the way. It's really clear and helpful. So thank you for that, Dominic.
And then a question by Andreas Klebinger. Have you thought about or tried staging as an alternative for compile time computations? I wonder if these kinds of type level computations is better or worse in terms of ergonomics, compile, and runtime.
Staging. What's staging here? As in, like, actually, yeah. If you could clarify, that'd be really useful. Sorry, I'm not too familiar.
I'll pull him in.
Brilliant.
You mean like template?
Oh, like template Haskell. Oh, okay. Yes. We haven't thought about that. I was thinking about this morning, funnily enough, because that might be a way to avoid the rearrangement step by saying, oh, why do we do this rearrangement when we could just ask template Haskell to order it for us after we do a type level computation? So it hasn't been explored, but it's a good idea. And I think it'd be really cool to investigate. Sorry to pull you in when I realized what was going on.
No, that's fine. Well, I guess as a kind of follow-up, right? Just generally, when I did type-level programming, I didn't do a whole lot. But term-level programming in Haskell at least seems more ergonomic. And I imagine with template Haskell, you can just basically lift this up to compile time and just say, run this at compile time instead of having to reformulate it at the type level. And so, and you obviously, right, you went at the type level. So I wondered, like, I imagine there's a reason. I know there's cross-compilations issues and similar things like that with template Haskell. So maybe you have some ideas or opinions on when should you go to the type level instead of going towards staging?
Simply put, I don't. Like, the main reason I went for type level stuff is because it seemed like a sensible solution. I didn't really think of template Haskell when implementing this in the first place. I would really like to try it with template Haskell because, as you say, it would be much more ergonomic. A big part of why we use first-class families is to bring that type-level language closer to the value-level language by introducing partial type families, which give us all the higher-order functions that we really enjoy. So it would be really sensible to go and explore that because, as you say, it is much more ergonomic, and I don't know what it would lead to in terms of performance. It would probably lead to some nice runtime performance benefits because instead of having to perform this rearrangement, you would just sequence it like we did on the first slide, except in the correct, guaranteed to be in the correct order. So I guess this is a nice case study for using graded monads with type level programming, but whether it is the absolute best approach, particularly for this example, I'm not too sure.
Okay, thank you.
Thank you. That's a really lovely question.
Kindly removing you from the stage, and then Mark, your question is answered. And the other one was, of course, answered as well. So I think this brings us to the end of the session. Thank you very much, Finbar, for giving the presentation and answering our questions. Well done.
Yep. Brilliant. Thank you. Oh, I can stop presenting now, can't I? And then probably get kicked off the stage.
And you get kicked off the stage.
Oh, no.
There you go. All right. After all these interesting, intriguing, inspiring, and amusing talks, I have one boring talk left, and that's my own. And that's the program chair report. Hold on while I open it. Right, so you should be able to see the slide. Holler if you don't. Okay, so, well, my name is Jurgen Haag, of course. I was the chair this year of the Haskell Symposium, and this is my short report, and then we can all have either dinner or do something fun. So, in case you weren't there when I did this at the first, welcome to the 2021 Haskell Symposium that, as you probably all know, is co-located with the Virtual ISFP 2021 and is sponsored by ACM SIGPlan. Some details about the submission process. So actually this year there were 5 paper categories, and I think I want to tell a little bit about these because it might inspire you to submit papers next year. So we have the research papers, the regular paper as they are called. They are 12 pages, double column style. And actually most accepted papers this year are of this kind. And these basically describe research that involves Haskell to a large extent. There's functional pearls, actually, the talk by Jamie Willis and Nicholas Wu. That was actually a functional pearl. They typically discuss something that is relatively well known, but in a way that is either very understandable or particularly elegant, or in this case also maybe particularly amusing. This year there was also a new category called a tutorial. There were no submissions in this category, but I actually hope that people will actually start doing this. The idea there is that you explain in a more didactically responsible fashion some aspect of Haskell. And this, for example, may also include how to use particularly complicated or useful libraries. Again, you can use 12 pages there. A 4th category is experience report, where people can describe their experiences of applying Haskell, for example, in industry. And then finally, there are demo proposals where there's a tool you made in Haskell that you would like to demonstrate during the symposium. Well, everything is formatted in ACM SIGPlan double column, and maybe some of you will complain, well, why isn't this the same format that we use for ICFP? So I can immediately send off my rejected ICFP paper to the Haskell Symposium. Well, this is simply because we're not allowed to. They insist on using the PAC and PL style only for those conferences. The submission process was lightweight double-blind, which basically means you can submit your paper, but try to avoid, it's the idea that you do not have specific references to yourself and to your work in there. But I mean, for example, you are allowed to give presentations while we are reviewing your work. That's fine. So some submission statistics. Haskell Symposium has 2 rounds. So there was an early round where we had 8 submissions. And then afterwards, a few months later, I think a few weeks later, we had a regular round where we had 2 resubmissions from the early round plus 40 new submissions. So the idea of the early round is, especially if you're not very experienced in writing papers, the idea is that you submit to the early round, that you get a first round of feedback from the reviewers. If you resubmit it in the second round, you get the same set of reviewers back. And then hopefully, the idea is that you fix the problems that they have seen and then increase your chances of being accepted. Where do all these submissions come from? Well, I've listed based on email addresses what I think are all the countries that these papers were submitted from. Most of these are indeed in Europe, but we also have USA, Japan, and Brazil. The number of submissions was actually relatively low. So in earlier years, there were more. Why this is, I have no clue. Could be Corona, could be the fact that we have to do this online instead of in the flesh. It could also be a lack of maybe publication or advertising. So what about acceptance and rejection? Because this was submitted. In the early round, there were 8 papers submitted, like I just said. Only one of them was accepted at the time, and all the other 7 were allowed to resubmit to the regular round. There were 2 papers submitted then from the resubmission. Only one of these made it, but this is already 50%. This is way better than the 1 out of 8 in the early round. Out of the remaining 14 papers that were submitted for the first time, 9 made it. So this means a total of 10 papers. And like I said earlier, one of these was a functional Perl, the other one were research articles. All papers got 3 reviews, as usual, at least 3 reviews. There was no shepherding. Basically, with Haskell Symposium, there is no time for shepherding. That's also why it actually makes sense to use this early round as a form of shepherding. One thing I really liked is that in the end, we had 6 papers that got an artifacts available stamp. So this is actually when you go to the paper in ACM portal, it actually says, well, this is an artifact available. This is different from, for example, ICFP and Popl, where these artifacts are also tried and compared with the content of the paper, etc. It's just that there is something available, but it doesn't necessarily mean that it has been checked by any of us. There's no formal process yet at Haskell Symposium to do that. Okay, so I move on to the 2 invited talks, of which we've already seen one. Both of these are about linear Haskell, but then from 2 different perspectives. This is an experiment on our part, or my part maybe. Mathieu gave an excellent talk already about, let's say, the professional side of why do they need linear Haskell and so forth, and specifically within Tweak. And tomorrow, Jean-Philippe Bernardi from Gothenburg will give a talk about a more technical talk about how this linear Haskell all works and its integration in DHC. I hope to see you all there as well, of course. Some food for thought, maybe for myself. At first I thought, well, the 2 rounds don't really help very much in the sense that there weren't that many resubmissions, but it is the case that out of the 2 papers that were resubmitted, then 1 was accepted. I think quite a number of the papers that were rejected in the early round could have been improved to make acceptable papers, but for various reasons, I guess the author decided not to do this. What was a bit disappointing is that I saw only Perls and regular papers. I would hope that there would be more things like tutorials and demos. There have been demos before, and generally the submissions were low. Is that a Corona effect or something else? I really don't know. So what about symposium participation? Of course, I don't know how many people have registered. There's no real thing as registering in this case for a particular symposium. What I did do is I kept track of how the audience developed on YouTube and inside AirMeet. I think the highest I've seen is a total of 97 participants looking on during the invited talk. And generally, I think there were about 65, 70 people attending. I think this is really, really good. And I have to thank you all for being here and sticking around. Next year's chair, I think the only thing I can say at this point is to keep an eye out on the Haskell Symposium website. There's a lot of thank yous I have to make here, of course, to the Haskell Symposium Steering Committee for advising me on various things, the PC members and Oliver Westphal to do all the review work. Hannelie Tavante has been an excellent help for use of AirMeet, and also the ISFP workshop chairs, Zoe and Leonidas helped me a lot. And I guess I want to stress from the Haskell Symposium Steering Committee, Richard Eisenberg, for stepping in when all of a sudden my AirPods didn't seem to work anymore. All the authors for submitting their work, and I guess all of you for attending. And then the only thing I can say right now is this: I hope I can see you back tomorrow for yet another day of Haskell. Goodbye. So with this, I'm going to end the session. You can still go to the lounge. I think the chairs, the tables are still reserved for us there, I assume, in case you want to continue talking about the papers or just have a chat over whatever else you want to. See you tomorrow. Welcome all. I hope you can all hear me. Good, thanks, Joachim. I'm waiting for Hannelie to send me the YouTube link. It seems that yesterday on YouTube, 100 people were additionally following the talk, the invited talk. Thanks, Yamin. Yeah. There goes. Open the meeting. All right. Good to go. Let's see. Match your buttons here. Our first speaker has arrived. Hi, Natchapan.
Hello. I hope you can hear me well.
Yes, I can hear you. I can see you.
I can just go ahead and share already.
So you can share your screen if you want.
Entire screen, share. And there we go.
Great. I will wait for a few minutes for people to drop in, but please your setup.
Yeah. It looks to be doing okay.
John has come over to the light side again. So I gave some participation numbers yesterday. I think at the top we were 74 people in AirMeet, and I thought we were about 23 or so in YouTube. But according to Hannelie, actually there were 100 people watching in YouTube the invited talk of yesterday. That is maximum. Which I think is very good. We're still working on making talks public after the symposium has taken place. But that's a bit more complicated in our case because we only have a live stream. We don't have pre-recorded videos.
It was quite convenient to not have to record videos.
Yeah, I thought so too. But
I mean, sure, there's a risk, but it's better than.
There are actually a few pre-recorded videos for people that did this just in case.
Yeah. Recording takes an awful lot of time because it's hard to excuse yourself for the little mistakes that you make.
Yes, exactly. Yeah, or you have to do it as this. There was one talk at ICFP who had programmed his entire talk. So it was spoken by a robot voice, a female robot voice. This was Manuel Serrano. He had programmed it with his own JavaScript compiler. Wow. And the nice thing is that, yeah, she doesn't make mistakes. And he said it took him less time than actually having to prepare it by hand. And everything, of course, is completely synchronized with the text on the slides because it's completely programmed. The text and the slides are completely programmed in his case.
Right.
As one whole. I do think it's a bit harder to keep your attention with such a voice. Like. All right, it is now 1 o'clock, but let's give latecomers a bit of time to 1 minute or so, and then we really have to start. I will quickly make Richard co-host. Just in case things go wrong again with the sound on my side. Welcome, Richard Burke, and thanks, Richard, and thanks again for helping out in case of disasters.
Yeah, no problem.
So we're a healthy 46 already. So I think we should just get started. People can hop in. Welcome everybody to the second day of the Haskell Symposium. The first talk, there will be 3 talks, then we have a break, then there's the invited talk by Jean-Philippe Bernardi on linear Haskell yet again, but now more from a technical scientific perspective. And afterwards there were 2 more talks, including one on linear Haskell, so you might as well call this the linear Haskell Symposium, I guess. But we start off today with Natyapan Baliapan. And I would say, okay, take it away.
Yeah, thank you. All right, so let me get started. All right, so you should be able to see my slides now. So welcome. This is a talk essentially about normalization for EDSLs, and this is joint work with Alejandro Russo, Sam Lindley, and I'm the other guy there. So like I said, this is a talk about EDSLs, right? So it's important that we take the perspective of an EDSL designer and put on our EDSL designer hats. So let us all do that. Right. So what we're looking at here is an EDSL, which takes the form of a deep embedding, right? And it's implemented using a data type, an expression data type. And here we have ways to insert integer literals. We have ways to add and multiply integer expressions. And most importantly, there's a variable constructor, which allows us to insert unknowns or free variables into this language, right? So this is important to the story. Just take note of that, right? Okay, so here's what we're going to do. So we're EDSL designers. We would like to extend this EDSL with arrays, right? So by arrays, I just mean like immutable full arrays as we know them. So, since we're dealing with deep embedding, we may go about them by extending our expression language with a few constructors, which denote the array operations we're interested in. So here we're going to add a way to construct new arrays, to compute the length of an array, and to index into an array. What the new array constructor takes, you compute the length of an array, you give it the length of an array, and a function which computes the elements or gives you the elements of the array, and you get an expression of an array type, a standard deep embedding way of going about things. Using this, you can derive a map array combinator using the standard array operations, which has the length of the original array, and you apply the function by indexing into the array. So this is a nice derived combinator, but it lacks properties of fusion, right? So if you consecutive map arrays are not fused, because all you're doing is simply building syntax, so it's a little too much to expect fusion to happen out of the box. So in such cases, typically one resorts to a form of shallow embedding, where instead of extending your expression language with the necessary syntax, you say, oh, well, I can implement a notion of arrays in Haskell. Let me implement that in Haskell and piggyback on Haskell's way to deal with arrays to program arrays in my EDSL. How do you do that? Well, here's a data type similar to the new array constructor before, which takes an argument which denotes the length and a function as before and returns an array. And you can implement the array operations as before. Before they were constructors, now there are Haskell functions. also has the same signature, but notice that the result, the types of the arguments are similar, but notice that the result is an array of an expression. That is an array containing an expression of type A, as opposed to an expression of an array type, right? So this is what I'm going to use to denote shallow embedding. And similarly, you can implement length of an array and index of an array by projecting out the arguments to the constructor, right? Once again, you can implement a map array using these functions, which, for the shallow embedding combinators, essentially. And here, unlike the previous case, you have fusion properties. Well, intuitively, all that's happening here is that we're leveraging Haskell's execution mechanism to achieve fusion in our shallow embedded arrays, right? And one can also observe this by essentially sort of inlining these functions, doing a bit of equation reasoning, and by observing that the left and the right-hand side are equal, and that there's no unnecessary intermediate arrays created, which is all I mean by fusion here. Right, okay, but we've lost something in the process. There's no longer a syntactic representation of this array operation, right? So that was nice because we could generate code for array operation before, but now we cannot do them anymore because they're just Haskell functions. So, it's quite common to sort of retain the benefits of both by combining these representations by having a way of going back and forth, right? So you have 2exp, which takes a shallow embedding, spits out the deep, and then you have from exp, which goes backwards. And you also have a requirement that, composing them in this fashion as here must be equal to the identity. Now, using this sort of juggling back and forth, you can implement a combined embedding combinator, if you will, of a map array, which essentially, it takes the given array expression, converts it to the semantics first, applies mapping in the semantics, so it leverages fusion in the semantics, and then converts it finally back into syntax, right? So what's neat about this map array, however, is that you now have fusion in the syntax, right? That's quite neat because you didn't actually do any rewriting or any syntactic manipulation. Everything's was achieved in the semantics, and you managed to reify it back into syntax. This is quite nice, and it works really well, for example, for pairs of expressions and also for functions on expressions. So it's a rather neat trick, but it fails, however, for more complicated types which have multiple introduction forms. For example, integers or sums or exceptions. And why is that? Well, this is because it fails when you try to go back from a deep embedding to a shallow embedding. Well, this is because of unknowns, right? And why is that? So let's say I give you a variable x of the type exp int, and I say, give me a shallow embedding representation, an integer, from this variable. How are we going to do that? There's multiple choices, so we cannot quite go back. So at this point, one may think, oh, well, but maybe the choice of shallow embedding is a problem. Can we sort of refine this shallow embedding and, somehow sort of keep track of how we can keep track of the expressions with unknowns in the semantics and somehow get away with that as well? You may as well. It may be possible to get away with it. But now the problem is we can no longer pretend that the shallow embedding is a sort of a natural semantic interpretation of the type that we're interested in, right? So we cannot reuse the host language features out of the box. You can't use addition and multiplication on integers as it is out of the box on your new semantic interpretation, for example. And also it's a bit mixed up, you're mixing up syntax and semantics, and it's a little bit difficult to reason about what exactly is going on. How do you prove the story correct? How do you know that the compiler, the EDSL compiler that you're writing, produces this semantically equivalent programs in spite of the fusion and the optimization that we're interested in? This is where it gets a bit complicated. But the main idea, the answer to this is essentially the essence of this paper, is to say, well, normalization by evaluation, or NBE, provides a principled account of specializing expression syntax by leveraging their semantics, right? And the key, so normalization by evaluation is a well-known technique, but the key here is the shift in perspective from deep embedding to syntax and from shallow embedding to semantics, right? And so that's essentially the idea that we're going to work with in the rest of this talk. Okay, so now when I say normalization, typically, at least in my mind, something like this comes up, right? I'm thinking, oh, well, you have some expressions, you're normalizing things, which is essentially by rewriting the syntax, and you end up in some kind of a specialized expression, which we're going to call normal forms. This is the traditional way of normalizing things. But NBE, on the other hand, has a deep involvement of semantics, right? So you start off with syntax, as always, and then you evaluate them into a suitable semantic domain, where you do the hard work by leveraging Haskell's or some other host language's evaluation mechanism, and then you reify the semantic value back into syntax, just as we did in the shallow embedding, deep embedding combination, and the result would be a specialized expression in normal form. NBE is a very similar story in that sense. It's just a more structured account of the story. Right, so the toolkit we're going to be dealing with, right? So here's a frame. By toolkit, I just mean a framework that we can instantiate and implement for our EDSLs. So here's a type class RF or reifiable, and there's a type family which allows you to define a semantic domain which interprets the object language type that we're dealing with. But it's not just any semantic domain we're interested in. We want some additional structure on this domain, and this structure are these two operations, reify and reflect. Reify essentially takes a semantic value and converts it to a normal form, which is just a specialized expression. And reflect is NBE's solution, essentially, it's NBE's answer to deal with expressions with unknowns in them, right? And these expressions are also called as neutrals, are inductively characterized by a different data type called E. And reflect, the job of reflex is to insert these expressions with unknowns into the semantic domain defined by the type family. So the other major component is once we've identified the suitable semantic domain, we have to write an evaluator or an interpreter which takes these expressions, evaluates them into the semantic domain. And then finally, once you've done that, you have a normalization function simply by composing eval and reify. So you evaluate and then you reify and you end up with in a normal form just by observing the signatures, type signatures of these functions here. Right, so let's kind of take this framework for a spin and see, what it feels like in some sense. So let's look at integers, which are a bit of the problematic situation before. And for this purpose of this talk, let's just consider two simple equations that we're interested in. Those are that if we add two literals, we want the addition of those two literals, we want the result to be a literal, and if we multiply two literals, we want the multiplication to be literal as well. We want our normalizer to apply these equations whenever possible, and that's essentially what I mean by equations for NBE. And once we've identified those equations, it's the next natural thing to do here is to essentially look at define neutrals, right? So like I said, neutrals are essentially expressions with unknowns in them. But let's try to inductively characterize them. A variable is clearly an unknown. We cannot determine the value of it. But also you can have an addition where the first argument is unknown. So then, okay, you allow the first argument to be an unknown. You can have an addition where the second operand or the second argument is an unknown, or maybe both of them are unknown, right? So we don't know. It could be, for example, x plus y. In that case, that you would use the NAD constructor. And similarly, you would define constructors for multiplication as well. So the key idea here is neutrals inductively characterize what it means for expressions to be stuck at unknowns. That's the key thing about neutrals. But once we've identified them, then it's time to start thinking about what is the result that we want the normalizer to produce. Well, in our simple case, all we're saying is that we want the result of specializing an expression of an integer type to be an integer literal, fully evaluated, or a neutral, which means you couldn't quite do everything, but just as much as well as you could do is what a neutral represents. So it's only one of these two possible values. And that's what a normal form reflects using the nup and nlift constructors. And once you've defined normal forms, then the semantic domain can just kind of shows up in some sense, right? So because it just resembles the normal forms. And the semantic domain is defined similarly, where we say, well, we interpret integers as either expressions with unknowns in them, or neutrals of type integer, or their integer values, meaning fully specialized. And of course, we must also implement reify and reflect. Reify replaces the left injection by nup, which is essentially taking the neutral and inserting it into normal forms. And reify replaces the right injection by nlift, which is just a literal and normal form. Reflection, on the other hand, is just the left injection here. Remember, reflect inserts the neutral into semantics, and that's what the left injection does according to our semantic definition here. So that's the instantiation of the type class. What remains for us to do is to implement the evaluator for addition and multiplication. And the way we do that is we define a semantic addition function, which takes two semantic integers, and it returns a semantic integer. Now, a semantic integer is basically is of the either type, which means you can pattern match on it, and you can get a left or right injection. And if both of them happen to be right injections, meaning they're literals, well, you can perform the addition that you're interested in. But if one of them is stuck, which meaning stuck at some unknown and you don't know what to do with it, you just build up a neutral and you reflect it into the semantics, right? Because you don't know what to do with it, you're just going to sort of say, oh, okay, I'm stuck, so here you go. Just reflect this back into the semantics. And we do the same thing for multiplication as well by pattern matching and all the possible combinations, and either performing the appropriate semantic action or reflecting the constructed neutral back into the semantics. I say back, but I just mean into the semantics. So that completes the entire story. And as a result, what we have is a normalizer which applies those two equations for NBE, for integer expressions. And so just to give you another taste for, just to sort of tie it back to what we started off with, which was arrays. So so for arrays, we identify the equations as the following. That is, if we have an array expression, it can be uniquely identified by an equivalent expression, which is sort of the eta expanded version, which says any array expression must be of the form new r, with the length of the original array and which indexes into the array. So this is the eta. The first line denotes the eta rule, and the second two lines, the latter lines essentially denote the beta or the computational rules. So if you compute the length of a new array, which is just as good as projecting out the second argument, and the index of a new array as good as projecting out the second argument, the latter case it was the first argument. So once we've identified the equations, typically we would do the same. There's a recipe here, right? We would identify the neutrals and identify the normal forms, and then sort of do the semantic domain. So I'm going to skip ahead to the semantic domain directly, and only to show you that it resembles shallow embedding, because once again we have a semantic domain which is defined by a data type, which accepts a semantic integer in place of an expression of an integer type, and a function which gives you the elements of the array as before, and it returns a semantic array. New array, length array, index array, as in the case of shallow embedding, are implemented exactly the same way. You use the constructor to construct them, and you project out the arguments in case of the other functions, right? And once you have the semantic operations, all you have to do is sort of fill in the rest of the story. Well, we instantiate the type class so we interpret arrays by this new semantic array that we've defined. Reify essentially, does a bit of juggling between semantics and syntax. So it takes a semantic array, it constructs a syntactic array in normal form, and reflection receives a syntactic neutral. So essentially, it constructs a semantic array. It can be filled out. It's just a bit of sort of recursive application of things. Not a lot of intellectual complexity there, if you will. And then the last bit is, of course, to implement evaluation. And for evaluation, well, we've already defined in the previous slide, we had identified new array, length array, and index array operations in the semantics. So we just use them to interpret the things in the syntax. And that once again completes NBE, but now for arrays. And so it's kind of systematic how we're going about doing these things, which is the nice thing about NBE. So you can also do this for the other types, for other more pure types, for functions, products, sum types. But you can also do this for computational effects, which is quite interesting, which means you can normalize effectful computations for exceptions and state effects. So the case for sums is a little bit complicated, so because it sort of messes with the other instances, it sort of pervades the implementation. But there's a more detailed account of how you can solve these problems, which arises due to the unruly eliminator of sum types in the paper, and how they sort of interact with effects in certain ways, and how you can go about solving them. That's in the paper. But instead of going through the full details of these instances, I'd much rather show you what it is that we get out of defining these instances at the end. What kind of examples, what kind of programs do we get at the end of the day? Right. So we're back to map fusion. But now I want to show you an example of a fusion in the presence of some kind of a pattern matching or branching in a program. So in this case, what we're essentially doing is we have a program which receives two arguments. One is of the either type and one is an array type. I'm going to call the first one a scrutiny and the second one an array. And what we're going to return essentially is an array, which is computed by the result of mapping with +1 or add 1 here. And all the things in blue here just deep embedded combinators. Now we're only dealing with deep embedding, so that's the only kind of combinator that we're going to program with. And the array argument to this map R over here is defined by pattern matching on the scrutiny argument. And on one branch you have another map operation, on the other branch you just have an array. The only thing that I'm trying to point out here, there's an opportunity for fusion on the first branch because there's two map operations, but on the second branch you must preserve the original map. So it's a slightly non-trivial interaction of how fusion should be done. And what you would expect, the result is also kind of expected. When you normalize this program, GHCI, what you get is a result. So let me walk you through the result. Essentially, this represents a function, the internal representation of this function, which is basically it receives two arguments and returns a single new array, which has the length of the original array, which was given as an argument, and the body of the array is computed by pattern matching. So essentially what's happened is that the case statement has been delayed to the point of absolute necessity. And on one branch, you can notice that it's the original array incremented with x and +1, which is basically the fusion of these two map operations, add 1 and add x. And in the second branch, you can notice that there's only a +1, and that's because of the original map has been preserved in the second one. So essentially, all the maps have been computed. There are no intermediate arrays. Notice that in the result, there's only one array which is being created. So that's kind of the result we get out of fusing array operations here. So that's nice, but you can also do a similar story for effects. So what you can do is, for example, in this program, you have an expression it's of a function type, which takes an array expression and it returns a stateful computation. Now let's look at this. It takes an array and then it says it's maps over the array with a +2, puts it, maps over to +1, puts that, and then gets the result and then returns the head of the array in the state. So, but the thing that we should notice here, there are two subsequent or two consecutive put operations. Clearly, the second one overwrites the first, so the first one can be thrown away, a put fusion. And then the get after the put is kind of useless because you know exactly what the state is, which is the array incremented with the 1. So this intermediate array is also a little bit useless. So we're trying to get rid of these in the result and by minimizing the put and the gets in the result. We normalize this program and we get one get and one put. So the put operation here, you can see, is basically stores a new array where the array has been incremented, the values of the original array have been incremented by +1, which is expected because you want to throw away the first put. And what you return is essentially the result of what you had, the head of the result of what you had stored incremented by 1, which is the same as the head of the original array incremented by 1. And that's what you return. There is an unnecessary get here, but this is kind of the consequence of eta expansion, which is the next bit that I want to get into. Because at this point, you may also be wondering, what is so practical about this story? There's this blog post I think that Derek Dreyer has about any paper which has practical in its title is probably trying a little too hard. If I'm being honest, I think it's kind of true. We are trying a little bit hard, but that's only because NB is a good idea. I think ADSL developers, such as myself, should use it because it kind of gives you a nice refined account of what's going on. But really, by practical, what we mean here is that the standard approaches to NBE can lead to unnecessary expansions, as EJA expansion, because typically they're used in different, more theoretical contexts. At least typed NBE is used for things like equality checking and so on. So you want to adapt things a little bit for our purposes. So to illustrate the problem, let me show you this example. So let's say I normalize a variable array, which is of the type exp array of integers, right? And if I normalize this variable, what's going to happen is that I'm going to get an eta expanded form, which basically says, oh, well, the result of this normal form is a new array, which with the length is that of the original array and the index of, index into the original array, which is a bit wasteful because if you normalize a variable, all you want is it's a variable, right? You don't want anything else to be done. And so, of course, you can solve this. That's kind of one of the things that I'm getting to is you can do this by augmenting the semantics with a normal form, which doesn't, with a normal form, which represents reduced expressions which are not eta expanded. This is essentially, reflects a technique called gluing. So what we're doing here is we're gluing the semantics with the syntactic component so that what happens during interpretation, we can sort of carefully build a piece of syntax that we would find we like without actually leaving reification to the mercy of the semantics and having to reconstruct things, from scratch by eta expansion. As you can see here, reify is a lot simpler now. You just sort of you project out the normal form, leaving all the work to the evaluation. So during evaluation, you will have to take care of this, which can be done if you do it the right way for defining normal forms. So of course, there's a lot more that I would like to tell you about, but it's all in the paper. So there's concerns about normalization, right? Because normalization causes duplication. We don't want that. So how do you? So there's a little story about how can you retain explicit sharing in the sort of semantic normalization process. How can you disable sharing, disable normalization on sub-expressions using a save combinator? There's concerns about, well, case expressions can explode. How do you optimize them? And sometimes you obviously want richer arithmetic equations. The equations that I showed you were very simplistic. You want, for example, to say that 0 plus x is equal to x. You want to say multiplication distributes over addition and so on. There's a number of other equations that one would like. This can also be found. And often you want to add domain-specific primitives that you don't really want to do much about, uninterpreted constants, such as fix, right? So because if you start normalizing fix, you're never going to terminate. So there are recipes to do this in the paper that you can have a look at if you'd like. So in a nutshell, here's essentially what I'm trying to say, sort of conclude things up, is that NDE provides a principled alternative two techniques that combine deep and shallow embedding for building and specializing EDSLs. There's a strong resemblance between both of these, but I think NBE is a more systematic way of going about things. But what's also nice is the NBE implementations are very modular. If you remember, our type class instances, they don't interfere with each other, and you can implement normalization for one, not for the other type, and so on. So you still have fine-grained control over the extent of specialization that you're interested in. Well, that brings me to the end of this talk. And if you'd like, well, obviously there's a paper on this matter, but you can also look at the GitHub link if you'd like to have a look at the code. Thanks.
Great, thank you very much. So there's a number of questions, and I will show the questions one by one on stage. The first is from Jesper Cox. Couldn't you just pick semint equals nfint?
Yes, you can.
Directly.
Sorry, maybe I was too quick. Yes, you can do that. The only reason to do that is because we want to sort of not, I mean, of course, it's more concise to do that directly, but I think this is basically to illustrate a point for, when you have sums, you start messing with the semantics a little bit more fine-grained way, but perhaps a more simpler answer that I'm trying to give away is that I still want to keep what's the syntax and semantics separate unless where it's absolutely necessary. If you put nfint, it just looks like a blob and you don't really know what it contains. And nfint could be defined as anything. I hope that.
Thanks a lot. I'll mark that as answered. The next one is by Gergo Erdi. NA2 can make progress given an exp into int. Why is it a neutral element?
NA2 can give, right. So this is because right. So in the equations that I had picked, this wasn't supported. So it's because I had showed very simplistic equations. So in the actual implementation, if one can have a look at the code, so there's a slightly more sophisticated implementation where you actually get to deal with this, where you have a partial application and you want to specialize with respect to that. So it's only because of the equation that I've chosen for this presentation.
Marked it as answered. And then we have another question by Andrew Hirsch. Is there a reason for the choice of expint instead of semint in the semantics of arrays?
Yeah, that's just to avoid unnecessary. It could have been semint. That's a good spot. I mean, the question is, why is there a exp int on the function? I mean, that's because it's in a negative position. You can avoid some unnecessary work by making it exp int, but it could have been semint. It doesn't matter so much.
Okay, thanks. And then the final question at this point, at least, maybe other people get inspired to ask a few more questions. So Youssef Svenningsson asks, semantic domains can get very complicated. Do you have a story for making sure that they don't leak to the end user of the DSL so that they don't need to be confused by them?
Absolutely. So what's brilliant about the story is all of this is the compiler developer's problem, right? Because so the only thing that is exposed to the EDSL developer is the deep embedding. So of course, now we're saying, put everything into the expression syntax. So all you're going to do is construct the expression syntax. So the only complexity we're leaking, if you can call it that even, is how to construct ASTs. But no, the NBE story, regardless of whether it exists or it doesn't exist, none of that is carried over except for the restriction on the types, right? I mean, this is quite common for EDSLs to have sort of this type class restricting the type of the expression. So that's the only thing which kind of leaks. But apart from that, no, nothing else.
All right, thanks a lot. I'm gonna mark that as answered. Any other questions, or maybe some of the? Oh wait a minute. I missed a few. John is asking a question as well. Is x times 0 neutral? If so, does that interact nicely with MBE, or do you effectively turn into a sum type as far as MBE is concerned?
So in the simplistic equations I showed, yes, x times 0 is a neutral, but of course that's a bit annoying. Like it's why would you want to generate code for x times 0? So in the sort of the claim I made about richer arithmetic equations, this equation is included as well. And no, this is a regex. It's not a neutral in the more sophisticated implementation. And so you have a choice depending on what equations you want. But for the latter, if so, does that interact nicely with NBE, or do you effectively turn int into a sum type? as far as NB is concerned. I'm missing something. I don't exactly follow the second part of the question, but maybe.
All right.
Yeah.
What I will do, I will invite John to the stage, and then he can maybe specify more precisely what he means.
Yeah, that would be nice. Thank you.
I hope he's still there.
Well, but maybe I can quickly answer that. We don't do any turning int into a sum type. So maybe that answers the question already. We don't do that.
There's John.
Hello. Yes, so I was just wondering if you distinguish the zero case from the non-zero case, does that effectively mean that you end up needing continuations as you do with when you have case expressions and sum types in NBE, or is everything just simple?
No, so it is a bit simpler. Yes, you need a structure like and we don't exactly use equivalent to the continuation, but there's a similar story. I don't know if that answers that.
Sorry, John, I muted you because I got feedback from your mic. But maybe you have to unmute it and then tell us whether you're satisfied or not.
Yeah.
I lost the sound, I'm afraid, but it's my setup, I think, which is causing the feedback. So just let's go on.
Okay. Mark has answered, remove you from the stage. And then we go to the final question, because I think we have only time for the final question here. Youssef has another question for us. Do you have a story for incorporating heuristic optimizations as well, like a limited form of inlining or loop unrolling?
Right. So in the paper, there's something to do with, so there's a feed-based, sort of fuel-based, primitive recursion, essentially. So there is a recursion story there, where you can control the amount of recursion because it's explicitly provided. Because you can do that, I can imagine that you can, I have no idea how this would be proved correct, but I can imagine implementing something in Haskell where you unroll a recursion combinator a certain number of times and you stop, because you do that already with a primitive recursion combinator. So yes, I haven't done it, but I can imagine. Yes, so I think that's your answer.
Okay. Well, let's thank the speaker again for his talk and answers. And I'm going to kindly uninvite him from the stage. And then I'll look for the second speaker. Hashan. Yeah, so Hashan is there. So now we'll look for the third speaker. And there he is, Gertjan Botu.
Hi.
Hi.
Let me just try and share my screen.
Yes. So Gertjan will be playing a pre-recorded video. So you're not seeing him now directly, but the video. And let's wait a bit. Maybe people will come in specifically for your talk, and then we're already started. Maybe you want to start just to have a trial run, Gertjan, just to see how it sounds.
Yeah, let's give it a shot. Welcome everyone to this Haskell Symposium talk. I'm just going to start off today with a simple coding exercise.
Okay, so I'm not sure how it is for you, but I think everybody should maybe increase their volume a bit.
I can maybe put it a bit louder.
Or maybe you can put it a bit louder. Maybe that's also a possibility, yeah.
Let's see if that works better. Welcome everyone to this Haskell Symposium talk. I'm just going to start off today with a simple coding exercise.
It's audible, but
defining a function.
Yep. So people say it's fine. So it's almost time. So maybe we should just officially start now. So the final talk of this session is by Gert-Jan Botu, who is a co-author of the paper with Richard Eisenberg. It's called Sequence Stability by Being Lazy and Shallow. Lazy and shallow instantiation is user-friendly. Okay, go ahead.
Okay, thanks for the introduction. Welcome everyone to this Haskell Symposium.
Gert-Jan, your sound is going, yeah.
Okay, that's a slight issue. How can I fix this?
Well, don't mute yourself, but I guess you didn't mute yourself, did you?
I really muted the microphone, but like the physical microphone. that might not be a great way of sharing my sound.
Okay, but what if you start playing again now? Now that
it's the only way. That's not a great way, is it? Well, I can just put a mic in front of the speaker, but that's...
Okay, would it be acceptable that I play the one that is in the system? Or is it really... Are there big changes?
Sure. Let's go for that, if that works better.
Yes? Okay. So what the rest... okay. So what you others maybe do not know is that there is a version of this talk inside AirMe. But there were some changes, so we tried to play the other one. So maybe you have to unshare.
Yeah.
And then I can see if this works.
This Haskell Symposium talk. I'm just...
Right, so in this case, I think I'm in charge. So I'll be starting the video now.
I'm going to start off today with a simple coding exercise.
Let me know
I'll
if
be
it works.
defining a function, let's call it tuple, with the following type. So we wanted to have type for all AA, for all BB, and then a tuple of A and B. The implementation of this function should be fairly straightforward, as we'll just take two arguments and place them in a tuple. Like this. Now, later on in my program, I want to define a second function with a new name. Let's call it my tuple, but with the same behavior. So I'll just define it as a synonym for the existing function. So later on, when I use this function, for example, in the main, I want to do so as follows. So I want to call my tuple, and I'll pass in a first argument, let's say 5. And then I want to specify that the second argument needs to be a Boolean. And I'll do this using visible type applications as follows. I'll then just pass in a second argument, for example, true, so that I can print the outcome. Now you can already see that my editor is complaining about this. And in fact, when I load this program in GCI, it'll give me a type error saying that I can't use type applications here. Though if I load the same program in GHC9, then it compiles just fine. So clearly, when going from GHC8 to GHC9, steps have already been taken to improve this behavior. Though it turns out that this behavior is still quite fragile and somewhat hard to predict. So for example, if I just do something silly like eta expanding this definition, which really shouldn't make a difference, and I reload the file, well, then suddenly it breaks again and we get the same type error we had before. So the question I'd like to answer today is, can we further improve upon this situation when going to GHC10? And in order to help me answer this question, let me just call my nearest tweak consultant.
Hello.
Hi, Richard. I have a question for you. So I have a couple of examples where both GHC8 and GHC9 show somewhat fragile and hard to predict behavior. And I was wondering whether we could fix this when going to GHC10.
Well, these issues are very interesting, and it's quite a bit more subtle than you might think. So let's take, for example, the identity function. So we can have this id function, as we see here, of type for all a arrow a. But when we use that, it has to be made concrete. At some point, when we say, for example, id of true, we have to instantiate this polytype with, or this a with bool, giving us the type bool arrow bool. And so there's a lot of flexibility in how we design this feature. For example, if we have myid equals id, well, we might instantiate eagerly. I haven't passed any arguments to id here, but I could say that instead of having this polytype with for all a, I could instantiate this with a unification variable. So here I'm writing that as u1, and it's essentially a type variable that we don't know what it stands for yet. We can almost think of it as just sort of a hole in the type that as we continue to do type inference, we might fill in. In this case, type inference doesn't tell us anything more. We don't learn anything more about u1. So when we're inferring the type of myid, well, we're just going to take this unconstrained variable, generalize over it, and then get another polytype. The difference is in this new polytype, we see that there's these little braces around the a. That marks the a in the last polytype written here as an inferred variable. Right? We don't actually use inferred variables for visible type application because maybe there's many of them and we can't really predict the order that they occur in. So with eager instantiation, that's what I'm describing here, where as soon as we see id, we actually instantiate it to a unification variable right away. We're going to get this type at the bottom here for myid. On the other hand, we could have lazy instantiation. So in lazy instantiation, we see id, and then we don't instantiate. And so that means that we can actually infer a type for myid that still has the exact same type as id has, and that means that now myid can be a drop-in replacement in all scenarios for id. GHC has moved around in this space a little bit. So GHC7 used eager instantiation. Then to accommodate visible type application, GHC8 uses lazy instantiation. But we see here in the image that the GHC8 icon isn't all the way over on the lazy side. And that's because some practical concerns still compel us to use eager instantiation in certain places. A key place where eager instantiation is still used is that right before we generalize the type, the inferred type of a definition, we instantiate it first. And this gives us a slightly more predictable type inference and slightly easier to understand type inferred types. But the fundamental action of the type checking algorithm in GHC8 is lazy. In GHC9, we went back to eager because that seemed like a simplification over this sort of mixed economy that we use in GHC8. But it turns out that eager versus lazy isn't the only issue at hand. And your tup and my tup example
actually that's not really about eager and lazy. That's instead about deep versus shallow. So here we have our tube type up on the screen. And if I instantiate this tube type deeply, what that means is I take all quantified variables, even after arrows, and instantiate all of them. So in this case, that means that when I instantiate tube, I'm going to instantiate both A and B. GHC8 does deep instantiation. GHC9 does shallow instantiation. So we've already also flip-flopped on this. Here in tube, we see that when we do deep instantiation, then we affect both of the variables here. On the other hand, in this version, this is what GHC9 does. This is shallow, which means that as soon as we see an arrow, we're going to stop instantiating. And so in this case, you see on the bottom here that we've only instantiated the first variable A. We have not instantiated B yet. So this is actually why we see the difference in behavior between GHC8 and GHC9 that you demonstrated at the beginning. That's because in GHC8 we do deep instantiation, meaning that this B variable ended up being instantiated, then regeneralized in the type of my tube, so man, we couldn't use it with visible type application. GHC9 only instantiates the A, meaning that this B variable is still around in my tube. In this diagram, we see now not only do we have eager and lazy going left to right, but we have deep and shallow going bottom to top. So GHC7 was both deep and eager. There's ways that we can observe deep in GHC7, although eager is harder to observe because we don't have visible type application there. GHC8, as I explained before, is both lazy and a little bit eager in some situations, but it's always deep. GHC9 is always eager, but now it's shallow. And so a big question is, what's best? Do we want to use which spot in this or which quadrant in this axis, in this set of axes do we want to use? And we seem to be having a hard time figuring it out. All of these are sound, but what's best for users? Makes me wonder, should we organize a user study? What do you think?
Thanks for that interesting discussion. So, while I would like to do a big user study, I'm a bit worried that organizing a big user study with 4 different versions of GHC would get quite expensive and quite hard to organize fast. So I'm wondering, could we try to approximate this result using a more formal method? And that's the second question that we're trying to answer today. How can we approximate evaluating a user-facing design decision, but using a more formal method of evaluation? And we're going to be tackling this using the concept of stability. So with this we mean that making small innocuous changes or program transformations to the code should not have a major impact on the meaning of the code. And we're going to start doing this by constructing a small list of program transformations or properties that we want our compiler to satisfy. And the first one of these properties is, for example, that let inlining should be type preserving. So, for example, if we have a function or a value bar that uses another definition foo, well then inlining the second definition should not alter the type of bar. And the reverse should hold as well. Extracting some implementation from bar into a second definition should not alter the type of bar. Furthermore, let inlining and let extraction should not influence the runtime outcome of this function. So with that I mean that if we evaluate bar, then the outcome or the value should remain the same in both cases. Looking at another example, if we duplicate an equation in a function definition, while being a bit silly, this should never alter the type of this function. And let's have a look at one more property. Eta expanding a function definition, like foo in this case, which has a function type, well then that should not change the type of foo either. Now we've enumerated all these properties in this table, and the next step is to evaluate our different forms of type instantiation against these 5 properties. And we're going to do so as follows. So the first step is to formalize our type system family. And with that we mean that we're going to formalize our type system, but parameterized over the form of type instantiation. So if later on we instantiate our type system family with a specific form of instantiation, well then we should get one of the 4 type systems as we discussed earlier. Next up, we need to formalize the different transformations or properties that we expect our compiler to satisfy. Some of these we've seen before, but the paper introduces a number of additional properties as well. And then finally, we need to evaluate all of our different properties against our type system family. Now you can find the full proofs along with a set of counterexamples in the paper, but the outcome looks as follows. So we conclude that our recommendation for GHC 10 is lazy shallow instantiation. It preserves most, though not all of our different properties, but this makes it the most stable form of type instantiation. Again, you can find the full discussion along with additional properties and a full set of counterexamples in the paper. And this neatly brings us to the title of this talk. We hope you enjoyed the talk and will be available afterwards for any questions or further discussion on this topic. So I can't hear Jurian yet. So
yes, we've lost audio from Jurian again.
Right. Can you give an example of the one property that is not preserved by lazy shallow instantiation? So the reason why I wanted to share the video myself is that the table was a bit wrong in the version that we saw before. So I can say the properties that are not preserved by lazy shallow is, for example, the multi-equation property that we showed in the talk. So basically, if you duplicate a definition, you can hear Jurian again. If you duplicate this definition, then at some point you will have to instantiate the type, and the type will change, even though you're in lazy instantiation.
Does audio work again?
Yes.
Yes.
So now I've uncovered why it didn't work. Thanks a lot. There's another question by Alexander Dikelski. Can you talk a bit more about the counterexamples in the paper?
Right, that is a very open question. So in the paper we have about 11 properties, and for 10 of them we have counterexamples for specific systems of instantiation. Are you asking for a very specific counterexample? So in the paper, first of all, we do the proofs, and then we show that in some cases the proofs just don't go through. And then we try to find a very simple counterexample to show this in a real world or a slightly artificial example, why this doesn't work.
Right, so I've invited Alexander to the stage. Maybe he can give a bit more details.
Yeah, that was what I meant. I was just curious, like, what their kind of example is too, I guess. But yeah, that makes sense.
Okay, thanks.
Okay, so I can remove you again? Okay. Yes. This is answered. Are there any new questions? Not yet. So I may have a question then. How is this all related with the impredicative instantiation and the recent changes to GHC?
Right, that was basically one of the things that kicked off this work. So because GHC made these changes, we started wondering, like, is this the right way to go? And how can we motivate that this is the right way to go? And maybe there are other choices to be made in type instantiation that do actually have an impact for the end user. And how should we then evaluate this? And that's when it kind of started rolling, and we started figuring out examples like, look, maybe this is better, or well, then that breaks this other example. And that's how we started doing this work. Exactly.
Thanks. So there's another 2 more questions already. So Artem Penetchin asks, did you really consider a user study today with GHC up? It's not hard to switch between versions of GHC.
Right, we did actually consider a user study, and the point of this work is not to replace user studies. It really is supposed to be an additional tool of evaluating these decisions in a different way. For example, in this scenario, switching versions of GHC is not the hard part. The hard part is implementing 4 different versions of GHC. And this definitely can't fully replace a user study, but it is an approximation of the result without having to do this implementation work and just finding these many experienced Haskell programmers.
Thank you. There's a question from Yanis. I'll show on stage. Could you have done your stability checking not by trying to do the proofs, but really via automatic testing, like random programs, fuzzing, etc.?
To be honest, that was not something we considered, but it's an interesting idea, but then we kind of run into the same problem where we would have to implement these 4 versions of GHC to test against. But I do think it's an interesting idea to have at least some version of more applied study in there.
Okay. Oh, many more questions coming. Martin's one has answered, and then Yanis has a follow-up question. Okay, he says he realized something, but that's not really a question, I guess. But on the other hand, Adam Gunnery has a question. Is there a plan to move GHC towards lazy and shallow instantiation? E.g., are you planning a GHC proposal or an implementation? That's interesting.
That is a great question. So the idea of the paper was to spark the discussion and to introduce a number of arguments. I am not directly planning on doing this implementation, but it would be interesting to see how the community takes this work and evaluates these decisions. I'd be happy to help with the proposal in any case.
Okay, thanks. And then Matthew Flouet has a question. Is it that difficult, or is it maybe wrong to have the deep, shallow, lazy, eager as user visible compiler options or directives? Since it's only type inference, there seems to be no problem with mixing them between different modules.
That's a good question. I have to think about this. I'm not entirely sure if this would break anything. So I would, in my eyes, I think it would be possible, yes. But I'm not entirely sure. Don't quote me on that.
So I can imagine it might make GHC much more complicated also with maybe future changes. Do you envision this happening?
Yeah, that's certainly an aspect of it. So having all these different versions would add complication. Whether it really breaks something, I'm not sure. But it's a very interesting question in any case.
I can imagine if you have a new feature, you have to consider with 4 combinations of running the compiler to see whether everything still works. So
yeah.
Nice question. Okay, I'm going to mark this as answered. Do we have any more? The list is empty, but we've had 6. So that's a good number. If not, then I think we can thank the speakers again for their interactive recording and answering our questions. So this brings us to the end of the session, and we have a break. And then at the end of that break, we'll have a new session with our invited speaker, Jean-Philippe Bernardi, who will be talking about linear Haskell. I hope to see you all there. Of course, there's the lounge. You can go back. You can go back to when I turn on the take a break. You can go to the lounge. There's a few tables reserved for the Haskell Symposium, so if you want to talk to people there, go ahead. Yeah.
Hello.
Yeah, you hear me?
I can hear you with poor quality.
Poor quality. Okay.
It's getting better now. Yeah.
Okay. Yeah, my AirPods gave up, and then it takes a bit of getting the system to recognize it again. But, all right, you're ready, I hope?
Yeah, I'm ready. Can you see my screen?
I can see your screen. I can hear you.
Very good.
I can see the slides. Yeah. And you shared the entire screen. Yeah.
Yeah. This is on purpose. I'm planning to do minor demo.
Good. I can also turn on my screen. See your code. Hi, Richard.
Hi. I can hear sort of like a weird kind of heartbeat sound coming from someone.
Me too. Me too. I'm not sure where that comes from.
Maybe it's because my mic is on my chest.
I don't think so. No, I don't think it's an actual heartbeat. I think it's some
No.
sort of digital fragment of some sort.
Yeah.
Okay. Well, maybe it's due to the silence.
I'll mute myself to see if it.
No, I can still hear it. I think it's coming somehow from Jean-Philippe's setup. There may not be anything to do about it. It's not so bad.
No, I don't think I can do anything about it. In fact, I could try to improve it, but it might just make everything worse. I think this is what it should be. I think when I start talking, it will be better because the system picks up on silence.
So before you start, Jean-Philippe, I have a small announcement to make to people here. So Rudy Matela suggested that maybe you've looked at the final session of today. There are 3 slots. 2 of the slots are taken up by research papers, and I had to kind of allocate the 3rd slot. Otherwise, the speakers thought they had 45 minutes. So this is like a bogus slot. And now Rudy Matera suggested that we could do lightning talks in that particular final slot. So if you want to take advantage of that and spend 5, maybe 10 minutes on something related to Haskell, then you can send me a message and I'll see if what we can fit in. So that's all the announcements I want to make. Yeah, so send me a message privately through AirMeet. Well, without further ado, I'm going to announce the invited speaker for today. So yesterday we already had a large piece of linear Haskell, and you're gonna get another dose today. But now from Jean-Philippe Bernardi from the University of Gothenburg, who'll be talking about linear Haskell today and tomorrow. Go ahead.
Thanks for the introduction. Yes, indeed. So that seems to be the year of linear types in Haskell. I have planned this. So I'm first going to talk about, do a summary of what you can do today with GHC, with the linear types as implemented. And the second part will be about what I think could be the future, hopefully to inspire future research or discourage, maybe. We'll see. Hopefully inspire. Okay, so before we get into all that, let's just remind a little bit in a few words what linear types are about. So I'm sure all of you are familiar with the regular arrow type. So this type declaration here expresses that f is a function that produces b, or a value of type b, using a value of type a. And you have the linear arrow, which is written so traditionally with a circle. And this only adds an annotation about quantities. So to get out 1b, f consumes 1 or exactly 1. You could, here by 1 I mean exactly 1, 1a. So f produces exactly 1b using exactly 1a, and that's all there is to it. You can stop listening now. So no, joking aside, let's see what GHC can do today. So perhaps some of you haven't haven't had the chance to experiment with GHC9, which has linear types. So a quick demo. So you can use so the non-Unicode. I'm activating Unicode syntax because the non-Unicode syntax is pretty poor, as you can see down here, in my opinion, anyway. So we can declare the identity function, and well, I'm sure everyone is familiar with the identity function, and because it actually produces one output using one input, it can be assigned a linear type, and so here it is. So GHC checks the type here, and you can extract the type, and GHC pre-prints it like so. And this is another notation from the linear O. And here, this is the number of times that this argument is being used. And in this case, it's 1. It can also be written in all letters with the capital O. That's a type, essentially. Okay, and so does GHC actually checks that? Well, here you go. So if we examine here what GHC says about this forget function, if I attempt to not use X, GHC will come with this kind of error. So it says, you try to use X many times, whereas you declare it to be 1 time. And many really means any time, any number of time or whatever, or something like that. But the identifier any was already used, so implementers have resorted to many. So let's fix all errors. I could write X, but that's not the right type. And likewise, you cannot duplicate. So if you declare that you're going to use X exactly once, you cannot produce the results which where X appears 2 times. So that's also a check by the compiler. But let's fix the error maybe like this. This is no longer the duplicate function, so let's delete that. And so in sum, exactly once is a special case of many. So really, whatever, any number of times. So in particular, every linear function is also your good old function. So we can convert a linear function into a good old function. And here I'm also using the Unicode syntax. So here it is, the implementation is as simple as you can imagine. Well, actually, if you try to do this, it's not going to work. So there is no subtyping between this and that, but there is implicit conversion between the multiplicities here and that. Okay. And the other thing doesn't work. So any old function is not a linear function. So that's also an error. This I told you earlier. If you want to force this many multiplicity in a data type, you can by just using the linear arrow, the non-linear arrow, sorry. So here it is. So this UR is pronounced unrestricted. So unrestricted A, well, this is how you put this A in a box so that even in a linear context, you will have an unrestricted number of A's there. So that means that unrestricted times A linearly to B. So exactly one unrestricted A, that's the same thing or isomorphic to the good old usual arrow. So here is the conversion in one direction, we just wrap, and the conversion in the other direction, we unwrap. Okay, here I was a little bit lazy. So exercise, do the projection from here. Okay, so what about branches? Well, so it seems that here you have to write X 1 time to satisfy the type checker. So you have to do the same in every branch in reality. So so if we try to do this doesn't work because in the false branch we are not using X. I can also just not write this branch at all, and then we just have a warning. Well, the usual warning that we didn't define the branch. So this may be surprising. Linearity seems not to be checked. Well, this is a normal thing. So in Haskell, you can always satisfy the type checker by crashing. So this is the same with linear types. So this is only linear types give you only a static property And so be careful not to introduce magical properties to linear types. These are just types, nothing more. Okay, let's see now. Oops, here is the talk. Here are the slides. And so, okay, let's address immediately the elephant in the room. There had been other functional languages with uniqueness types, like clean, etc., and a lot of research on it. So why didn't we use that? Why did we go for this? And well, the answer is, as far as I can see anyway, Haskell is very much inspired by this Curie-Howard connection. So there is a correspondence between Haskell and second-order intuitionistic logic. And so our idea was, well, let's just draw on this correspondence and transport whatever exists in linear logic, and we're going to obtain linear Haskell. So as far as I can see, this is the principled way. I would argue the most principled way to go about this problem. And this way we can get a lot of research that we can apply. Not everything, maybe, because there are lots of variants of linear logic, but hopefully a lot. Okay, so, but then can you really do unique values with linear types? Okay, well, let's try to convince ourselves that this is possible. So this is in the original, the 2018 paper on linear Haskell. Okay, I redefine everything here. So this is the new thing. So how do you make a new unique object? So here is the design pattern. So we want to make a unique object here, and the way to do that is to use a sort of a double negation system here, where this arrow is linear. And so inside the continuation here, you're going to be given a single copy. And the reason why this is the right way to go is the continuation returns an unrestricted amount of A. And so it doesn't matter if this is called, if we need one A or if we need many A's, whatever, we are going to always get many A's. And so this means that to the continuation, it's always valid to give a single copy. And this single copy is going to be to remain a single copy as long as every function in the API that manipulates these objects preserves the quantity. So, for example, you have this type of signatures when you produce one object using another object, but well, it could be any other type as long as the quantity of objects are preserved. Notice, by the way, that the pairs are linear as well when you activate linear types. So that would be a quantity preserving function here. So let's go back to what we. Okay. All right. So what else do we have? Okay. So a big question is, if you introduce linear types, aren't you going to have a problem, because many functions can be either linear or unrestricted. So that means that you will have to create a different version of all these functions, and because these functions can be used by other functions, you're going to get a combinatorial explosion. Well, this is a legitimate concern, and we addressed it in linear Haskell by polymorphism. Okay, the usual answer to every problem in type system. Okay, so let's see how this plays out. So, okay, I'm hiding usual map function, so I can redefine it. So this is how it would be defined naively in Haskell. I mean, it's a correct implementation, but GHC does other tricks that we don't really care about here. So empty list becomes empty list. The cons becomes a recursive call in the tail and apply F in the head. Very well. And so we see that the linearity of the list here is preserved. So every element is used exactly once to produce exactly one result. So we can also, keeping the exact same code here, we can give it a linear type. Okay. So if the input function is linear, then the output function is linear as well. So, okay, so how we said polymorphism should do the trick. So how does it look like? Well, there it is. So here is the polymorphic list map function. So we quantify not only over the types A and B, but also on the multiplicity, which I call P here. So this means that this generalizes these two functions by generalizing on this arrow and on that arrow. And so here is what you get. This is how it reads. So to produce exactly one B, you need P times A. And well, this is the reading of this particular type. And the reading of this arrow is to produce exactly one list of B, you need P times the list of A. And the definition remains the same. Oops. And in particular, you're getting instantiation like so. And here it's implicit. So like type application usually don't have that. So this is nice. And well, okay, so this is, I became lazy here and I didn't. This is the same as this. Okay, there you go. It loads. Just to let you know, this is live GHC. So if I put here this, you can see that the GHC actually checks multiplicities. This works today. Okay. So here we are. So that works. Very good. So in sum, you have it. It works. And what can we do with that? Matthew gave us yesterday an overview of high-level things we could do, and these are actually addressed in this 2019 paper. So we develop unique references, like I've shown earlier, but well, developed in a lot more detail, and bindings for foreign stateful APIs, which is what Mathieu was most concerned about yesterday. In case you missed the talk, I think it should be available somewhere on the conference website. So come back to these 4 details, or even better, read the paper. Well, if you have more time, you can read the paper. And well, this year we have more contributions in the Haskell Symposium. So both of these papers give us more applications. So in particular, session types. In fact, session types with priorities will be presented in a few minutes. This is the next talk. And after that, we will talk about symmetric monoidal categories. So I'm not going to get into details here, but everything that you can do in a symmetric monoidal category, you can represent it using a nice lambda function in linear Haskell. And so all this you can do today. It will be type checked and multiplicities will be checked, and so you will have this nice sense of safety that things work and are safe by construction. Another thing which is very important, I'm going to start with this. So the implementation effort, even though I'm giving the talk, the implementation effort wasn't, I didn't take part in this. We have to thank, Arnaud led the implementation effort, and a lot of work, probably even more work was done by Christophe and Mathieu. And so, already in GHC 0.0, so released all sets of packages compiled with it, so go ahead and use it. And if you're wondering how to, if you don't want to redefine, let's say, linear maps, etc., the linear version of the map function, check out the linear base, which is an extension or a replacement for the, well, let's say just a base library for linear types. So all that is available for you right now. Okay, so that was it for this part. A little interlude. So let's come back to, so that I can explain to you research directions which I envision. Let's come back to the seminal paper, why functional programming matters. And so I don't think I make a big mistake if I paraphrase it this way. So John Hughes is arguing that in Haskell, so in any functional programming language with the lazy evaluation, the composition G after F is a powerful thing. And the main reason for this is because the glue is powerful. And as far as I can see, when you read the argumentation, the glue is really this type B in between here, which is very powerful. So let's say in Haskell, and John Hughes uses this example extensively. What if you have a list of something, doesn't matter what, I want alpha here. If you have a list there, well, I mean, this is nice because this kind of, this composition kind of behaves like a conveyor belt. So you can have here a function which is in charge of making a series of approximation of a numerical function. So you get more and more precise results as F runs. And here in G, you're going to, let's say, filter these approximations, find one which is sufficiently close to the result that you like. So you have more ways to structure your programs. And this is thanks to restriction in the language, which makes composition always safe and easy to understand. Okay. There is, though, a slight problem with this picture. So a lot of examples use this case where these well, not the arrows, in fact, but rather the circles, they are like pipes. So in the sense that whatever comes in, comes out. A lot of examples are like this. But it turns out that, of course, this is completely wrong because the function G can use its arguments any number of times. Let's imagine G uses its argument 2 times. Well, then you have 2 possible implementations for the composition. Either you run F 2 times, so you get well, you get your 2 copies of B by running F twice, or you run F, you make a copy. Okay, so you run F and then you save the result, and then like this you can use it twice. And so you have two different kinds of behavior. And depending on whatever the compiler decided to do, you're going to get different runtime behavior. And this makes it very hard to reason about performance. I think in terms of the previous talk, this is unstable, so even. So if you make a small change, you can switch to one behavior to the other without realizing it. And well, that makes it, this is a big part, I think, of why Haskell has this reputation as surprising performance. And so, well, I mean, linear types restore the simple picture, right? Okay, so we get, if we extract 1C here, while we are sure that if this one is linear, we're sure you're going to get to need exactly 1B, and so then it becomes easy to reason about performance again, about runtime behavior in general. So I think, to me, if I had to sum up why linear types matter by direct reference to the seminal paper, I think this is how I would sum it up. So hopefully this is a nugget of information that you can remember. So there is just a little bit of a problem, is that I think even though, yes, the picture is restored, it's still hard to know if what's going to happen in reality, even in the presence of linear types. So the situation, from a practical point of view, there are lots of optimizations in GHC, and a lot of these optimizations depend on multiplicity of functions. And so the compiler today computes these multiplicities, but these analyses are only approximations, conservative approximations. And the reason why it's difficult to do is because of recursion and, well, maybe module boundaries and things like that. And so, the behavior of the program depends on this complex analysis, and so in consequence, the runtime behavior can be difficult to predict by the programmer, because they would have to, every time they make a change, to run in their head the analysis, and sometimes, well, this can fail. I mean, the programmer's reasoning can fail. So one possible path, one possible research direction, I think it would be to make sure that GHC has consistent predicate and predictable behavior by using these, by taking advantage of these linearity declarations. And also, well, I think all the other goodies are there in GHC, so I think this is ready for the taking. So this way, if all of this is done, then it means that the programmer can declare a linear type, and just this typing declaration would ensure more predictable behavior at one time. So I think this would be, this is not started. If you're interested, I think this is up for taking, if you think this is a meaningful idea. Now, second thing, improve the runtime behavior. So today, linear Haskell is just in the type system. And so for Mathieu, this is satisfying because, I mean, it's sufficient because, all these linear functions will resort to calls to the FFI, so it doesn't really matter what if the implementation is efficient or not. But but so this is linear Haskell is only in a type system, and so don't think that anything clever is done. So, for example, let's go back to our example here. So here I said, well, look here, this is going to be a unique object. And so if you implement this with FFI, that means that this one here can be implemented using the FFI by a mutable update or anything you like. However, if you implement this object type within Haskell, the runtime system is going to be exactly the same. So this is going to be allocated on the heap, maybe like this. Okay, so we have this. I made a trivial implementation here. The object type could be something like that. I mean, obviously that would be something more complex, but for the sake of the discussion. So that would create an object, and this object would be allocated on the heap today. Likewise, a function that manipulates the object here, well, it would behave exactly the same as before. Now this is just the identity function, so it doesn't matter, but you can imagine it can be anything, something a lot more complex. And so this will be allocated on the heap, and this will be implemented by allocating more closures on the heap, probably, in practice. Well, that seems a bit wasteful. So here, if the object type is abstract, so not exported by the module, the compiler could prove that unicity is preserved and could potentially provide more efficient implementations. So not using the garbage collected heap here, and this could be even an in-place update and things like that. So this could be done. And I think what's funny, or at least when I read Gerard's paper from 1986, where he proposes linear logic, I think he's already suggesting that this could be used for an efficient programming language. But we haven't done that, and we don't even have a clear plan yet. So this is, well, hopefully a topic of research for some of the people at the Haskell Symposium. Okay. Third thing. We have multiplicities. And multiplicities are, well, they exist already, and they are quite powerful on their own. So they form, well, they almost form a ring. So we have this one thing, we have a notion of multiplication, we have a notion of addition. And that seems that would seem only natural to complete the structure and add a zero identity element. And if you look at a lot of type systems, they are special cases of, let's call it linear Haskell, plus a zero and a notion of subtyping for multiplicities. So formally, this can be an order or semi-lattice on the multiplicities. And this gives a general notion of modalities that could be used for a lot of things. So seemingly with just a little bit more stuff, we could do at least all these things. So not just linear, but affine, relevant, type systems, so all kinds of substructural type systems. We could count things a lot more precisely, not just exactly once and whatever many, but maybe one, exactly 2, 1 or 2, 0, 1 or 2, 0 to 5, etc., etc. So that could be used very useful in certain contexts. So in fact, there is a lot of research that defines and takes advantage of such systems for practical purposes. These modalities or these multiplicities become modalities, can be used as capabilities, for example, for information flow security. Yesterday, there was a talk on graded monads. So instead of using an explicit monadic structure with the grade, you can use the multiplicity in arrows to represent the grade. So throwaway monads. In a lot of cases, you don't really need the monad. You just need a modality. So real numbers fit this structure. And so if you really want very precise quantities, for example, for differential privacy type systems, well, there you go. You could use that. There is a notion of irrelevance, which is important in dependency type programming. Well, Haskell is moving in this direction, so who knows? That can be very useful for irrelevant arguments. The zero modality can be used for that. And in reality, arbitrary effects can be associated with these modalities, in fact, co-effects. And so this is a very general, it becomes a very general device to express things within the type system. So this, I looked at it with Andreas Abel, and you can look at the paper ICFP last year. Titled Unified View of Modalities in Type Systems. So, and in some way, it's a small extension of linear Haskell. Okay, oops. Yeah, no. So, be careful. This is so in the paper we looked at the type system itself, but in practice, it's going to make type inference. Well, probably the programmer needs to add a lot of type annotations, and the problem is it's not clear. The design is not obvious, don't hold your breath for GHC. But I'd like to work on that. So, in conclusion, what I would say is this was a good choice, a good design, if I may say so myself, because multiplicities give you a lot for a relatively small cost. Okay? So yes, we had to change the arrow type in GHC, so that's, well, you can imagine that this touches a lot of places in the compiler, but even for a very mature system like GHC, it could be done. It passed all the roadblocks and it's within the compiler. So in some sense, this is already paid for you. And you can do a lot of things. So all these stateful APIs that Mathieu talked about yesterday, protocols, session types that we're going to see a bit later today, symmetric monoidal categories that comes afterwards. And I'm hoping that, so without touching the type system, but with, not more work on GHC, we could have just faster programs using just linear types. So what I mean by this is just change the type annotations and your programs become faster. More control on runtime behavior. This is partially today as well. Okay, if you declare a function linear, the user of the function will know better what the function does. And these more expressive types, well, this is what I mean by this. All these things that are in the literature, you can import them. Sometimes exactly, sometimes with a small difference. Okay. And I see I have like 5 minutes left, so I don't know if I should be interrupted, but I don't see any catastrophic thing. So I think what I'm going to do in these 5 minutes is to show you. So the next talk will be on quite complicated session types, but I want to show you how linear types help you do these protocols. So let's dive into some code a little bit. So in fact, you can do protocols today, so to speak. So if you have an ambient type of fx, which I call f here, a lot of times it will be just IO. You can represent a protocol which, let's say, so in this example, we take one query and there is a reply, and another query and a final reply before we stop. Well, you can do it like this, okay? So if you have a server that follows this protocol, we can write a program that uses it by, well, calling the server one time with the first query. I'll just call it Q1 here. And the server comes, you have to be not afraid of continuations. So if you're not afraid of continuations, you just use this. So the server comes back with the reply, R1, and a callback to continue the protocol. So we can maybe do some more things and then call back into the server, and we send the Q2, and the server comes back with the second reply, still in continuation passing style. And finally, we are we are done with this protocol, and we can continue doing whatever we want with these 2 replies that the server gets. Well, that's all well and good. The issue here is that this callback function could be called several times. And that would mean that the protocol has to be reentrant. So, or the server has to be reentrant. So every time you're in the middle of a conversation, you can either drop the conversation right there, or save this, save the point in the conversation you were, and come back to that point in the conversation. And this is usually not what it wants, even though sometimes it is. And so, well, how do linear types help? Well, I mean, let's just make sure that these continuations can be only called once. And so, okay, that's it. Maybe you don't see the difference even because it's so small. So let me try to line things up. If I may. Maybe I can. There you go. So if you look carefully on here, the points become a circle, and that's it. This is your linear, this is your Foreman session type right there. And so there is a slight difference here as well, that the continuation combinator cannot be just that. It has to be a little more complicated. Right, this. So I would say this is a rather small. Well, it's one way to get started with the session types or protocols that you can do today very simply, as long as you're comfortable with continuations. That gets you there. So I think this is another example of getting a lot for a small cost, even though I think in a few minutes we're going to have an example of a much more powerful library to do session types using still leveraging linear types. So stay tuned for that. And I think I'm done now. We'll relinquish.
All right. Thank you for your presentation.
Thanks a lot.
There were a number of questions already lined up for you, so I'm going to show them on stage and also, in this case, invite to the stage the person who asked the question. We have a bit more time in this case.
Oh, this is an excellent question. So I think it means
we have to read out the question because otherwise the YouTube people can't follow it. They can't see the question.
Ah.
So
do you want to do it, Toby?
Yeah, I think, can you pose the question?
I can pose the question.
Yeah, sure. There was an example of MK unique or make unique in the talk, and I wasn't sure why you need UR in the continuation.
Absolutely. So can I recover presentation mode? As long as the question is shown, apparently I cannot. I
don't think so. I'll remove the question from the stage. I can take this away, I think, and then you can reshare your screen and show the slide.
Yep. Okay, so here is the situation, and if I understood the question correctly, you're going to. It's just what if we had removed this thing here?
Exactly.
So what if we remove this thing here? Well, so in this case, the continuation produces just one A. And so that would be, of course, I mean, this is fine as a type, but now, if someone, there is a caller to MK unique itself, okay? And if the caller to MK unique needs just one A, then this type would be fine. We would only need one object. But it can happen that MK unique is called in a context where someone wants many A's, or a ton of A's. And if it needs a ton of A's, well, we need to call the continuation a ton of times to get a ton of A's, because the continuation produces only one A. So if we want a ton of A's from one object, then we have to put this box around it. Yeah, this is unrestricted. So we want a ton of A's, or an unknown. We want to be able to get an unknown number, and this is how it's done. Is this answering the question?
Yep. Thank you.
Okay. Thanks a lot for your question. In the implementation, are there any interesting, okay, I don't know if the questioner wants to ask the question themselves. I think, Jorian, you're muted, and the question is...
No, he cannot, he cannot be invited to the stage.
Okay, it's popping in and out of existence, so we can just read the question. Yeah. In the implementation, are there any interesting interactions between linear types and core transformations? For example, a need to ensure that a value doesn't get duplicated during optimization. Yes. So we need the core. I think the first thing to say is we need the core. So the core is the internal representations that GHC is using, and this should be linearly typed. Otherwise, we can make mistakes. And so I don't know if this was achieved 100%. I think 99.999 or something. But the core-to-core transformations had to be linearity preserving, were made to be linearity preserving during the course of the implementation. And I think this has even uncovered some bugs, or at least some, interestingly complicated design, let's say. I can't remember any of it from the top of my head, unfortunately. But the answer is yes. This should be answered by the implementation guys like Arno or Christoph.
Okay, so I marked this as answered, but there's another question by the same person who just wants to see this confirmed. So is there a way to express at most one's usage in the current implementation? His understanding this is no, but...
Well, I mean, so there is a way, but it's not very convenient. So if you quantify over a modality, this modality can represent anything you like, or if you quantify over a multiplicity, okay? So you say for all Q, and then you make sure that this Q is convertible to whatever you, well, if you have Q times alpha, you want it to be convertible to at most once. The thing is, this notion of at most once would have to be part of your API as well, because the native pattern matching, let's say, uses the notion of one time or things like this. And so, yeah, so you have to do the explicit conversions yourself. I think this would be the upshot there. So currently, no, and I mean yes, but it's extremely inconvenient. And so what you need is the extension that I talked about in the second part of the talk. That would be, so there you define the addition and the multiplication to mean what you want, and from there you can, you have what you have. This is called a fine type system, I think.
Okay, thanks. I don't see any other questions, so I think I'm at liberty to ask a question myself. So this relates back to, I think, what you just talked about. So when you talk about using linear types for optimization, then I think you would like to have affine types, wouldn't you? Because if I say I want to create something, and I know that if I know it is used exactly once, then that's fine, and the compiler could take advantage. But maybe it could also be used 0 times, and then I still would like to be able to say that doesn't change anything, at least not in terms of being able to destructively update the value, for example.
Well, it depends what kind of optimization you want, right? So some optimizations will want that, but let's say I think if you have linearity, this would help you trigger things like, you know, you don't even have to do a deallocation, for example, in certain cases. So both are useful.
Okay, so there's another question from Gergo. I'll show him on stage.
Could you have?
It's very difficult to read this out, I think.
Yeah, but I mean, the answer is yes. Yeah, I mean, yeah, I mean, this is so the question is, I think the question actually, so there are several ways to. Oh yeah, we have to read this for the YouTube people, right?
Yeah.
I don't think we can read that, so we have to do by hand. So again, if you give me the if you hide the question, I will
I will
explain.
hide, yeah, give you the screen back. You can share.
Okay, I have to remember to share. There we go. It's a little bit fuzzy. There you are. Okay. So the question is, can we have this? And there are several ways to understand this question. Is this a subtype of the actual dollar, which is something else? And I think the answer of that is no, it's not a subtype. Another question is, can you define this? Well, I think the answer to that is yes. If I define it correctly. There you go. So we can define it. And another, okay. Finally, another interpretation of the question is this a suitable implementation for what's below here? Well, let's give it a try. Okay, so we have errors due to this, but those are fine. And so the answer of that is yes. And finally, can we just use it directly here? And this I don't know, I will have to try. And I think the answer to that is yes. So I think that was all I could think about this question. Of course.
Maybe for myself,
yes.
Does that mean you cannot use $... to replace the old dollar? Is that?
Well, what is the old dollar? Well, we can. I mean, we can try in this context, and in this context, I think that will work. Yeah, that does definitely work in this context. The actual dollar is something which is
A to B to A to B.
This is, I think, what most people think. And in this case, I think that does not exactly work because it has to be expanded at least, and that works. So I think this, yeah, I actually misread that at first. But it's yeah, that works. So that would be the case. I think there is nowadays an extra special thing going on, and I think this extra special thing is about to be removed, if I remember correctly, in GHC. But yeah, I think now we have exhausted the question. Thanks to you.
Okay, I'll mark this as answered. I think this also answers, I think, the next question of Gergo, but let's check.
There is one raised hand. Oh no, he's raising his hand now, Gergo. But
right.
Maybe
so I'll just give him the mic and then he can clarify, and then we can conclude the session.
Yeah, so
Gergo,
I guess my real question is whether you could define a single dollar with the type from my previous question, and it seemed like after Urian's follow-up question, it seemed that the answer was yes. But then, of course, there's also the fact that dollar is wired into GHC, and there's all kinds of extra special magic going on to support basically higher rank applications of it, right? So that you can do run st dollar something. So, but I guess my question is whether all of that is orthogonal to the linear types work, and whether all that would just work if we changed dollar to be that single multiplicity polymorphic version.
I mean, I would love to tell you just yes, right, for everything. So the extra special thing for run st is about to go away, if I understand the state of the
I think 9.2 it will be gone, so there's no special hack anymore for dollar.
Okay, and then when it comes to I mean, there is a practical question: is in certain cases, maybe this isn't going to be, you know, like maybe the P won't be inferable, and that's going to be annoying for the programmer. And this is very hard to tell you, like, on the spot.
Okay, I guess all of this was just motivated with just me not liking the worth of having to have a different dollar operator just for linear application. So it seems like we don't. So that's cool. Okay, thanks.
Okay, great.
Yeah. Thanks a lot for the question.
I'll kindly remove you from the stage and mark this as answered. So going back, all the questions have been answered, and it's exactly 4 o'clock. So I think this is time to thank the invited speaker for his presentation and answering our questions. And
thanks a lot for the invitation, all the attention you gave me, and these very insightful questions that allowed me to, you know, like make an even better point. Thanks a lot.
Great. Thanks a lot. I'll invite you from the stage, and then that doesn't work. I don't see why not. Okay, this also concludes this session. So I'm going to click on take a break. That means that in half an hour, we'll be back for the final session of the Haskell Symposium. If you want, you can go to the lounge and talk to other people at the tables reserved for the Haskell Symposium. Please do. And I hope to see you there. Goodbye. Hi, Ben.
Well, that's interesting.
What
Let's
is?
see if I can. I'm afraid I'm going to have to restart this browser again. It's
Oh, you can do a reload. You can probably also do a reload.
Yeah, that's fine.
If it's something with error meet. Yeah. Okay. Go ahead. I've already started the session.
Yeah. No, I saw that. I just wanted to point out, I think Arno also wanted to just sort of check his connection to the stage. If we have a few minutes before.
Yeah. Arno, why are you here? Right. Now that's Ben again. So when had we started? So if we have Arno around, but I don't see him yet.
Oh.
A minute ago, he was still in the... Oh, no, I haven't. Okay, Ben, I'm going to uninvite you for a minute.
That's okay.
Then I put Arno on. Then he can check his setup.
Oh yeah, camera's off.
Yeah, I can see you. I can hear you.
And I can probably share a screen. Just checking. Will you be able to read the Q&A and like, will you be willing to interrupt me?
As questions come in, you mean?
Yeah. So I think it's a better format for me.
Okay.
I'll read the chat, but I will trust you to read the Q&A. Oh, of course. I know what the
All right, I've seen the slides. Yeah.
Yeah.
Yeah, I'll read the Q&A during your talk.
Fantastic. Yeah, just jump in when there's an interesting question, and don't hesitate to interrupt.
And to me, every question is interesting, just so that you know.
Good, good. I like this attitude. So okay,
So
you can uninvite me. It's all fine.
I will uninvite you now, and then get them in. Or yeah. All right. Still look for Ben again. So I've invited Arnaud, and Arnaud wants things to be handled slightly differently during his talk. So whenever you put a question in the Q&A, I'm to interrupt him and ask him this question. So
yes,
think about that
rude.
when you put a question in the Q&A that you actually want it answered at that time. And otherwise you can save them up, of course.
Or you can just say you want
it
at the end in the question, I guess.
Yeah.
Share screen. Okay.
So, yeah. So, Arnaud, take it away. You have, of course, as usual, a half an hour. Yeah? So it's about, it's now 10 past approximately, so you have about till 17:40.
Sure. So, hello. Yes, I don't know where to start, but I want to point out that this is very much Jean-Philippe's work. But since he gave a 1 hour talk already, he deserved a bit of rest. So that's me. And we're going to talk about things that look like this, box and wires diagrams. I think it's a fairly frequent kind of DSL, like not the most frequent, but it just comes up from time to time. You want to do something that just best conceived of as I have boxes of things. Like functions are kind of boxes, and then you pull wires between the boxes, and you sort of assembled some kind of a circuit. For instance, when you want to write a DSL for circuits, I put a bunch of examples there. There's probably more. There's also this fairly celebrated talk by Dan Pipone at ICFP 2009, I believe, called Commutative Monads, Diagrams, and NOS. That's very much about this subject, about the sort of applications you can get out of this. Just to fix the things, so we have this, box and wires things. Just looks like graphs, but the edges have types, so they can carry types. Like in Boolean circuits, you don't really think of wires having types because they're all Booleans, but you can also make fat wires. You can draw a wire that has really width 8, and that's a type, I suppose. This comes up from time to time. And if you're a seasoned Haskell programmer and you see a thing like that, you probably think, oh, arrows. Well, let me tell you something about this. So here is a small, very small piece of circuitry or diagrammery, I don't know, with 4 boxes, a few wires, and you can write it. I wrote it as some kind of an arrow abstracted thing. Words are hard today, but using the arrow abstraction, you have the combinators. You can imagine phi and psi having type R, A, B for some arrow. You can write this function. You can write it that way, but you can also write it this way. And what's fairly crucial here is that the second way is just not the same thing. It's just a completely reasonable implementation of this diagram as an arrow, well, an element of an arrow, or morphism in an arrow. I don't know how we like to call them. And they're not equivalent. They're not equivalent up to arrow laws. And I will show you in a second. Well, actually, let's do that right now. Let's give us a bit of space. they just don't do the same thing. So among the examples I didn't speak of but wrote in the first slide, there was the idea of scientific workflow. So then I want you to think of each of these boxes as some kind of black box task, maybe a Docker container running something. And it's doing some computation, and you're a data scientist here. You're assembling these. You're assembling these, as some kind of secretary. You just, the output of phi, there's two outputs, and one goes to psi and one goes to zeta, and things like this. And when you're in this situation, you want to maximize parallelism. That's just really how I got into this, actually. So let me just show you how these things differ. Is there a question? I'm hearing some noise.
Nope.
No. Okay. So since you turned on your microphone, I thought that might be it. These things, they with arrows, they are forced to evaluate in stages. In the first case, you have phi and psi in parallel, but then you have to wait for both phi and psi to start psi. So if phi is long, despite the fact that psi has no data dependency on psi, it will wait on psi. So this is complete wasted computer time. This is bad. This is costly. And on the other hand, in the second diagram, we have these three stages where psi can start immediately as phi is done, but psi also waits for phi for absolutely no reason. And so zeta has to run after all this. And that is also bad. And in both cases, you're just wasting computing time. You just have this idle CPU there, and that's very costly. Probably the CPU is some like AWS resource that you have on the cloud that you're renting, and you're renting something to do nothing. This is not what you want to do. And this is what drew me into this work personally. And it was a real like scientific workflow of this sort, and this lack of parallelism was costing a client that was not working on this, but colleagues approached me with this problem, and we realized that there's no way to solve this problem within the confine of arrows. Truth is, despite the fact that we tend to think of arrows as missing second before zeta, this is probably true. Yes. I assume you're absolutely right. I can edit it now, but I don't think we have time. So let's imagine there's written second zeta near the 3. Thanks, Tom. Yeah, I lost track of my thoughts, but the point is that that arrows are not a faithful representation of Box and Wires diagrams. That's a misconception that we have as a community. It's not unknown, but it's something that we tend to forget about. The right abstraction is called a symmetric monoidal category because it's such a mouthful and it looks absolutely awful on slides. I'm going to abbreviate it as SMC throughout the talk, except in these boxes for some reason. So the details of what these combinators do don't really matter. What matters is we have this sort of tensor product or monoidal product between types, and there's a lot of all the rest is structural things saying, oh, I can commute the two things in the product, or I can associate the product, etc. Something unit something. So if the solution is known, and it's very much not a new observation. No more R for shuffling things around. Yes, we don't have the R. Oh yeah, that's an excellent point, Diego. Thank you. The problem, the reason why things were so synchronized there it's because of R basically. Because when you have an R thing coming on, it really expects a product of values. You have to produce the entire tuple. You can't really get the two values of the tuple independently. So this is not a new observation. I don't remember when it was first observed, but that's like in the 80s. I'm not sure I could read by then. And it's so if it's not no observation, why don't we use symmetric monoidal categories? So I cooked up a slide to demonstrate why. Okay, ignore the tensor, Jeremy. I can explain later. It doesn't matter. Yeah, you don't have to have the tensor being a parameter, or you might want to have it. It's a choice because there's isomorphic representations due to some equivalence theorem between props and symmetric monoidal categories. I don't want to speak any more word about this today, or maybe in the after session. So ignore the tensor. So if you look at this diagram, it has 4 boxes and not many more wires, and then you see how you write it as a syntactic expression with all the sigmas and the alphas. And here's alpha bar where I wrote alpha -1 in the previous line. That's because I'm an idiot. But that's a I don't know about you. I can't read this. And to be honest, I haven't written this. We have generated this expression, but that's a story for another time. You can read the paper. We talk about that a little. So yeah, it's just impossible to write these. It's impossible to read these. It's just silly. And that's where ROs shine, really. Let's take something like much simpler, like cycling types in the tensor, right? And if you do that in an arrow fashion, then it's basically a lambda. It's I don't know what you think. The arrow version is not shorter, but it's much more explicit. It's completely obvious what it does. For the record, this one I wrote by hand this week, and it took me several minutes to write the SMC version. So I had to manually check. Oh, I do this, and I associate there. Okay, and then etc. And this does literally nothing. This is this entire expression on the right does nothing. It shuffles wires around. That is the most nothingy that it will do. Whereas in arrows, well, you have to be. It's more explicit than in Haskell proper. But at the end of the day, you just write a tuple, decompose the tuple, reorder the tuple. It's super obvious. I wrote it in like 5 seconds, and I could check immediately that it was correct. It's very different, and the reason for that is that all these sigma, alpha, etc. They deal with the structure of your category, and these are the things you don't really want to think about. These are the trivial bits. So the entire SMC abstraction, to some degree, is all about the trivial bits of symmetric monoidal categories, and we don't want to write them down. And with arrows, you have these variables that do that for you, just like in Haskell. And that's not that bad. It's just that arrows are not quite what we want. And so we need a solution for this. We need a way to write SMCs. Or we abandon them. But the point is that we have found a solution. We hope it's convenient. So linear types, of course, they're coming. They had to. I guess everyone was expecting them at least. They were also in the title, so that's not really a surprise. Anywho, I'm not going to explain much about linear types besides what's on this slide, because it's been done already 3 times today, including half an hour ago. So what matters for this talk anyway is that there's a type of linear function, a log b, and that to some very formal level, linear types are, tightly related to symmetric monoidal categories. you can make a bunch of formal statements, like the internal language of symmetric monoidal categories is intuitionistic linear logic, or something like this, or intuitionistic, or like linearly type lambda calculus. Words are still hard, but the point is that linear types and symmetric monoidal categories, they're very, very closely connected, and linear Haskell exists, and so we thought, could we do something about this? Can we leverage linear types, the linear types that we have, to write symmetric monoidal category expressions without, dying a little inside every time? Because that's the crux of the matter, right? So the first idea is to leverage Connell's excellent work on called compiling to categories, where he uses a bit of template Haskell to reify an expression as core, and then he has a compiler from core to Cartesian or Cartesian closed categories. If we take the linear Haskell fragment, this should compile to symmetric monoidal categories. And look, it probably works. I don't have any somewhat different approach to a similar problem, only as GC plugin translates arrow prognotation to monoidal categories. Okay, I'm going to talk about the prognotation later and my thoughts on that. So hold that thought, Adam. So that's one approach. It probably works, but it does require plugins and template Haskell, so some metaprogramming capability. It's not really, it's not very lightweight. So we wanted to explore something sort of more linguistic, like as opposed to meta-linguistic. Right? Try to do something within Haskell. And so I'm going to show the end result, and it looks kind of like this. So use the phi. So awesome. I don't know. I haven't used the plugin myself. I thought it used template Haskell one way or another, but maybe I'm wrong. But yeah, I guess you could just use a plugin and sure. Anyway, that's my bad then. So yes, then all these boxes just appear as functions. They're written tuples, and they looks very much like functions. And they have these decode f at the end that sends my function back into the category. And that's the expression from the 4-box example. So like I don't know. I can read the expression on the right and not on the left, and I think it's big improvement. I think it's fairly readable. I can't really expect to have something any more readable than this. So it's pretty nice. So how does it work? Is it magic? No, it's Haskell, which I guess is not very different. But anyway, so terminology. Terminology. These different wires going out of the box we called a port. So I pointed at one of them, but there are 5 ports here. And we are going to represent a box phi as a function from port to ports. So here phi takes 2 ports as an argument, and it returns 3 ports because that's what's written in the diagram. So I said in the previous slide that it can't get any better than this. That's not true. We could also be able to just draw the diagram. That would be much better. But that's not something I can do in Emacs today, unfortunately. So we do with what we have. It's already good. So note the important thing. This P type here is very important. It's not a pair of an A and a B. It's a pair of a port of A and a port of B, and that's really crucial. That's sort of where the difference with arrows stands. Yes, Atom, that's what I was thinking about. Sufficiently sophisticated Haskell is undistinguishable from magic. Oh yes, I said it's a function. It's a linear function. very importantly, because of this connection between linearity and exceptions and exception. I don't know why I said that, between linearity and SMCs. So this is the library, the entirety of the library. Well, okay, I'm lying a bit. I removed a bunch of type class constraints, but apart from this bunch of type class constraints, there's the library. Here it is. So I don't know whether it matters too much to read through it. I can give a few hints. So the encode function takes something in the original category, which we call k, and transforms it into a function. It has just it's a linear function with one port in and one port out. And the split and merge function lets you transform output port and input ports of tensors into pairs of ports. Yeah, that's a comment on a previous talk this week that was really exciting about visual representations, like having code and representation mirror each other in an editor. That was fantastic. I think that was a keynote. Well deserved. So there's the R parameter here that is useful in decode that returns that, as we said earlier, transforms the function back into its original thing. Well, inside the category, this R thing is it's a technical device. It comes from Unetta lemma, if you know what that means. Except linearity is important there. We think we can remove it, but that costs an unsafe coerce, and we don't know whether it's wise. So for now, it's there. There's a link to the library here. I will give you a link to the slides at the end so you can check the references. Right. I'm actually a bit ahead. That's good. We'll have plenty of time for questions if you want. So how do we do this? I'm going to spend a bit of time here then. So we need to give some meaning to a port, and ports don't exist in a symmetric modular categories. There's no such object as a port. So you need to give them some sort of syntactic existence. So you can take a bit and say, oh, we're really concerned about the output ports because it's function from ports to ports. So we're producing ports. So these are all output ports. So we can take the output of a firebox. So we have like 3 outputs. So we can say output number 3, for instance, or 1 in this case, or 0 maybe, because I'm a computer scientist. But that doesn't really help us like manipulate them. And so we sort of gave it like to give them a sort of a mathematical existence and something well defined and composable, or something that has some theory already. What we did is we take K, the monoidal category, and we embed it into a Cartesian category, like sort of the free Cartesian category over that monoidal category. So it shares the same product. It just became Cartesian forcefully by the power of syntax. So we had all these bits of syntactic things that we can use to define a port. So we define a port by saying, oh, we take phi from the original category, and then we project the first component in that case. We might require several projections if the projections are just binary product, but the point is we project out something, and that gives us a port, and then we can assemble things using pairing in that category, which might sound scary because now we have 2 copies of phi, and we could have to run it twice or something. But the truth is that because the functions are linear, we can actually eliminate all these Cartesian special thing like the pairing and the projections, and just go away. They're just syntax, and we have a function that just removes them. this function is a bit non-trivial, and that's sort of what we spend a lot of time in the paper setting up to. But it's not very long to write. And when we have removed all these pairing and projections, then we are sure that we have deduplicated the phi's. So because otherwise that wouldn't make any sort of sense. We can't duplicate in a symmetric monoidal category. So the linearity constraint is what lets us do this. So it's I don't know, it's nice, but it doesn't really yet yield a very big understanding of the question. Like it's the proof is combinatorial, and we don't have like a good conceptual understanding of what this all means. So there's more research to do on the theory side, but it works practically well. So to wrap up, let's go back to this phi, at least 4-box example, the parallelism one. This example, so we have the arrow thing. I use the proc notation on the left because that's the most charitable way of writing an arrow thing. So I hadn't talked about that earlier because it's not really necessary for this particular example. It yields yet a third implementation of this diagram as an arrow, well, as an arrow morphism. It's very similar to the first one, but not exactly. So that's kind of fun. It has very little parallelism. And on the right, we have a very similar looking expression, but this one has the entire parallelism restored, no loss, nothing bad. It represents exactly that diagram. And so we'll stop losing money at some point, hopefully. So that's what I wanted to say. Here's a bunch of links. The QR code is a link to the slides themselves. So presumably you can use this through your screen to get the slides. So that's pretty much what I had to say. But because there's already been questions that I haven't answered or remarks, let me answer a question immediately. Jojan, yes?
All right, yeah, let's thank the speaker.
Thanks.
There are no more additional questions in the Q&A. Are there still questions in the chat?
So Adam Gundry mentioned that there's a plugin to detrigger the proc notation into SMCs, and that doesn't sound very adequate to me because of the proc notation is really tied. Like it corresponds very closely to arrows, and arrows and SMCs, they're just not quite the same thing. You can find arrows that are not symmetric monoidal categories and symmetric monoidal categories that are not arrows. And so I'm not exactly sure what the result of that would be, and maybe I should have spent more time investigating OLX plugin. I don't exactly know. I don't have a good comparison to say. It doesn't like, we've also like considered this to be a solution at some point, but it doesn't really work for us. That being said, something that I didn't say very clearly is that in our method we have this evaluation that eliminates the Cartesian thing, happens at runtime. So before you run the arrow, or the arrow, before the morphism, before you run your expression, but during the runtime of your program, could be at load time or something of your program. So it's not the same as doing that at compile time, and there's a cost to it. Of course, in cases like scientific workflows where when you run the thing, it's going to take minutes, this is insignificant and it's completely fine, but it's not necessarily good for every application. If every single of your blocks takes milliseconds to finish, then suddenly the cost of preparing the expression up front becomes significant. There's a question, I believe.
Yeah. There's a question from Jeremy.
Let's go, Jeremy.
Who's still curious about the tensors. Do you have uses for anything other than pairs or products?
Okay, so yes and no, in the sense that it's actually equivalent to have tensors be an argument or using the normal pairs, as long as you can restrict the object to a subclass of the types. So in reality, we have an object constraint in this implementation, and with just that, you can do every symmetric monoidal category. It might just require us to do an encoding. So you basically write your things as being lists of types. There's an example where in the paper where the tensor is very much not something to be interpreted as Haskell's products, Cartesian products, but we still can encode it within it. So it's a choice of ergonomics, whether you want to have more arguments in your type class, which has some issues with inference, or whether you want to have some encoding in your types. And honestly, I don't know what is the good solution. It's just an aesthetic choice that we've made for this particular paper because it was a bit shorter to deal with, presentation-wise. But it's equivalent. So because you can always arrange your types to just basically be a list of atomic whatever. And when you have a symmetric monoidal category of that way, so where the monoidal product is basically concatenations of the list, that's called a prop, and every symmetric monoidal category is equivalent in the sense of category equivalence to a prop. It's not very hard to prove, at least to sketch. It's not hard to sketch. I assume that the proof the proof in its totality is a bit involved as always, but it's not particularly difficult because you just add some arrows to make sure that the list of A and B is equivalent or is isomorphic to the A tensor B singleton, and that's basically it. And then you're done.
Okay, well, since you started answering your question, we have 3 new questions. So
fantastic.
Michael Klein, could some of this also be used to model profunctors?
Can be modeled using profunctors.
The nodes in the circuit diagrams look like profunctor composition to me, where the parallel wires could be arranged using coproducts.
Okay, so the home set of a category is a profunctor. Saying that the categories are profunctors, basically. Well, I mean it's not exactly true, but you could add. I think if you ask for your category to be a profunctor in addition, you can do more things on the wires. You have to be a bit careful about the details, though. So it's a profunctor in the theoretical sense. That doesn't. I think I'm missing the question. Profunctor.
I think there's a profunctors package, right, on the.
Yeah. So I think that's profunctor in the theoretical sense, and I think there's so when you like if you have 2 home sets, for instance, like homes are profunctors. You have 2 home sets that are consecutive. You can compose them. That gives you the set of pairs of arrows. So you still need to apply composition to get an actual object. So I think my answer is no. It depends on what exactly you mean, though. So
maybe you can take this offline.
Sure. And don't hesitate to contact me, by email if I'm not there at all.
There's a few more questions. One from Artem. Do you have some case studies implemented or in mind, quantum circuits and such, and also a straightforward way to render
Okay, so the entire paper is rendered. So the second paper, the second answer is yes. Well, straightforward. I don't know, but there's a way at least. So the entire paper is written in Haskell, and it's basically impossible to do these things correctly. At least the expressions with the sigmas and the alphas. So these are generated, but the graphs are also generated, so that we are pretty sure that we're not printing nonsense. There's a lot of graphs, so we wanted to make sure that we didn't edit the graphs and the expressions independently. We have some implementations. You can find, so if you go to the paper page, you'll find an artifact. There's a Docker container there. You'll find some things implemented. And in mind, we very much have, so we have at least been thinking about like quantum circuits, about automatic differentiation, and on my end, very much about the workflows things. As I was saying, that's just real money was on the line that made me think about that. But that we haven't implemented yet.
Okay, well, Mark has answered, and there's still more questions.
Mm-hmm.
So, if your goal is simply not to lose money, why cannot you just recover the underlying graph from any kind of representation and execute it in some maximally parallel machine?
Well, the point is that arrows just obscure the graph for you. You have these functions; they are black boxes. So of course you can maybe sort of, oh, I'm going to look at the call and modify it, but that's not, I don't have the time investment to do this sort of trick to GHC. So when you have an arrow, it's just impossible to even recover this graph, because you don't really, the R combinators just block your view, and it doesn't let you understand whether there's an actual data dependency between phi and xi, or whether it's just not there. And they sort of, they go everywhere. You can't remove them. Your code will be littered with it, and therefore the workflow will just no way through.
All right, then a question from Eric.
I don't know how it's possible.
A question from Eric Gorelik. Are you aware of any extensions to SMCs or box diagrams that might map to something interesting when viewed as linear types?
Not really. I mean, I assume that if you have some kind of a trace or some compactness things, you will just encode them one way or another. They will, I think they will basically appear as boxes as far as we're concerned. I'm not sure. It's a bit tricky. I haven't really thought about it. We can easily say, okay, we're able to execute pure function on any port. For a good definition of a port, some kind of atomic port, that's fairly easy to define, I guess. That's not particularly interesting theoretically, but that's probably useful.
Okay, there's a related question by Known, who says, well, in Dynamically Pony's celebrated talk, there was a discussion of unknotting string diagrams. Could we do something similar with this kind of scheme?
Well, you can define string diagrams as a symmetric modular category. So you can define them using this abstraction, this generic API, and then you can do the unknotting, based on the you can do some reduction rules on your syntax, basically. So I think yes. I haven't seen Dan's talk in years, so I don't remember exactly what his point was, but I assume that whatever he does, we can do. What I'm giving you here is just a way to write these things, to input these things into Haskell. Then you can do the normal thing because you have your normal SMC abstraction. Maybe what I didn't say, and I should have, is that if writing something in the SMC abstraction is painful if you do that directly. Using the SMC abstraction is very easy, really, really very easy.
Okay.
Jean-Philippe also says that there's some unknotting done by the decode function already. So,
and then maybe two final questions. So this is the question by Gergo. Is rendering based on some kind of free SMC?
I think yes. Jean-Philippe will answer in chat. Yes, he says yes.
That's the easy one. And then Conal has the final question for this talk. Did you choose to target SMCs over Cartesian category because it made translation from the lambda calculus easier, or because you wanted to exclude forgetting and duplication in your applications, or maybe other reasons?
Okay. It might be easier, but no, we started from SMCs. And the reason for that is because they are, and there's a theorem that relate them, their equational theory with the topological transformation that you can do on a graph. Like I have f and g on two wires and I can move them along, and that's visibly the same circuit. And it's also the same expression up to SMC laws. To some degree, we wanted to control forgetting and duplication, not necessarily to exclude them. In an early version of the paper, we had example that added duplication and weakening to the mix in that example, though they had to be explicit, which has pros and cons. But I don't know how to have them implicit, and the entire discussion still makes sense, because we can make circuits where in Boolean circuits you can freely duplicate things. It actually costs energy, so it's not that free, but you don't really think about that too much, I think, in practice. So you might want to just let that be inserted automatically, and we suggest that it might work, but it might not really, because if you are in Cartesian category, there's a lot of laws. Like if I have a duplication, then f twice is the same as having f, then the duplication. And preventing the machinery from applying this low backwards, so I have a single f and then suddenly I execute it twice, is not completely obvious, and we really, really don't want that to happen. So instead, just doing things up to SMC laws, and that only makes sure that duplications are not moved around and computation is not duplicated. Yeah, okay. That's my answer. I hope it answers the question.
And otherwise, I think you have to take it up in the lounge. Although, sure. Well, Arno, thank you for your talk, and thank you for answering our questions. I think we had quite a number of questions, in fact. So this concludes the formal part of Haskell Symposium. Let's say that this was the Haskell dinner, but there's also like a Haskell dessert. And Rudy asked me if there would be a possibility to have lightning talks for the last half hour. Well, the last half hour have turned into the last 9 minutes because there were so many questions. But I think I would like to give Rudy at least some time to present his idea. There were no other people that wanted to participate. So I'm going to uninvite Arno.
Cheers,
Thank
everybody.
you, Arno. And I'm going to look for Rudy. And there's Rudy. Invite him to the stage and give him his 9 more minutes, I think. Hi, Rudy.
Hi again. Yeah, thanks for.
If you want to present something, this is your time. And,
sure. So let me share my screen here. Entire screen 2. Guess.
See it? Okay.
Can everyone see it?
I can see it.
Yeah, cool. Great. Okay, so should I start?
Yeah, go ahead. So a live demo of the Express library. So Rudy talked about this yesterday, in case you weren't there.
Yes.
He had, but maybe so it's the application of dynamically typed Haskell expressions. Go ahead.
Okay, cool. So as Julian said, yesterday I presented my paper, Express, Applications of Dynamically Typed Haskell Expressions. And I would like to do a quick live demo of the Express library to show you how it works in live and in practice. So let me move to the terminal and let me open up GHCI, right? And let me import data.typable, just so the types are nice, and then I import data.express, which is the library I presented. And what can we do with this library? So as I showed in my presentation earlier, we can encode, one of the things we can do is encode Haskell values as express, as expressions. So here I will encode the value 1 of type int as an expr. So I have here, if I check the type of 1 is an expr. And if I show this value 1, it will show that it is a 1 of type int. And this will also work when you evaluate it directly on JCI. And we can get this value, we can get the value that is encoded back as a regular Haskell type. So if I run evaluate 1, that's the type maybe int, I'll pull back the value that I had encoded. So just the one value. And if I try to evaluate this as the wrong type, I'll get nothing. There's also the function eval, which takes a default value, and and of course that returns the default value when the type doesn't match. Okay, so what else can we do with this? So let me try to encode another value, plus, which is the value plus, and then I encode the function plus. I don't have type applications enabled, so I have to type the complete type. So I have plus encoded as an expr. So this is an expr. And I can write plus apply to 1, apply to 1. And I can really go wild with this. So I can have plus, apply to 1, apply to 1 again. And I get an expression. And of course, I can use evaluate again on plus apply to 1, apply to 1. So type maybe and get the value back. So that's the sort of stuff you can do with this. And the idea here is that we not only encode dynamic values like in data.dynamic, but we extend it with pretty printing and delay devaluation and even expression matching. In my talk, I showed also a couple of examples of a small library I made using Express to synthesize functions that match a certain set of argument result pairs. So I showed the function square, a partially defined function square, and then I defined a list of primitives that I thought were useful in full implementation of square, namely 0, 1, plus, and times. And this library you can implement using Express. If you write synthesize square with the primitives, you get square of x is equal to x times x. And this is a fully defined definition of square. I show the same thing with factorial by adding full dar and num from 2. And it does print factorial, the product of 1 through x. But of course, this is supposed to be live. So let me try to show you this live. So I'm already in the right folder. So here I have the microconjure library, which is the library that synthesize functions. And it's pretty short. It has 85 lines if you include white space. And if I run a clock on it, it has 65 actual lines of code. So with this small library, I can import it into a file. So here I have a file, which I imported the microconjure I just implemented. I just showed you the implementation. I import also the Express library. And I declare the square partial function, the factorial partial function, and the primitives I just showed you. And then I write conjure square with the primitives or conjure factorial with the primitives. And if I run this, run Haskell arith, it does print the two functions, and it's, let me run a time here. It runs pretty quickly. And another example is I prepared a list example as well, so it also works for list functions involving lists. Here's a partial definition of sum that folds with plus. Here's a partial definition of second, the function that takes the second element of a list, and a partial definition of append, which is you just append to lists, and this is just defined for lists with size 1 and size 2. And at the end here, I'm trying to conjure these functions with this weird list of symbols here, which I won't have time to go through. But if I do a run Haskell list and time, and it does generate some second and append using the folds here, head and tail. So it kind of, and of course it has limitations. Like for example, if I were to try to generate reverse, so if I were to write conjure, reverse prime, prims, it's not able to generate everything, and it's pretty limited because this is just a proof of concept to show that Express can be useful in the implementation of program or function generation. There's a paper which details this. It has lots of details and goes through step by step of how each of the example applications work. You can find also more info in the GitHub page of the project. And it's on Hackage. You can Cabal install it and run the examples I just showed you. And the paddock documentation is pretty comprehensive. So there's also that as well if you want more info. And that is actually all for the live demo. Thank you for taking the time to watch.
Okay, thanks. I actually have one question of you, Rudy. So in the case of factorial, it could also take the multiplication of the list from x down to 1. Why does it prefer your version?
Actually, for that one, I would need to provide a num from then to, so that it would be able to decrement. Okay. So it ended up the functions it is able to generate are very dependent on the symbols you provide to the actual small library. So yeah,
that's also why it doesn't generate doesn't use 2x, for example, which would also work.
Yes, exactly. Because I don't have
because 2 was not in the list of constants.
Yeah. Okay. Exactly.
Thanks. Well, I mean, this is 1 minute before 6, so this is really the end of the Haskell Symposium. I thank you all for coming. I hope you had a good time. I hope you learned a lot.
Yeah, I think Julian, I think your sound is not working. So Richard is just joining.
I was just going to say the same thing. Unfortunately, as you were wrapping things up, your mic cut out again. Still we can't hear you. I assume Yurian will be back momentarily. I think in the past when he's had trouble, sometimes just logging out and logging back in again would allow him to change his microphone and then get back in.
I'm back.
Yes, and we can hear you.
Cool.
But now I can't hear you. Is it okay again?
Yes, we can hear you, but we cannot see you.
But I can't hear you. That's,
oh.
Can you hear me? Yeah, we can hear Julian.
Well, actually, so I don't have a final goodbye. I hope that many of you are inspired to write some papers for next year's Haskell Symposium. That, of course, we hope will take place physically in Slovenia, Ljubljana. And for me, it was fun organizing this. And even with some of the problems that audio and AirMeet could give us, but I think it went fairly well. So thank you all, and see you next time. Doesn't this work? Yeah.